Hey guys, good morning and welcome back again to your Unacademy NEET English channel. Let me know quickly in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you, my dear students. Quickly in the chats. Good morning. Good morning and welcome back. Good morning and welcome back, people. So what's up? How are you all doing? All great? All well? How's the preparation going? All right. Thank you so much. Thank you. Well, yes, I'm back to the channel after 7 to 8 days. Let's start from the basics. Don't worry, I start all my sessions from basics only. Don't worry about that. Every single thing is going to be detailed. Every single thing is going to be detailed. And let me tell you, today we are going to complete your class 11th physical chemistry. So basically, we'll be completing mole concept, atomic structure, redox reaction, chemical equilibrium, ionic equilibrium, and thermodynamics. Okay, these are the chapters which I'll be covering in the today's session. Well, the duration of the session is going to be again 10 to 12 hours for sure. Okay, 10 to 12 hours for sure it's going to be. So you would have to be with me till the end. And one thing I'm going to tell you, after watching this complete session, you would be in a position to solve a lot of questions from your modules or whatever material you'll be having at this point of time. Okay? So can you quickly let me know in the chats from which part of the country you guys are watching me from right now? I just want to know which state you are from. I just want to know which state you are from. Quickly. I just want to know in the chats. I just want to know in the chats which part of the country you guys are watching me from right now. The chats are running fast. Okay. Tamil Nadu, Uttar Pradesh, J&K, Kerala, Telangana, Assam, Haryana, Karnataka, Maharashtra, AP. All right. Pondicherry, Mizoram, Haryana, Sikkim, Bangalore, Bihar, okay, Punjab. All right, people. All right. I think we are good to go, yeah? I think we are good to go. Well, the first thing, my dear students, before starting this particular session, let me tell you the handwritten PDF of the today's session. The handwritten PDF of the today's session I'll be sharing on my Telegram. If you are not the part of the Telegram channel yet, be the part of the Telegram channel. The name of the Telegram channel is Wassim Bhat Chemistry Official. Wassim Bhat Chemistry Official is the name of the Telegram channel on which I shall be sharing the handwritten PDF of the today's session. Okay? On which I shall be sharing the handwritten PDF of the today's session. So if you are not the part of the Telegram channel yet, be the part of the Telegram channel as quick as possible. Because all the important stuff I'll be sharing here. And one more thing. Once we complete the session, on this particular Telegram, I shall be sharing a DPP with you. You're supposed to solve that DPP. Okay? You are supposed to solve that DPP. Sir, is it live for Re-NEET? Yes. This is live for Re-NEET, of course. So we shall be discussing your complete class 11th physical chemistry today. Again, let me repeat. Whole concept, atomic structure, redox reaction, chemical equilibrium, ionic equilibrium, and your thermodynamics. These are the 6 chapters which I'll be covering in the today's session. Okay? These are the 6 chapters which I shall be covering in the today's session. So watch this particular session till the end, my dear. Till the end. All right. The first chapter with which we shall be starting the session, my dear students, that is something which you all would be already knowing. What is that? The first chapter with which I shall be sharing this particular, with which I shall be starting this particular session, that is going to be your first chapter, your mole concept. Now, before starting the chapter mole concept, you should first of all know what are the topics from which questions are asked in the chapter mole concept. What all topics are there in the mole concept chapter from which questions are asked? Let me talk about those topics first. My dear students, the first and the basic topic will be the calculation of moles. Calculation of moles. This is the first topic. The second topic is going to be your average atomic mass. Average atomic mass of isotopic mixture. This is the second topic from which questions have been asked. Questions will be asked. My dear students, the third topic which we shall be discussing here, what is that going to be? That is going to be your stoichiometry. That's going to be your stoichiometry. And after stoichiometry, it's going to be your one more important topic, your limiting reagent. And my dear students, at the end, it's going to be empirical formula and molecular formula. Well, my dear students, these are first of all the topics from which the questions will be framed, the questions will be asked in your Re-NEET examination as well. And I shall be covering these topics in detail over here. Perfect. So already just give me some thumbs up in the chats. Someone is saying, I hate this chapter. Don't worry, you'll love this chapter after watching this video. Tell me guys in the chats, quick. Is everyone ready? Let me know with the thumbs ups quick. Quickly. Okay, one more thing which I would want to share with you. What is that? I'll be giving you the breaks in between as well. Right? Once we complete a chapter, then I'll give you the break of 20 minutes. One more chapter, 20 minutes break. One more chapter, 20 minutes break. So I'll keep the breaks in between as well. You should not get tired too. And I should not get tired too. Yeah? So don't worry about the breaks. Lunch break, everything will be given. You just be with me till the end today. And you are going to love it for sure. Every single thing will be from basics only, from scratch only. Yes, completely NCERT based. Okay? Well, if you can make notes alongside with me, then go ahead. Or you can wait for the handwritten PDF of the today's session, which I'll be sharing at the end of the session on my Telegram. All right? Duration will be almost like 10 to 12 hours. Perfect? Chalo guys. Let's get going then. Let's get started with the today's session. My dear students, I am going to start this chapter with one statement. And what is that statement exactly? I am going to write one simple statement which you will be remembering from now onwards. What is that? That is 1 AMU, which is also called as 1U, which is also called as 1D. 1 AMU, 1U or 1D. What is meant by this 1 AMU? Let me tell you, 1 AMU, it is defined as 1/12th of the mass of carbon 12. 1/12th of the mass of carbon 12. And let me tell you, my dear students, this 1 AMU is also equal to 1.66 into 10 raised power minus 24 grams. And it can be also written in terms of Avogadro's number as 1 divided by Na grams. This is the first statement, my dear students, which I would want every one of you to remember from now on. 1 AMU. AMU stands for atomic mass unit. U stands for unified mass. D stands for Dalton. So let me write their full forms as well. AMU stands for atomic mass unit. Atomic mass unit. This U over here, this U stands for unified mass. Unified mass. And this D over here, which I mentioned, this D stands for Dalton. So this is the first statement which I would want every one of you to remember from now onwards. Okay? Sir, sound please. Am I not perfectly audible? Just a second, let me check. I'm perfectly audible. I think there is a problem from your end. Yeah? It's perfect. No, from my end, voice is completely fine. I think you have to increase the volume of your phone or laptop from where you are watching me. Okay. Perfect, guys. Let's move on. So first of all, the first statement which I gave you, I would want every one of you to remember this from now onwards. 1 AMU, which is also called as 1U, which is also called as 1D. And how do we define it? 1/12th of mass of carbon 12 atom. Its value in grams is equal to 1.66 into 10 raised power minus 24 grams. And in terms of Avogadro's number, you can write it as 1 divided by Na grams as well. Point number 1. Point number 2, my dear students. There are basically 3 terminologies which you should first of all be familiar with. What are those 3 terminologies? The first terminology is what you call as atomic mass. First terminology is what you call as atomic mass. The second terminology is what you call as molecular mass. Molecular mass. And the third terminology is something I call as molar mass as well. These are the 3 basic terminologies which you should know before starting the chapter. And my dear students, what are these basic terminologies? What is the meaning of these basic terminologies? Let's have a look. How do we define the term atomic mass? Atomic mass is nothing but it is the mass of one atom of an element. It is the mass of one atom of an element. It is the mass of one atom of an element. All of you must be knowing. For example, if I talk about nitrogen, I'm asking you, what is the atomic mass of nitrogen? All of you would answer, the atomic mass of nitrogen is 14 AMU. The atomic mass of nitrogen is 14 AMU. That means this is the mass of one atom of nitrogen. This is the mass of one atom of nitrogen. I can say one atom of nitrogen is 14 times heavier than 1 AMU. I can say one atom of nitrogen is 14 times heavier than 1 AMU. Right? But dear students, you can do some more things as well. You can write this 14 AMU as 14 multiplied by 1 AMU. You can do that. Right? And at the same time, instead of 1 AMU, you can write 1.66 into 10 raised power minus 24 grams. Okay. And instead of same 1 AMU, you can write 1 divided by Na grams as well. Perfect. So first of all, I'm talking about nitrogen, whose atomic mass is 14 AMU. That means mass of one atom of nitrogen is 14 AMU. It means that one atom of nitrogen is 14 times heavier than 1 AMU. It means that one atom of nitrogen is 14 times heavier than 1 AMU. At the same time, I would say this is the mass of one atom of nitrogen in grams. Even you can say this is the mass of one nitrogen atom in grams. Even you can say this is the mass of one atom of nitrogen in AMU. Okay? So what is atomic mass in short? The mass of one atom of an element. For example, I'm talking about oxygen. What is the atomic mass of oxygen? You'll say 16 AMU. That means the mass of one atom of oxygen is 16 AMU. You can say one atom of oxygen is 16 times heavier than 1 AMU, right? All those things you can do easily. Now, my dear students, how do we define the term molecular mass? Molecular mass. Molecular mass, in short, is simply defined as the mass of one molecule. The mass of one molecule of a substance. The mass of one molecule of a substance. For example, if I take NH3, I have taken ammonia over here. I want you to calculate its molecular mass. I want you to calculate its molecular mass. How do you calculate the molecular mass exactly? Pretty much simple. What is the atomic mass of nitrogen? That is 14 AMU multiplied by how many nitrogen atoms? 1 plus. What is the atomic mass of hydrogen? 1 AMU. How many hydrogen atoms? 3. When you solve this, you get the value as 17 AMU. What is the 17 AMU? I would say this is the mass of one molecule of NH3. This is the mass of one molecule of NH3. I can say one molecule of NH3 is 17 times heavier than 1 AMU. I can say one molecule of NH3 is 17 times heavier than 1 AMU. If I want to write the mass of one molecule of NH3 in grams, I can do that too. I can write 17 multiplied. Instead of 1 AMU, I can write 1.66 into 10 raised power minus 24 grams. Or instead of 1 AMU, I can write 1 divided by Na grams as well. Okay? These are the things, my dear students, which you need to remember. So what is molecular mass? It is simply defined as the mass of one molecule. As I took the case of NH3, I'm saying the molecular mass of NH3 is 17 AMU. It means that one molecule of NH3 is 17 times heavier than 1 AMU. This is the mass of one molecule of ammonia in grams. Even this is the mass of one molecule of ammonia in grams. Okay? Now, people, how do we define the term molar mass? Molar mass is simply defined as the mass of 1 mole of a substance. The mass of 1 mole of a substance. Or you can say it is defined as the mass of 6.022 into 10 raised power 23 particles of the substance. The mass of 6.022 into 10 raised power 23 particles of the substance. Now, people, for example, imagine that I'm asking you, what is the molar mass of carbon? For example, I'm asking you, what is the molar mass of carbon? What does that mean? That means I'm asking you, what is the mass of 1 mole of carbon? That means I'm asking you, what is the mass of 6.022 into 10 raised power 23 atoms of carbon? Okay? And let me tell you, if I talk about carbon, what is the atomic mass of carbon? That is 12 AMU. What is the molar mass of carbon? You'll write 12 as such. Instead of AMU, you'll write grams. This 12 grams is what I call as the molar mass of carbon. Okay? This 12 grams is what I call as the molar mass of carbon. This is the mass of 1 mole of carbon. This is the mass of 6.022 into 10 raised power 23 atoms of carbon. For example, I'm talking about nitrogen. What was the atomic mass of nitrogen? 14 AMU. Molar mass of carbon will be 14 grams. Basically, you just have to replace AMU with what? You just have to replace AMU with grams. That's all. Perfect? That's all. So I believe these three terminologies are very much clear to you. One is atomic mass, one is molecular mass, and one is molar mass. Okay? Now, my dear students, there is one more terminology which I would want to share with you. What is that? Or before mentioning one more terminology, there is one simple question that I'm going to give you right here. One simple question that I'm going to give you right here. What is this simple question exactly? The question is saying, if 1U is defined as 1/24th of the mass of carbon to an atom, if 1U is defined as 1/24th of the mass of carbon to an atom, then calculate the molecular mass of carbon dioxide on new scale. These sort of questions you can get in your examination. How do we deal with these questions? Try to understand. First of all, my dear students, how did we define 1U? We defined 1U as 1/12th of the mass of carbon to an atom. This is how we defined 1U. As per the question, how they are defining 1U? They are defining 1U as 1/24th of the mass of carbon to an atom. They are defining 1U as 1/24th of the mass of carbon to an atom. Okay? In order to differentiate, I'll be calling this as U dash. Just to differentiate the two scales. Differentiate the two scales, I'm calling this as 1U dash. Okay? Call this equation 1. Call this equation 2. your first step always will be to divide these two equations. Your first step always will be to divide these two equations. My dear students, when you divide these two equations, what do you get? You get u divided by u dash. You get u divided by u dash is equal. This term cancels out. In the numerator, you get 1 by 12. In the denominator, you get 1 by 24. And this value comes out to be 2. So u divided by u dash is equal to 2. I can say u is equal to 2 times u dash. I got to know u is equal to 2 times u dash. Now, my dear students, what am I supposed to calculate? I need to calculate the molecular mass of carbon dioxide. Molecular mass of carbon dioxide. As per which scale? As per new scale. As per new scale. Right? As per u dash. Do we already know the molecular mass of carbon dioxide as per our scale? Do we already know the molecular mass of carbon dioxide? Absolutely. What is that? That is 12 plus 16 into 2. The value comes out to be 44u. This is the molecular mass of carbon dioxide as per our scale. As per our scale. As per u. But I don't need the answer in u. I need the answer in terms of u dash. So what do I need to do is, I'll write 44 as such. And instead of u, I'll write u 2 times u dash. Okay. Instead of u, I wrote 2 times u dash. So the value comes out to be 88 u dash. So what is this 88 u dash? I would say this is the molecular mass of carbon dioxide as per the new scale. Right? These sort of questions you get frequently in your examination. My dear students, point number 2. Point number 2. Point number 2. There is a topic called as average atomic mass of isotopic mixture. Average atomic mass of isotopic mixture. Okay. First of all, you should know what exactly isotopes are. Try to understand. This is an important topic and frequently questions are asked from. Frequently questions are asked from. Understand properly what I'm going to say. My dear students, imagine that you have got an element X. Imagine that you have got an element X. And this element has got, for example, 2 atoms. This element has got 2 atoms with same atomic number, but different atomic mass, M1 and M2. I took an element X. It has got 2 atoms with the same atomic number, but different atomic mass. Let me tell you, I'll be calling these atoms as isotopes. I'll be calling these atoms as isotopes. And my dear students, whenever element has isotopes, whenever an element has isotopes, for that element which has isotopes, we do not define the normal atomic mass of that element. That particular element which has isotopes, we do not define the normal atomic mass of that element. What do we define? We define average atomic mass. We define average atomic mass for that element which has isotope. Now, my dear students, in order to calculate the average atomic mass of an element which has isotopes, what do I need? I need percentage abundances. I need percentage abundances of these isotopes. What are percentage abundances? You'll get that in some time. You'll get that in some time. First of all, whenever you see an element has got the isotopes, for that element, we do not define the normal atomic mass. What do we define? We define average atomic mass. And in order to calculate the average atomic mass, what do I need? I need the percentage abundances of these isotopes. And let me tell you, percentage abundances are represented by A% and B% respectively. And once we get the value of A and B, then there's a formula to be used. Formula is M1 into A plus M2 multiplied by B divided by A plus B. This is the formula by means of which you can calculate average atomic mass of an element which has what? Which has isotopes. Point number 1. Point number 2, my dear students, remember the sum of the percentage abundances. The sum of the percentage abundance of all the isotopes, that's always equal to 100. The sum of percentage abundances of all the isotopes is always equal to what? Is always equal to 100. Okay? Now, my dear students, for example, you have got an element chlorine. Imagine that you have got an element chlorine. As you all must be knowing, chlorine has got 2 isotopes. One is Cl35, one is Cl37. Okay? Now, since chlorine has isotopes, so I am not going to define the normal atomic mass of chlorine. I'll be defining the average atomic mass of chlorine. And my dear students, in order to calculate average atomic mass, what do I need? I need percentage abundances of these isotopes. And let me tell you, my dear students, it has been observed experimentally that the percentage abundances of these isotopes is 75%, and 25% respectively. Now, since you have an element, it has got isotopes. So you are going to define average atomic mass for this element. In order to calculate average atomic mass, what do I need? I need percentage abundances, which are represented by A and B respectively. This is the value of M1. This is the value of M2. So my dear students, I can use the formula. Now, what is going to be the formula? Formula you already know, that is M1 multiplied by A plus M2 multiplied by B divided by A plus B is always 100. Now put the values, that's it. M1 into A, 35 into 75 plus M2 multiplied by B, 37 into 25. 37 into 25 divided by A plus B is 100. When you solve this, the value comes out to be 35.5 AMU. So what is the 35.5 AMU? Is there the normal atomic mass of chlorine? No. It is the average atomic mass of chlorine, my dear student, which I was supposed to calculate. Right? Am I clear with this? Everyone in the chats? Quickly. Why are some people saying voice is not clear? Are you not listening to this? It's probably clear. What are you saying? Sound is all clear, okay? Whosoever is talking about the sound now, I'm going to block that person, okay? Understand? I'm going to block them right now. Whosoever is saying sound is low, sound is not perfect, sound is all perfect, I just checked it. Okay? Either listen to the class or you can go to some other class. Okay? Don't need to disturb the students in the chat. Just give me a second. Perfect. I believe this particular topic is clear. Now, let's do one thing. Let's try to solve this question. This is your asked question. It has been asked. Okay? Look at the question carefully. Look at the question carefully, people. Look at the question carefully. The question is pretty much simple. You have got an element boron. And it is mentioned that boron has two isotopes. One is B10, one is B11. The percentage abundance of B10 is given to me as 19%. And the percentage abundance of B11 is equal to 81%. What do I need to calculate? I need to calculate the average atomic mass of boron. Percentage abundances we represent with A and B. You know that already. This is the value of M1. This is the value of M2. Therefore, the formula becomes M1 into A. So it is 10 multiplied by 19 plus M2 multiplied by B. It is 11 multiplied by 81 divided by A plus B is what? 100. When you solve this value, it comes out to be 10.81 AMU. So what is this 10.81 AMU? It is the average atomic mass of the boron, which I was supposed to calculate as far as the question is concerned. Right? Perfect. Similarly, my dear students, let me give you one more question. For example, you have got the question like this. You have got an element X. Imagine that it has got two isotopes. One is X35, one is X37. For example, the average atomic mass of X is given to me in the question. That is 35.5. Average atomic mass of X is given to me in the question. Average atomic mass is given to us in the question as 35.5. I am asking you to calculate the percentage abundances of these isotopes. I'm asking you to calculate the average atomic mass of these isotopes. Can you give it a try? Can you give it a try? Can you give it a try quick? See guys, first of all, few minutes back I told you, the sum of percentage abundances of these isotopes is always equal to 100. The sum of percentage abundances of these isotopes is always equal to 100. Therefore, let's do one thing. Let the percentage abundance of this isotope is X%. So this automatically becomes 100 minus X%. It automatically becomes 100 minus X%. Because their sum has to be 100. Therefore, I would say this is the value of A, this is the value of B, this is the value of M1, and this is the value of M2. Now we can directly use the formula. I can say M1A plus M2B divided by A plus B. A plus B is 100. And this value as per the question is 35.5. So M1 is given to me as 35. A value is given to me as X. M2 value is given to me as 37. B value is given to me as 100 minus X divided by A plus B is 100. And this value as per the question is 35.5. Now, when you do the cross multiplication and stuff, you get the value of X here as 75%. And what was this X? X was the percentage abundance of the first isotope. Therefore, the percentage abundance of second isotope will be 100 minus X, 100 minus 75. That will be 25%. So these sort of questions can be asked in your exam, right? It is a general question, a standard question. Now, the values can be changed in the exam. Rest, the pattern is going to be the same. Got it? Now, my dear students, there is something called as calculation of moles. How do we calculate moles of different substances? How do we calculate the moles of different substances? Let me tell you, there are few formulas, my dear students. There are few results with the help of which you can calculate moles of particular substance. There are few formulas by means of which we can calculate moles of different substances. The first formula, what is that? Number of moles of a substance is always equal to given mass of the substance in grams, divided by molar mass of the substance. Given mass of the substance in grams divided by molar mass of the substance. This gives me what? It gives me number of moles of the substance. And let me tell you, this particular formula, it is valid for solids, liquids, as well as gases. This particular formula is valid for solids, liquids, and gases. Sir, please solve PYQ as well. This was your PYQ in JEE Mains. Okay? This was your PYQ in JEE Mains as well. These are PYQs only which I'm solving. Some JEE Mains, some NEET. It is just, I'm not mentioning that this was asked in year 2022, 2023. These are otherwise the PYQs only. Don't worry. Okay? Chalo. The first formula, my dear students, by means of which we calculate number of moles of the substance. What is that? That is given mass of the substance in grams. Given mass of the substance in grams divided by molar mass of the substance. This particular formula is valid for solids, liquids, as well as gases. Point number one. Point number two, my dear student. There is one more result by means of which you can calculate moles. Number of moles of the substance. That's equal to given number of particles divided by Avogadro's number. This is one more result with the help of which you can calculate moles of a substance. And this formula again is valid for solids, liquids, as well as gases. The third formula which I'm writing over here. Number of moles. This third formula is valid for a gas. Number of moles of a gas. And the gas should be present at STP, standard temperature pressure. The formula to calculate is going to be given volume of the gas in liters divided by 22.4 liters. This is the formula by means of which you can calculate number of moles of the gas. But the gas should be present at STP. I believe this is clear. These are the three formulas, my dear students, which you are supposed to remember to calculate what? To calculate moles of a particular substance. For example, calculate the number of moles in 160 grams of NaOH. So if you look carefully, we are given with the mass of NaOH and we are supposed to calculate moles of NaOH. So I'll say number of moles of NaOH will be equal. Given mass of NaOH, which is 160 grams, divided by molar mass of NaOH. You can easily calculate molar mass of NaOH. Sodium is 23, oxygen is 16, hydrogen is 1. Do the sum of these, the value comes out to be 40. So the value comes out to be 4, right? So you can basically say 160 grams of NaOH means 4 moles of NaOH. 160 grams of NaOH means 4 moles of NaOH. Look at the second one. We are given with the volume here, liter. Liter means volume. We are given with the volume of the gas. We are supposed to calculate moles. I'm writing number of moles of carbon dioxide is equal to given volume of the gas in liters divided by 22.4 liters. The value comes out to be 3, right? The value comes out to be 3. As simple as that. Similarly, people, over here we are given with the particles. We are given with the particles. And when you are given with the particles and you are supposed to calculate moles, what do? Number of moles of carbon will be equal to given number of particles divided by Avogadro's number. The value of Avogadro's number you already know. So therefore, the value comes out to be 4. Over here also, my dear students, you are given with the molecules. You are given with the particles. If you are given with the particles and you are supposed to calculate moles, so I'll write given number of particles divided by what? Divided by Avogadro's number, right? The value comes out to be 80. So basically, you have got 3 formulas by means of which you can calculate number of moles of a substance. Given mass divided by molar mass, number 1. Given number of particles divided by Avogadro's number. Given number of particles divided by Avogadro's number. And number 3, given volume of the gas in liters divided by 22.4 liters. Okay? Perfect. Now, my dear students, let me show you one simple diagram with the help of which you can solve some basic questions which are there in mole. Some basic questions you can solve by the help of the diagram which I'm going to give you right now. And what is that diagram all about? Let's have a look. My dear students, as I told you, how many ways do we have to calculate moles of a substance? How many ways do we have to calculate moles of the substance? First thing is, either I am given with the mass of the substance, or I am given with the number of particles of the substance. Or I will be given with the volume of the gas in liters at STP. Right? Now, people, tell me one thing. If we are given with mass and we are supposed to calculate moles, what am I supposed to do? Given mass divided by molar mass. That gives me moles. Now, reverse of it. If moles are given, mass is to be calculated. Then what do we need to do? Moles multiplied by molar mass. That's going to give you what? That's going to give you the mass. Okay? Given mass of the substance divided by molar mass of the substance. That gives me moles. Moles multiplied by molar mass. That gives me mass. Similarly, my dear students, remember, if number of particles are given and we are supposed to calculate moles, then remember, given number of particles divided by Avogadro's number. That gives me moles. Just reverse of it. If moles are given, particles are to be calculated. Then multiply moles with the Avogadro's number, you will be getting the particles. Similarly, my dear student, if volume is given and we are supposed to calculate moles, then given volume of the gas divided by 22.4 liters. That gives me moles. Now, if moles are given, volume is to be calculated. Then moles are to be multiplied with what? 22.4. You will be getting the volume. Right? Am I clear? Then how long this chapter? This chapter will be for 1.5 hours. Am I clear with this, people? Am I clear with this particular diagram? Now the point is, how do we exactly? Sir, P block. Bro, don't see the title of this particular session. It is complete class 11th physical chemistry. Since when P block has come in physical chemistry? That will be done in inorganic. Okay? Don't write some random stuff. First, read the title of the session. See who is teaching. See what am I teaching. Then keep on comment. Don't comment like P block, organic. This is the physical chemistry session going on, right? Other chapters will do in inorganic. P block, your bonding, your periodic classification. Okay? I believe this particular diagram is like very much clear to you. Now let's have a look exactly what kind of questions can be solved from this particular diagram. Let's have a look. Let's have a look, people. For example, these are the two questions, two basic questions. I believe you can easily solve them. I believe you can easily solve. Have a look, people. Calculate the mass of 67.2 liters of carbon dioxide. We are supposed to calculate the mass of 67.2 liters of carbon dioxide. So first of all, what are we given with? We are given with volume. We are supposed to calculate mass. We are given with volume and we are supposed to calculate mass. We are given with volume. We are supposed to calculate mass. So I will be starting from volume and I'll have to reach till mass. Now, which all arrows should I follow to go from volume till mass? The first arrow is going to be this one. The second arrow is going to be this one. These are the two arrows which I'll be following to go from volume till mass. Right? So, what is my first step, my dear students? First step is convert the given volume into moles. So I'll say, convert the given volume into moles. So I'll say number of moles of carbon dioxide is equal to given volume of carbon dioxide in liters divided by 22.4 liters. The value comes out to be 3. So what is this 3? This 3 is basically the value of moles. Now moles are to be multiplied with the molar mass. You'll be getting the mass. So I'll say mass of carbon dioxide will be equal to moles of carbon dioxide multiplied by molar mass of carbon dioxide is 44 grams. The value comes out to be 132 grams. So you can directly say 67.2 liter carbon dioxide at STP will have the mass of how much? Will have the mass of 132 grams. I believe this is clear. Now, my dear students, look at the second question. The second question. Calculate the number of molecules. Calculate the number of molecules which are present in 440 grams of carbon dioxide. So look carefully. We are given with the mass. We are supposed to calculate particles. We are given with mass. We are supposed to calculate particles. So basically, in this question, we are given with what? We are given with mass. We are given with mass. And we are supposed to calculate what? We are supposed to calculate particles. So I will be starting from mass and I'll have to reach till particles. So follow all the arrows which take you from mass till particles. So which all arrows I should follow? This is the first arrow I'll be following and this is the second arrow I'll be following. So two steps. First step is convert mass into moles. So given mass divided by molar mass gives me moles. Then moles multiplied by Avogadro's number gives me particles. So the question will be done in two steps. The first step is number of moles of carbon dioxide is equal to given mass of carbon dioxide divided by molar mass of carbon dioxide. The value comes out to be 10. Second step. Molecules means particles. Particles of carbon dioxide will be equal to moles multiplied by Avogadro's number. This is the final answer of the question. As simple as that. Perfect. Now, my dear students, will you be able to solve this question on your own? Check it out carefully. We are supposed to calculate the number of moles present in 96 kg of X. So basically, imagine that you have got the container. In the container, we have got 96 kg, which means 96,000 grams. In the container, there is 96,000 grams of X. In the container, there is 96,000 grams of X. What am I supposed to calculate? I'm supposed to calculate moles. So basically, I'm given with mass, I need to calculate moles. I'm given with mass, I need to calculate moles. So moles of X will be equal to given mass of X in grams divided by molar mass of X. Divided by molar mass of X. Now, given mass of X is how much? 96,000 divided by. Am I given with the molar mass of X? No, I'm not given with the molar mass of X. I'm not given with the molar mass of X. Remember, my dear students, remember, molar mass of a substance X is always equal to mass of one particle of the substance, mass of one particle of the substance in grams, multiplied by Avogadro's number. This is one result which I would want you guys to remember directly from now on. Molar mass of some substance X is always equal to mass of one particle of the substance in grams multiplied by Avogadro's number. Now tell me, what is the mass of one particle that's given to me? The mass of one atom of X is given to me as 4 × 10⁻⁻23 grams. multiplied by. Avogadro's number is simply 6 into 10 raised power 23. This term cancels out. 6 fours comes out to be 24 grams. So what is this 24 grams? It is the molar mass of X. It is the molar mass of X. So what am I supposed to do? Given mass of the substance in grams divided by molar mass of the substance. The value comes out to be 4,000. So this is something I was supposed to calculate. I was given with mass. I wanted to calculate moles. So given mass divided by molar mass. Now, given mass is given. Molar mass was to be calculated. And molar mass is nothing but mass of one particle of the substance multiplied by Avogadro's number. As simple as that. As simple as that. Right? As simple as that. Look at this question, guys. Look at this question. Look at this question. Calculate the atoms. Atoms means particles. Calculate the atoms. Atoms means particles. Calculate the molecules. Molecules means particles. We are given with mass here. And mass is in grams. We are given with mass. We are supposed to calculate particles. So first, convert mass into moles. So number of moles of helium is equal to given mass of helium in grams divided by molar mass of helium. The value comes out to be 4. Now, since we got the moles, therefore atoms will be moles multiplied by Avogadro's number. This is the answer of the first question. Simple. Just using the diagram that I gave you right now. But here, my dear students, again, we are given with mass only, but mass is not in grams. We are given with mass only, but mass is not in grams. We need mass in grams. We need mass in grams. So I can write 16U as 16 multiplied by 1U, or I can say it can be written as 16 multiplied by 1 by Na gram. Because I've told you already 1U is nothing but 1 by Na gram. So I have now the mass of helium in grams. So the first step is moles of helium will be equal. Given mass of helium in grams, divided by molar mass of helium. The value comes out to be 4 by Na. Right? So these are the moles. Now, atoms of helium will be equal to moles multiplied by Avogadro's number. Moles multiplied by Avogadro's number. The value comes out to be simply 4. So the point of solving this question is, sometimes you'll be given with mass in U. So first of all, you have to convert this in grams. Then use the formulas. That's it. Okay. Similarly, if you look at this question, calculate the molecules. Molecules means particles. We are given with mass. We have to calculate particles. But the mass is in U. I need the mass in grams. So I'll write 126. Instead of U, I'll write 1 divided by Na grams. So this is the mass of HNO3 in grams. Now, the first step is moles of HNO3 will be equal. Given mass of HNO3 in grams divided by molar mass of HNO3, that is 63. The value comes out to be 2 by Na. So these are the moles. Now, molecules, which means particles. Molecules of HNO3 will be equal to moles multiplied by what? Multiplied by Avogadro's number. And Na cancels out. The value comes out to be 2. Done? Done, people? This is again your JEE mains PYQ. Look at this question carefully. The question is saying how many moles of electron weighs 1 kg? How many moles of electron weighs 1 kg? So technically, my dear students, if you understand the language of the question, we are given with 1 kg electron. 1 kg electron means 1000 grams of electron. We are given with 1000 grams of electron. So we are given with mass of electron. We are supposed to calculate moles. Number of moles of electron will be equal to mass of electron in grams divided by molar mass of electron. Now, mass of electron is given to me as 1000 divided by molar mass of electron. I do not know. Molar mass of electron I do not know. But right now, few minutes back, I gave you the formula. Molar mass of electron can be written as mass of one electron, which is 9.1 into 10 raised power minus 28 grams, multiplied by Avogadro's number. When you solve this, the value comes out to be 54.6 into 10 raised power minus 5 grams. This is the molar mass of electron. Few minutes back, I told you, molar mass of substance is equal to mass of one particle multiplied by Avogadro's number. So molar mass of electron will be equal to mass of one electron in grams multiplied by Avogadro's number. So I got the molar mass of electron. So given mass divided by its molar mass. Molar mass is 54.6 into 10 raised power minus 5. You just have to solve this, get the moles of electron. Am I clear, people? Sir, it is not 28, it is 31. This is grams here. It is 9.1 into 10 raised power minus 28 grams. Minus 31 will be kg. I don't need the mass in kg, I need the mass in grams. Am I clear till here, people? Everyone in the chats once? Everyone in the chats, people. Sir, please tell PYQ years. This was asked in JEE examination. I don't know which year, but it's a... Why do you need in which year it was asked? Perfect, people. Why multiplied with Na? I gave you the formula a few minutes back. Molar mass of the substance is equal to mass of one particle multiplied by Avogadro's number. And this mass of one particle has to be in grams. Moving on, people. There is one very important topic in this chapter, that is stoichiometry, right? And I'll give you one simple trick to solve the questions based on stoichiometry. I'll give you one simple trick to solve the questions which are based on stoichiometry. Okay? What is that trick? Have a look. For example, you have got a reaction like this. 2 times A, let's say it's in gaseous state, plus 3 times B, let's say it's in gaseous state, or leave it as such. 2 times A, which is in gaseous state, it gives 3 times B, which is in gaseous state, plus 5 times C, which is again in gaseous state. Imagine it's a balanced chemical equation. Imagine that it's a balanced chemical equation, right? Now, my dear students, if this is a balanced chemical equation, then what you can do here is, you can write one simple equation, which will solve all your questions based on stoichiometry. What is that equation? You can write number of moles of A divided by stoichiometric coefficient of A is equal to number of moles of B divided by stoichiometric coefficient of B is equal to number of moles of C divided by stoichiometric coefficient of C. This equation will solve all the questions based on this particular chemical reaction. Similarly, my dear students, you can write the same equation in terms of volume as well. You can write volume of A divided by stoichiometric coefficient is equal to volume of B divided by its stoichiometric coefficient is equal to volume of C divided by its stoichiometric coefficient. You just have to write the equation like this and you will be done. You will be done. You will be done. You will be done. You'll be done. How exactly? Let's have a look. Let's have a look. For example, this is one common question, guys. This is one common question. Read the question once. Read the question once. Read the comments once. See, guys. See, how do we deal with the questions of stoichiometry? Try to understand. I'll show you a simple method of solving the question. Calculate the mass of O2 gas produced on heating 12.25 grams of KClO3. So basically, as per the question, we have got KClO3. And we are going to heat up this KClO3. Let me tell you, when KClO3 is heated, we get KCl, and with KCl, you get O2. So the first point is always to write the reaction. First point always is going to be writing the reaction. Now, after writing the reaction, you are supposed to balance the reaction. You are supposed to balance the reaction. After balancing the reaction, you are supposed to convert the given quantity into moles. You are supposed to convert the given quantity into moles. So I'm given with mass of KClO3. Convert it into moles. So moles of KClO3 will be given mass of KClO3 in grams divided by molar mass of KClO3. When you calculate molar mass of KClO3, that's 122.5. The value comes out to be 0.1. The value comes out to be 0.1. First, write the reaction. Second, balance the reaction. Third, convert the given quantity into moles. Done? Now, do just one thing. Calculate the mass of O2 produced on heating 12.25 grams of KClO3. Write the equation that I told you a few minutes back. Write it like this. Number of moles of KClO3 divided by stoichiometric coefficient 2 is equal to number of moles of O2 divided by stoichiometric coefficient 3. Correct? Take this free here. I'll write number of moles of O2 will be equal to 3 divided by 2 times number of moles of KClO3. As simple as that. So it's going to be 3 by 2. Number of moles of KClO3 is equal to 0.1. The value comes out to be 0.15. So these are the moles of O2 which are being produced here. These are the moles of O2 which are being produced here. But I do not need the moles of O2. I need the mass of O2. So mass of O2 will be equal to moles of O2 produced multiplied by molar mass of O2. The value comes out to be 4.8 grams. So this is the mass of O2 which is produced, which I was supposed to calculate. Isn't this method very, very simple method, people? Isn't it simple, people? Quick. Everyone in the chats once. Yeah? Let me show you a few more questions. For example, this is the question. We are given with a reaction. The reaction is 3 times NO2 plus H2O. It gives what? It gives 2 times HNO3 plus what? Plus NO. Plus NO. The question is, how many grams of NO2? How many grams of NO2 are required to produce 25.2 grams of HNO3? What is my first step? First step is to convert the given quantity into moles. To convert mass into moles, I'll say moles of HNO3 will be equal to mass of HNO3 divided by molar mass of HNO3. Right? These are the moles of HNO3 which we have. So how much this value comes out to be? Can you give it a check? Can you check it out? Can you check it out? How much it's coming? Let me use the calculator quickly. So this is 25.2 divided by 63. This value is equal to 0.4. So I converted the given quantity to moles. Now, use the stoichiometric equation. I'll say number of moles of NO2 divided by stoichiometric coefficient 3 is equal to number of moles of HNO3 divided by stoichiometric coefficient, that is 2. Perfect. What do I need to calculate? I need this particular term. I can say number of moles of NO2 will be equal, take this 3 here, it is 3 by 2 times number of moles of HNO3, that is 0.4, the value comes out to be 0.6. So these are the moles of NO2. But am I supposed to calculate moles of NO2? No, I need the mass of NO2. So mass of NO2 will be equal to moles of NO2 multiplied by molar mass of NO2. Molar mass of NO2 will be 46. The value comes out to be 27.6 grams. So this is the mass of NO2 which I was supposed to calculate. Simple. Right? Perfect. Let me show you one more question. I believe it's clear now. You should be in a position to solve questions like this easily. Look at it, guys. You are given with a reaction. First thing, leave the question aside, convert the given quantity into moles. So number of moles of MnO2 will be equal to given mass of MnO2 divided by molar mass of MnO2. That's given to me in the question. The value comes out to be 0.8. Right? Now, how much HCl is needed for the complete reaction with 69.6 grams of MnO2? So use the stoichiometric equation. You'll write number of moles of HCl divided by what? Divided by 4 is equal to number of moles of MnO2 divided by what? Divided by 1. I need the moles of HCl here. Moles of HCl will be equal to 4 times the moles of MnO2. Moles of MnO2 are 0.8. The value comes out to be 3.2. So I got the moles of HCl. Now, what will be the mass of HCl? Mass of HCl will be moles of HCl multiplied by molar mass of HCl. When you solve this, the value comes out to be 116.8 grams. So this is the mass of HCl which I was supposed to calculate. Pretty simple. Is it clear? Is it clear? Everyone in the chats? Is it clear? Everyone in the chats, people? Everyone in the chats. Just you have to make this equation and you are done. You are sorted. Yeah? Now, my dear students, there's a topic called as limiting reagent. There's a topic called as limiting reagent. What is limiting reagent exactly? Limiting reagent is that reactant which gets completely consumed in the reaction. Limiting reagent is that reactant which gets completely consumed in the reaction. Understand? I'll give you the tricks to solve the questions. For example, you have got the reaction like this. 2A plus 3 times B. It gives, for example, 5 times C. This is the reaction, let's say. This is the reaction, let's say. For example, at time t is equal to 0, at time t is equal to 0, initially, we have got 10 moles of A and we have got 10 moles of B. Right? So this would be 0. Why is that? Because the reaction has not started yet. The reaction has not started yet. Now understand. When the reaction starts, I would say moles of A and B will start to decrease. When the reaction starts, moles of A and B will start to decrease, right? Can I say there will be one reactant which would have got completely consumed in the reaction? There would be one reactant which would have got completely consumed in the reaction. That reactant is called as the limiting reagent. The point is, how do we identify which one among the two is the limiting reagent? How do I identify whether A is the limiting reagent or B? There's a trick for that. What? See, divide this 10 with the stoichiometry coefficient 2. Divide this 10 with the stoichiometry coefficient 3. This value comes out to be 5. This value comes out to be 3.33. Okay. Which one is getting the lesser value? This is the lesser value. So, this is my limiting reagent. Simple way of checking which substance is the limiting reagent. If one is limiting reagent, other one we call as the excess reagent. If one is the limiting reagent, other one we call as the excess reagent. Now, if B is the limiting reagent, it would have got completely consumed in the reaction, right? It would have got completely consumed in the reaction. Now, the point is, how many moles of C would have got formed? How many moles of C would have got formed? How do you check that? How do you check that? Just do one thing. What exactly? C. For example, I have to calculate how many moles of C have got formed. What is the stoichiometric coefficient of C? That is 5. Divided by. What is the stoichiometric coefficient of limiting reagent? That is 3. Multiplied by. How many moles of limiting reagent we are given with? 10. So, this comes out to be 50 by 3. These are the moles of C which have got formed at the end of the reaction, when the reaction would have stopped. Do you understand? I'm just giving you the tricks to solve the question. So, for example, I have to calculate moles of C formed. Stoichiometric coefficient of C divided by stoichiometric coefficient of limiting reagent multiplied by moles of limiting reagent. Simple. Okay. Similarly, guys, what is this A? A is the excess reagent. A is what I call as the excessive reagent. Now, first of all, out of 10 moles of excessive reagent, there would be some moles of it which would have reacted. The point is, how many moles of A have reacted in the reaction? Number of moles of A reacted in the reaction. Reacted will be equal. Stoichiometric coefficient of A divided by stoichiometric coefficient of limiting reagent multiplied by moles of limiting reagent. So this is 20 by 3. 20 by 3 is 6.66. These are the moles of A which have reacted. These are the moles of A which have reacted. How many moles of A I took? I took 10 moles. How many have reacted? 6.66. So how many will be left? 10 minus 6.66. The value comes out to be 3.33. These are the moles of excessive reagent left in the container. Did you understand this concept? Did you understand this, people? Did you understand? Quick. Is it clear? Is it clear? Is it clear? Everyone, guys, quickly. Yeah? Done? Perfect. Great. Let's see what kind of questions can be framed here. Let's see what kind of questions can be framed. A simple question. A reaction is given. A reaction is given. And we are starting with 3 moles of NaOH and 4 moles of H2SO4. This would be 0. This would be 0. Perfect. What do I have to check? I have to check which one is the limiting reagent, right? How do we check which one is the limiting reagent? Divide the given moles by the respective stoichiometry coefficients. So 3 divided by 2. Similarly, 4 divided by 1. This value is equal to 1.5. This value is equal to 4. Which one is getting the lesser value? This is the lesser value. So this is my limiting reagent. Simple. Right? Clear, people? Now, for example, this is the question. We are given with a reaction. 6 times LiH plus 8 times BF3. It gives me what? 6 times LiBF4 plus what? Plus B2H6. This is your reaction. Now the question is saying, on starting with 2 moles each of reactants. On starting with 2 moles each of reactants. So we are starting with 2 moles each of reactants. This will be 0 in the beginning, this will be 0 in the beginning. Because the reaction has not started yet. The reaction has not started yet. Now which one is the limiting reagent among the two? 2 divided by 6. 2 divided by 8. 2 by 6, 2 by 8. Which one is lesser? This value will be lesser. BF3 is my limiting reagent. So it would have got completely consumed. The question is saying, how many moles of B2H6 are formed? How do we check the moles of product formed? Stoichiometric coefficient of product, that's 1. Divided by stoichiometric coefficient of limiting reagent, that's 8. Multiplied by moles of limiting reagent, that's 2. The value is 1 by 4, which comes out to be 0.25. So these are the moles of B2H6 formed. Simple. Correct? For example, this is the question. This again your J mains PYQ. This one. This one is again your J mains PYQ. The question is, we are starting with 0.1 mole of BaCl2 and 0.3 moles of Na3PO4. In the beginning, this will be 0, this will be 0 because the reaction has not started yet. Now tell me which one is the limiting reagent. 0.1 by 3. 0.1 divided by 3, which will be 0.033. 0.3 divided by 2, which will be 0.15. Which one is lesser value? This is lesser value, so this is my limiting reagent. Since I found which one is my limiting reagent, so it would have got completely consumed. It would have got completely consumed. What I need to calculate? I need to calculate the moles of barium phosphate formed. I need to calculate moles of barium phosphate formed. So how to calculate this? Stoichiometric coefficient of barium phosphate divided by stoichiometric coefficient of limiting reagent multiplied by moles of limiting reagent, that's 0.1. So it is 0.1 by 3. The value will be 0.0. So these are the moles of barium phosphate which have got formed at the end of the reaction. Is it clear, guys? Everyone say it once in the chats. Is it clear? I want to know this. I want to know this. Quickly, people, I want to know this. Is it clear to everyone? Is it clear, people? Simple. Stoichiometric coefficient of product divided by stoichiometric coefficient of limiting reagent multiplied by moles of limiting reagent. Okay, let me write it for you. Whenever you have to calculate number of moles of product formed, it's going to be stoichiometric coefficient of product divided by stoichiometric coefficient of limiting reagent multiplied by moles of limiting reagent. This is how you calculate the number of moles of product formed. Okay. Similarly, number of moles of excessive reagent reacted. Number of moles of excessive reagent reacted is equal to stoichiometric coefficient of excessive reagent divided by stoichiometric coefficient of limiting reagent multiplied by number of moles of limiting reagent. That's all. These are the two things which you have to remember, and you are done. You're sorted. Okay. Now, my dear students, there is one more topic from which questions are frequently asked. What is that? That's your empirical and molecular formula. That's your empirical and molecular formula. First of all, people, what is the difference between empirical and molecular formula? Questions have been frequently asked from this as well. So try to understand what exactly I'm going to say. For example, if I talk about glucose, one of the formulas of glucose is C6H12O6. The formula for glucose, which you must be knowing, that is C6H12O6. Now tell me one thing. In glucose, how many elements do you see? 3. Carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen, right? What is the ratio of the atoms here? It is 6:12:6. This is the ratio of atoms. This is the ratio of atoms. Perfect. Tell me one thing. Can you further simplify this ratio? Absolutely, I can further simplify this ratio. I can make it to 1:2:1. So how many ratios do you see here? There are 2 ratios. This is something I call as simplest whole number ratio. This is what I call as simplest whole number ratio. And this is what I call as actual ratio. This is what I call as actual ratio, right? As per the actual ratio, what is the formula? C6H12O6. As per the simplest ratio, what should be the formula? C1H2O1. As per the actual ratio, this should be the formula. As per the simplest ratio, this should be the formula. My dear students, that formula which gives me the simplest ratio, you call it as the empirical formula. And that formula which gives me the actual ratio, you call that as the molecular formula. That formula which gives me the simplest ratio is the empirical formula. That formula which gives me the actual ratio, you call that as the molecular formula. 2 simple things. Okay, 2 simple things. Now, with the help of molecular formula, we can calculate molecular mass. With the help of empirical formula, you can calculate empirical mass. How exactly? Have a look. Molecular mass will be equal. Carbon, atomic mass 12 into 6 carbon atoms. Hydrogen, atomic mass 1 into 12 hydrogen atoms. Oxygen, atomic mass 16 into 6 oxygen atoms. The value comes out to be 180 U. So what is this 180 U? 180 U is the molecular mass of glucose. It is the molecular mass of glucose. Similarly, with the help of empirical formula, I can calculate empirical mass. How exactly? It's going to be 12 into 1. 12 into 1 plus it's going to be 1 into 2. 1 into 2 plus it's going to be 16 into 1. 16 into 1. The value comes out to be 30U. What is this 30U? This is what I call as empirical mass. With the help of molecular formula, we calculate molecular mass. With the help of empirical formula, we can calculate empirical mass. And once we calculate molecular mass and empirical mass, there is a number. There is a number that is X. There is a number which I'm going to define. What is this X? X is what we call as molecular mass divided by empirical. X is what we call as molecular mass divided by empirical. And once we get the value of X, remember, molecular formula is always equal to empirical formula multiplied by X. At the same time, one more thing which will be used in the questions. Remember, my dear students, molar mass is equal to 2 times the vapor density. Sometimes in the question, they'll give the vapor density. And from the vapor density, you can calculate molecular mass as well. Let me show you the questions directly so that you can understand where do we have to use it. Let me quickly recap it. First of all, I took glucose, right? The ratio of atoms was 6:12:6. When I simplified it, it was 1:2:1. Okay, it was 1:2:1. From this formula, what do we got? Actual ratio. From this formula, we got the simplest ratio. This formula is called as empirical formula. This is called as molecular formula. With the help of molecular formula, we can calculate molecular mass. With the help of empirical formula, we can calculate empirical mass. Ratio of these two, I'll be calling as X. And at the same time, molecular formula is called empirical formula multiplied by X. Simple. And people, at the same time, molecular mass is equal to 2 times. Okay. All right. Now see what kind of questions can be handled from all of this. For example, this is your first question. This is your first question. Understand? As far as the question is concerned, calculate the empirical formula of the compound that contains. You have got a compound which contains certain elements. You have got a compound that contains certain elements. What are elements? Potassium, chromium, oxygen. You have got a compound that contains these three elements: potassium, chromium, oxygen. My dear students, the first thing which you will be remembering from now onwards, in the question, either you will be given with the mass percentage of these elements, or you will be given with directly the masses of these elements, or you'll be given with the mass ratio of these elements. Out of these three things, anything can be given to you in the question. Out of these three things, anything can be given to you in the question. Either you'll be given the mass percentage of the elements, or you'll be given the masses of these elements, or you'll be given the mass ratios of these elements. Now, in this question, what am I given with? I'm given with the mass percentage of these elements. What is the mass percentage of potassium that's given to me? 26.6%. What is the mass percentage of chromium that's given to me? That is 35.4%. What is the mass percentage of oxygen that's given to me? That's 38.1%. Okay. Now, remember, the first step always is to calculate the atomic ratio. The first step always is to calculate what? The first step always is to calculate the atomic ratio. How do we calculate atomic ratio? Whatever things are given to you, you just have to divide them with the respective. What is the atomic mass of potassium? 39. Chromium, 52. Oxygen, 16. So divide the given quantities by the respective atomic masses. So it's going to be 26.6 divided by 39. Similarly, 35.4 divided by 52. Similarly, 38.1 divided by 16. And when you solve these values, this particular value will come out to be 0.68. This particular value will come out to be 0.68. And this particular value will come out to be, I think it will be approximately how much? 2.68. Okay. This is always my first step. Now, after calculating the atomic ratio, what is the second step? Least atomic ratio. How do we calculate the least atomic ratio? Tell me which one is the smallest term among these. Smallest term is 0.68. Divide all these terms by 0.68. So 0.68 divided by 0.68 is 1. 0.68 divided by 0.68 is 1. 2.68 divided by 0.68, that is 3.5. Okay, that is 3.5. So the ratio is coming out to be 1:1:3.5. 1:1:3.5. I need the whole number ratio. This is not the whole number ratio. 3.5 here. So what am I supposed to do? Sorry, it's not 2.68, it's 2.38. Okay? Perfect. So what am I supposed to do? Convert them into whole numbers. So multiply throughout with 2. When you multiply throughout with 2, this becomes 2, this becomes 2, this becomes 7. So the ratio is coming out to be 2:2:7. So the formula will be, empirical formula will be K2Cr2O7. Empirical formula will be K2Cr2O7. This is something I was supposed to calculate. Did you understand? Did you understand, people? Let me show you one more question. With that, things will be more clear. Look at this question. Look at this question, guys. Look at this question. The question is saying you have got a compound containing nitrogen and oxygen. The mass ratio is given to as 7:16. Mass ratio is given to me in the question as 7:16. What is my first step? Atomic ratio. Atomic mass 14, 16. Atomic ratio 7 divided by 14, 0.5. 16 divided by 16, 1. Least atomic ratio. Which one is the smaller term? 0.5. 0.5 divided by 0.5 is 1. 1 divided by 0.5. 1 divided by 0.5 is 2. Therefore, empirical formula would be equal to N1O2. Empirical formula would be equal to N1O2. What am I supposed to calculate? Empirical formula or molecular formula? I need to calculate the molecular formula. Since I told you already, molecular formula is nothing but it is empirical formula multiplied by X. Empirical formula I calculated. What do I need now? I need X. What is X? X is molecular mass divided by empirical. X is molecular mass divided by empirical. So molecular mass will be equal to 2 times into vapor density. 2 times into vapor density. 2 times 46, that is 92, divided by empirical mass. You will be calculating from this formula. So 14 into 1 plus 16 into 2, that will be 46. Value comes out to be 2. If you got the value of X, you can calculate molecular formula, which will be equal to empirical formula N1O2 multiplied by X. X value is 2. The value will be N2O4. This is the molecular formula of the compound. Let me know once in the chats if this is very, very, very clear to all of you. Yes? Is it clear, people? Is it clear? Everyone in the chats? So with this, our first chapter is done. Let me know once in the chats if you understood all these things. Let me know, people. Let me know. Let me know quickly in the chats. Let me know quickly in the chats. Is it like super clear? Everyone? Yeah? As I told you, after every chapter, I'll give you 20 minutes of break. So, break till 1. Do your lunch quickly. Do your lunch quickly, and we'll start the next chapter exactly at 1. Exactly at 1. But I would want every one of you to be on time. I would want every one of you to be on time. This is enough, guys. Don't worry. This is sufficient, super sufficient. I would want every one of you to be on time. Exactly. The concentration terms. Concentration terms will be done in 12th physical chemistry, solution chapter, not here. I would want every one of you to be back exactly at 1. So have your lunch quickly. This is your lunch break. Is everyone back? Is everyone back? Let me know once in the chats. Is everyone back? All right, so people tell me, is the first chapter clear to everyone? Is the first one clear to everyone? Just let me know once the chat's quick, everyone. Is the first chapter clear? Notes I told you I'll be sharing on the Telegram at the end of the session. Notes I'll be sharing on the Telegram. All right, people. All right. Got it. Chalo, let's start the next chapter, and your next chapter is going to be your atomic structure. The next chapter is going to be your atomic structure, and before starting the atomic structure chapter, before starting this particular chapter, let me first of all tell you what all topics are there from which questions are asked in the NEET examination from the atomic structure. Okay. The first topic is going to be you will get the questions on the Bohr's model. Number one. Number two, you'll get the question based on your hydrogen spectrum. Hydrogen spectrum. You will get the question based on Heisenberg's uncertainty principle. Then you are going to get the questions from the calculation of nodes. You'll be getting the question from psi versus R and psi square versus R. You will get the question from electronic configuration. These are the topics, my dear students, from which they'll ask you the questions when it comes to the chapter atomic structure. Okay? Atomic structure. So let's get going. Let's get started. Yes, quantum numbers will come here only in this electronic configuration. Don't worry. So let's have a look on all these topics one by one, and let's see what kind of questions can be framed from this and what kind of questions can be asked from. Okay? All right? Sir, will you not explain the full chapter? This is actually your full chapter. Actually your full chapter. Don't worry. All right? Chalo, let's get going, guys. Let's get going. The first topic with which I shall be starting, what is that? That is basically the formulae related to Bohr's model. The formulae related to Bohr's model. My dear students, the first thing which we have here, what is that? That is how to calculate the radius of nth Bohr's orbit. How do we calculate the radius of nth Bohr's orbit, which I represent with Rn? How to calculate the radius of nth Bohr's orbit, which I represent with Rn. So what is meant by that? For example, you have got an atom, and this is the nucleus of that atom. Let's say this is the shell in which electron is revolving. This is the shell in which electron is revolving. Let the shell number of this particular shell is equal to n. And let the atomic number of the atom over here is equal to z. Let the atomic number be z, and let the shell number in which electron is revolving is equal to n. Now they'll ask you, calculate the radius of the nth Bohr's orbit. They'll ask you to calculate the radius of nth Bohr's. How do we calculate the radius of the electron moving in the nth Bohr's orbit? How do we calculate the radius of nth Bohr's orbit? There is a simple formula for that. Radius of nth Bohr's orbit is equal to R naught n square divided by z. What is this R naught? R naught is a constant whose value is 0.529 angstrom. This is the first formula, my dear students, which I would want every one of you to remember. Okay? Every one of you to remember. Number one. I'll show you its application in some time. Number one. Number two, imagine that here you have got one more atom. Imagine that here we have got one more atom. And this is the electron which is revolving in this particular shell. For example, atomic number of this particular atom is Z1 and the electron is moving in N1 shell here. Let's say the atomic number here is Z2 and the electron is moving in the shell number N2 here. Okay? Now, how do we compare the radii of these two Bohr's orbits? How do we compare the radii of these two Bohr's orbits? You'll be just writing one thing. You'll be writing R1 divided by R2 is equal. It will be N1 square divided by N2 square multiplied by Z2 divided by Z1. This is the formula, my dear students, with the help of which you are going to compare the radii of two Bohr's orbits. This is the formula with the help of which you can calculate the radii of two Bohr's orbits. Okay, radii of two Bohr's orbits. Well, it has got the derivation as well. And this is derivation. It's of no use to us. Okay, it's of no use to us. We just have to remember the formula that I gave you. We just have to remember the formula that I gave you. Perfect. We just have to remember the formula that I gave you. Similarly, guys, there is one more thing which will be asked. What is that? That is velocity of the electron in the nth Bohr's orbit. Velocity of the electron in the nth Bohr's orbit, which I represent with Vn. Velocity of the electron in the nth Bohr's orbit. Now the point is, how do we calculate the velocity of electron in the nth Bohr's orbit? Again, there's a formula for that. Velocity of the electron in the nth Bohr's orbit is equal to V naught Z divided by N. V naught Z divided by N. And similarly, my dear students, if you have to compare the velocities of two electrons moving in two different orbits, you'll be writing the formula V1 divided by V2 is equal to Z1 divided by Z2 multiplied by N2 divided by N1. N2 divided by N1. So these are the two results which I would want every one of you to remember. And my dear students, this V0 is a constant here. Its value is 2.18 into 10 raised power 8 meter per second. Okay? Perfect. Formula to calculate velocity of the electron in the nth Bohr's orbit. This is the formula by means of which we can compare the velocities of electrons moving in two different Bohr's orbits. Point number 2. Point number 3, my dear students. Point number 3. What is my point number 3? Point number 3 is, how do we calculate the time period? How do we calculate the time period of an electron? How do we calculate the time period of the electron? Again, there is one direct result which I would want you guys to remember. Time period of the electron moving in the nth Bohr's orbit is equal to T naught n cube divided by z square. T naught n cube divided by z square. Again, it has got derivation and stuff as well, but we do not need this derivation. We just have to remember the result. Okay? And this T naught value, T naught is equal to 1.5 into 10 raised power minus 16. 1.5 into 10 raised power minus 16. 1.5 into 10 raised power minus 16. This is the value of T naught. Similarly, guys, if you need to compare the time periods of two electrons, you'll be writing T1 divided by T2 is equal to N1 cube divided by N2 cube multiplied by Z2 square divided by Z1 square, right? This is the formula with the help of which you can compare the time periods of two different electrons moving in two different Bohr's orbits. Okay? All right? Similarly, guys, there is one more thing which can be asked. What is that? That is total energy. Total energy. Total energy of the nth Bohr's orbit. I mean, total energy possessed by the electron in the nth Bohr's orbit. Let me tell you, total energy of the electron in the nth Bohr's orbit is equal to minus 13.6 Z square divided by electron volt. This is the formula with the help of which you can calculate total energy possessed by the electron moving in the nth Bohr's orbit. Similarly, my dear students, sometimes they'll ask you about the kinetic energy. Kinetic energy possessed by the electron in the nth Bohr's orbit. That is nothing but 13.6 Z square divided by n square electron volt. And sometimes they'll ask you about the potential energy possessed by the electron in the nth Bohr's orbit. That will be equal to minus 27.2 Z square divided by n square volts. These are some of the results which I would want every one of you to remember from now onwards. The first result is the result of what? The first one, just give me a second, guys. Just give me a second. Hello? Hello? Hello, this class. Just give me a second. Just give me a second. Okay, so what I was telling you is, you have to remember the formula based on radius, formula based on velocity, formula based on time period, formula based on total energy, potential energy, and kinetic energy. Questions will be directly framed from these formulas. Okay, so let's have a look. What kind of questions can be framed here? For example, this is the first question which is on the screen. Can you check it out? Can you check it out, people? Can you check it out? Can you give it a try? Quick. Quickly. Sir, V naught में 6 आएगा. What did I write? Did I write something else? Just a second, guys. Just a second. What did I write here? I think there's a... Okay, this is 10 raised per 6. Sorry, my bad. 10 raised per 6. Okay, just modify this. This 10 raised per 6. Quickly, guys. What do you think about this one? If you look at the question carefully, how you are going to solve this, calculate the radius ratio of second orbit of He positive. So first of all, I'm given He positive, and the second one that's given as Be tri positive, right? These are the two ions, two single electron species that are given to me. Now, first of all, atomic number of helium, hydrogen, helium, that's 2. Atomic number of beryllium, hydrogen, helium, lithium, beryllium, that's 4, right? Second orbit of He positive, N1 value is 2, second orbit. And here they have mentioned third orbit, N2 value is 3, okay? Let the radius here be R1, let the radius here be R2. What do we have to calculate? We have to calculate the radius ratio. So basically, we have to calculate R1 by R2, R1 divided by R2. As I told you, R is equal to R naught n square by Z, right? So it's n1 square divided by n2 square multiplied by Z2 divided by Z1. Correct, people? So what is n1 ka square? 2 ka square is 4 divided by n2 ka square. 3 ka square is 9 multiplied by Z2. Z2 value is 4 and Z1, that is 2. So it comes out to be 16 divided by 18. So it is going to be simply 8 to 9. Everyone got this? This is the radius ratio which I was supposed to calculate. Yeah? Perfect. Can you give this question a try too? Can you check it out? Can you check this question out? Quickly. Quickly, people. Quickly. Absolutely. So basically, I'm given with hydrogen atom, and at the same time, we are given with Li dye positive as well. So tell me the atomic numbers of hydrogen and lithium. Hydrogen's atomic number is 1. Lithium's atomic number is hydrogen, helium, lithium, that is 3. If the velocity of electron in the first orbit, so n1 is equal to 1. If the velocity of electron in the first orbit is equal to v, what will be the velocity of the electron in the third orbit? In the third orbit. So v2 value we have to calculate. Few minutes back, I gave you the result. You have to use that particular result. What is that? That is v1 divided by v2 is equal to, you know, v is equal to v naught z by n, right? Z by n. So it is z1 divided by z2 multiplied by n2 divided by n1. v1 is nothing but v. v2 we have to calculate. z1 value is equal to 1. z2 value is equal to 3. n2 value is equal to 3. And n1 value is equal to 1. So 3 gets cancelled. This value comes out to be 1. So you can say v2 is equal to v. Is it clear? These sort of questions are frequently asked in your examination, and they're simple questions. Similarly, my dear students, you can give this question a try as well. This is the question based on time periods, and this I'm keeping as your homework question. You can check it out afterwards. Okay? Again, you have to compare the ratio of the time period. Now, there is one more important topic, guys. What is that one more important topic? That is basically your hydrogen spectrum. That is your hydrogen spectrum, from which questions are asked frequently. Hydrogen spectrum. Hydrogen spectrum. Try to understand what exactly I'm going to do. Try to understand what exactly I'm going to do. First of all, if I talk about hydrogen atom, let me first of all draw some lines over here. After that, I'll make you understand what this hydrogen spectrum is all about and what kind of questions can be framed of it. Now is, look carefully what exactly I'm going to do. Since I'm talking about hydrogen atom, let's say this is n is equal to 1 for hydrogen, this is n is equal to 2 for hydrogen, n is equal to 3 for hydrogen, n is equal to 4, n is equal to 5, n is equal to 6, 7, 8, and this n is equal to infinity. N is equal to infinity. Okay? N is equal to 1. This is something I call as ground state of hydrogen. Okay, ground state of hydrogen. N is equal to 2 is called as first excited state of hydrogen. This would be second excited state of hydrogen, third excited state of hydrogen, and so on, and so on. Now you should know one thing. When the electron makes a transition from lower energy state to higher energy state, when the electron makes a transition from lower energy state to higher energy state, at higher energy state, electron is highly unstable. At higher energy state, electron is highly unstable. It jumps back. And when the electron makes a transition from higher energy state to lower energy state. When the electron makes a transition from higher to lower, it emits energy in the form of radiation. It emits energy in the form of radiation, right? It emits energy in the form of radiation. You know that already. When the electron makes a transition from higher to lower, it emits energy in the form of radiation. Now, my dear students, what you need to do over here is, you need to understand one thing. Remember, when the electron makes a transition from higher energy state to shell number 1. When the electron makes a transition from higher energy state to shell number 1, like this. When the electron makes a transition from higher energy state to shell number 1, like this. So, electron making a transition from higher energy state to shell number 1. We get a series of radiations. Which we call as the Lyman series. This line over here, from 2 to 1, this is something I call as the first line of Lyman. Or you can call it as H-alpha line of Lyman. Similarly, this particular line, you can call it as the second line of Lyman, or you can call it as H-beta line of Lyman. Similarly, this one, third line of Lyman or H-gamma line of Lyman. Perfect. Similarly, guys, when the electron makes a transition, from higher energy state to shell number 2. When the electron makes a transition from higher energy state to shell number 2. This is the higher energy state, this is shell number 2. Electron making a transition from higher to shell number 2. Similarly, from higher to shell number 2. Similarly, from higher to shell number 2. From higher to shell number 2. From higher energy state to shell number 2. From higher energy state to shell number 2. So, electron making a transition from higher energy state to shell number 2. The series of lines which we got here, the series of radiations which we got here, you call this series as the Balmer series. You call this particular series as the Balmer series. This is what I call as the first line of Balmer. Or you can call it as H-alpha line of Balmer. Similarly, second line of Balmer or H-beta line of Balmer. And similarly, it keeps on going when the electron makes a transition from higher energy state to shell number 3, like this. From higher energy state to shell number 3. Higher energy state to shell number 3. Higher energy state to shell number 3. The series of radiations which we get, is what I call as Lyman-Balmer. This was what I call as the Paschen series. And this is what I call as the first line of Paschen, or you can call it as H-alpha. This is called as H-beta, and so on. Right? Similarly, Lyman, Balmer, Paschen. Then comes your bracket series. Then comes your fund series. Perfect. Now, guys, what is important here? Important is just one thing. One thing. I got Lyman series. I got Balmer series. Lyman, Balmer. Then you have got Paschen. Then you have got bracket. Then you have got fund. Over here, I just want you to remember one thing. Lyman, U, V, I, and I. What is U? U is ultraviolet. V is visible. I is infrared. This I is also the infrared. Similarly, this I is also the infrared. So these are the questions which are frequently asked. They'll ask you the question. Lyman series falls in which region? It falls in ultraviolet. Balmer series falls in which region? Visible spectrum. Paschen series falls in which region? Infrared. This is also infra, this is also infra. Or here you can write far infrared. Here also you can mention far infrared. Okay? These are direct memory-based things which can be asked to you. Now, people, I told you one thing. When the electron makes a transition from higher energy state to lower energy state, it emits energy in the form of radiation. How do we calculate the wavelength of the radiation? Emitted when the electron makes a transition from higher to lower? That wavelength is calculated by the formula called as Rydberg's formula. That's called as the Rydberg's formula. Rydberg's formula is used to calculate the wavelength emitted or absorbed by the electron when it makes the transition. Now, guys, what is this formula all about? Formula is something like this. 1 divided by lambda, which is called as wave number, is equal to R Z square 1 upon N1 square minus 1 upon N2 square. This is the formula with the help of which I can calculate the wavelength emitted or absorbed when the electron makes a transition. Now, my dear students, what is N1? N1 here represents the lower energy state. N2 represents your higher energy state. And at the same time, this Z represents the atomic number. R is the Rydberg's constant. Remember, 1 by R value is equal to 911.5 angstrom. 1 by R value is equal to 911.5 angstrom. Now, let's try to analyze this formula and let's see what kind of questions can be framed from this. For example, if I talk about the Lyman series, guys, try to understand what exactly I'm going to say. In case of Lyman series, electron makes a transition from higher energy state to shell number 1. You know that already. Now, for example, the first thing they can ask you, calculate the series limit. In case of Lyman. Series limit means shortest wavelength. In case of Lyman. First of all, one thing I believe every one of you will be knowing, delta E is inversely proportional to lambda. Now, I have to calculate lambda minimum. I have to calculate the minimum wavelength. For lambda to be minimum, energy gap has to be maximum. Now tell me, in case of Lyman, when is the energy gap maximum? In case of Lyman, the energy gap is maximum when the electron makes a transition from infinity to 1. So, in order to calculate the lambda minimum, I have to make sure the transition I take is from infinity to 1. Because in case of Lyman, energy gap is maximum when the electron jumps from infinity to 1. And when the energy gap is maximum, the wavelength automatically becomes your minimum. Right? Now, guys, the lower energy state I represent with N1, higher energy state I represent with N2. Now, you can use the Rydberg's formula, that is 1 divided by lambda is equal to R. Z value for hydrogen is 1 upon N1 square minus 1 upon N2 square. Right? So, it's 1 divided by lambda is equal to R. 1 by infinity is 0. So, I can say, if I take the reciprocal, lambda is equal to 1 by R. 1 by R value already I know that's 911.5 angstrom. So, this is the series limit. This is the shortest wavelength in case of Lyman series. Now, they can ask you about the longest wavelength of Lyman as well. Calculate the longest wavelength of Lyman. Lambda maximum. Now, you tell me one thing. In case of Lyman, when can be lambda maximum? Lambda can be maximum if delta E is minimum. And when is delta E minimum in Lyman? When the electron makes a transition from 2 to 1. Correct? So, lower energy state, I represent with N1, higher energy state with N2. So, you can use the formula. 1 by lambda is equal to R, Z square, 1 upon N1 square minus 1 upon N2 square. Now, use the formula. So, I can say 1 by lambda is equal to R. This will be 2 square, 4 minus 1 is 3. So, this is 3 divided by 4. Or, I can say lambda is equal to 4 by 3 multiplied by 1 by R. And 1 by R value already you know how much is that? 911.5 angstrom. Right? So, this is the lambda maximum in case of Lyman. Similarly, you can calculate lambda minimum and lambda maximum for Balmer series, for Paschen series, etc. Right? Am I clear, people? Am I clear? Can you let me know quickly in the chats? Am I clear to everyone? Now, guys, one more thing. They can ask you. What is that? They can ask you to calculate the total number of spectral lines. Obtained when the electron makes a transition. And total spectral lines are calculated by the formula N2 minus N1 into N2 minus N1 plus 1 divided by 2. This is how you calculate the total number of spectral lines which are obtained when the electron makes a transition. Now one more thing. The number of spectral lines in a particular region, is equal to N2 minus ground state of that region. What is meant by that? Let me make you understand the meaning of these formulas. Understand, guys. For example, there is a question that the electron is making a transition from 10 to 1. And they are asking you, first of all, how many total spectral lines can be observed? Total spectral lines is equal to lower energy state is N1. Higher energy state is N2. So it's higher minus lower. N2 minus N1 multiplied by N2 minus N1 plus 1. Divided by what? Divided by 2. Right? So this can be written as, this got cancelled. 10 minus 1 is 9. 9 tens are 90. Right? 90 divided by 2 is 45. So total spectral lines obtained will be 45. Now, out of total 45 spectral lines, how many spectral lines will fall in Lyman series? How many will fall into bracket? How many will fall into Paschen, etc., etc.? So, out of 45, the number of spectral lines which will fall in Lyman will be equal. What exactly? It will be equal to N2. N2 value is 10 minus ground state of Lyman is 1. The value is 9. Right? Lyman. For example, they're asking me about Balmer series. N2 minus ground state of Balmer. What is the ground state of Balmer? That is 2. So 8. Lyman Balmer. How many will fall into Paschen series? N2 minus ground state of Paschen 3. So like that, you can calculate all this stuff. For example, look at this question. Guys. Just a second. Look at this question. The question is, electron in the hydrogen atom jumps from some higher energy level to the third energy level. If 6 spectral lines are observed, total spectral lines are 6. Okay? Find the initial position of electron. Since total spectral lines is equal to N2 minus N1 multiplied by N2 minus N1 plus 1 by 2. Total spectral lines observed are 6 is equal. N2 I have to calculate. N1 is 3. N2 I have to calculate. N1 is 3 plus 1 divided by 2. So 6 2s comes out be 12 is equal. This would be N2 minus 3. This would be N2 minus 2. Perfect. So can you tell me the value of N2 that satisfies this equation? Quick. What should be the value of N2 here? Everyone. What do you think? What should be the value of N2 here? N2 value should be 6. If N2 is 6, 6 minus 3 comes out to be 3. 6 minus 2 comes out to be 4. So 4 into 3 will come out to be 12. So N2 value has to be 6. What was N2? N2 was the higher energy state, which I was supposed to calculate. Understood? Simple question. For example, you have got one more question. The question is like this. Hydrogen atom in ground state, so N1 value is 1, is excited by the monochromatic radiation of wavelength lambda. Let's say the electron went to higher energy state N2. On coming back to ground state, 15 different spectral lines are observed. Total spectral lines are 15. Okay, 15 spectral lines are observed. Calculate lambda. This is the question. Now see how I'm going to solve this. It's again simple question. See guys, total spectral lines is equal to N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. Total spectral lines observed are 15 is equal to N2 value I will be calculating first. N1 is 1. N2 I will be calculating minus N1 is 1 plus 1 divided by 2. So this 1 and 1 cancelled. 15 2s are 30. So 30 is equal to N2 minus 1 multiplied by N2. Can you tell me the value of N2 here? N2 value should be 6. Then only 6 into 5 will come out to be 30. So N2 value has to be 6. It means that the transition is happening between 1 and 6. Now, we have to calculate lambda. You know the Rydberg's formula, 1 by lambda is equal to R, Z value is 1, 1 upon N1 square, 1 upon N1 square minus 1 upon N2 square. So this will be 1 by lambda is equal to R. This will be 36 minus 1, that is 35 divided by 36. You can take the reciprocal. You can say lambda is equal to 36 divided by 35 multiplied by 1 by R. So it's going to be 36 divided by 35. 1 by R value is 911.5. Okay. This is how you are going to calculate lambda. I believe this is also clear to everyone. Yeah. So these are, my dear students, the questions which can be framed from what? From hydrogen spectrum. This can be one more question asked. This can be one more question asked. Look at the question carefully. What transition in hydrogen spectrum? What transition in hydrogen spectrum would have the same wavelength as the Balmer transition of He positive? So in He positive, the electron goes from 4 to 2. In case of He positive, the electron is going from 4 to 2. Now think over it. When the electron will be going from 4 to 2, it will be emitting energy in the form of radiation. That radiation will be having some wavelength. That radiation will be having some wavelength. Now the question is saying, what should be the transition? What should be the transition in case of hydrogen such that the wavelength emitted is same lambda as was emitted here? Whatever wavelength is emitted here, what should be the transition in case of hydrogen atom so that the wavelength emitted is same, that is lambda, as was emitted here in this particular case? Now, if you think logically, I can say 1 by lambda is equal to R. Z value for hydrogen is 1. 1 upon N1 square minus 1 upon N2 square. This is your Rydberg's formula which I used here. Use the same Rydberg's formula here. It's going to be 1 by lambda is equal to R. Z square. Z for helium is 2. 2 ka square is 4. Right? 1 upon N1 square. N1 square. 2 ka square is 4. Minus 1 upon N2 square. 4 ka square is 16. So this is 1 divided by lambda is equal to R. This 4 gets cancelled. So it becomes 1 here. 4 4s are 16. So it becomes 4 here. Or you can write it like this. 1 by lambda is equal to R. You can write as 1 upon 1 square minus 1 upon 2 square. My dear students, just compare these two equations, this equation and this equation. When you compare these two equations, you have got 1 by lambda here, 1 by lambda here, R value here, R value here, 1 upon N1 square, 1 upon 1 square. When you compare, N1 value came out to be 1, right? Similarly, N2 value came out to be 2. N2 value came out to be 2. This is something I was supposed to check. So basically, in case of hydrogen, the transition should be from 2 to 1. In case of hydrogen, the transition should be from 2 to 1. Then only the wavelength emitted will be same as was emitted when the electron makes a transition from 4 to 2 in case of He positive. Is this clear? Is this clear, people? Can you tell me quickly in the chats if this particular stuff is clear? Everyone in the chats. If this is clear, then let's move on and talk about your Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. What this Heisenberg's uncertainty principle says? Heisenberg's uncertainty principle simply says one thing. You cannot determine the position and the momentum of the electron, of the microscopic particle like electron, simultaneously with 100% accuracy. You cannot determine the position and the momentum of a microscopic particle simultaneously with 100% accuracy. If you are going to determine the position, then there will be error in its momentum. If you are going to determine the momentum, there will be error in its position. So both the things, position and momentum, they cannot be measured, they cannot be calculated simultaneously with 100% accuracy. Okay? So you just have to remember one result here. The result is something like this. I'm writing a term here, delta x. Delta x represents your error or uncertainty in the position. Similarly, I'm writing delta v. It is going to be error or uncertainty in the velocity. Okay? Delta p. Delta p is nothing but m delta v. Okay? Delta p. Delta p is error or uncertainty in the momentum. Similarly, if I write delta lambda, that is going to be error or uncertainty in de Broglie's wavelength. Now, as per your Heisenberg's uncertainty principle is concerned, we have got an equation, delta x dot delta p is greater or equal to h upon 4 pi. This is one result, my dear students, which you have to remember directly. Error in the position multiplied by error in the momentum is always greater or equal to this number. This number is h upon 4 pi. H is your Planck's constant. Now, you can write it like this as well. Delta x dot. Delta p is what? M delta v. So delta v I'm writing as such, and that m goes into the denominator here. So you can write the result in this format as well. You can write the result in this format as well. Okay. Now, what kind of questions can be framed from it? What kind of questions can be framed from it? For example, this is the question. This is the question, for example. This is the question, for example. The question is, you have got a particle which has got the mass of how much? You have got the particle which has got the mass of 10 raised per minus 10 grams. Whenever from now onwards, there's a question asked from Heisenberg, use all the values as per SI system. Right? Use all the values as per SI system. So I'll be divided by 1000. It becomes 10 raised per minus 13 kg. Okay. Now, velocity of the particle is equal to 10 raised per minus 6 centimeter per second. Centimeter per second. Is centimeter per second SI unit? No. Meter per second is. So divide with 100, it becomes 10 raised per minus 8. 10 raised per minus 8 meter per second. What is the error in velocity? Error in velocity is equal to 0.001% of what? Of 10 raised per minus 8. Okay. So delta V will be equal to 0.001. Perfect. This is your delta V here. This is your delta V here. Now, my dear students, what you have to do exactly is, you just have to use the the equation that I gave you a few minutes back. That was delta x dot delta V is greater or equal to. I'll just use the equality sign just to solve the equation. H upon 4 pi. What we have to calculate? We have to calculate delta x. So delta x will be equal to h upon 4 pi m. Right? Sorry, not, yes, 4. This is delta x dot delta V is equal to h upon 4 pi m. Now, delta V will also come here. Now, h value you already know. 6.6 into 10 raised per minus 34. Right? Divided by 4. Pi value will be simply 22 by 7. M is 10 raised per minus 13. And delta V here, you have calculated as per SI system. So, it will be, this will be 10 raised per minus 4 divided by 10 raised per 2 multiplied by 10 raised per minus 8. Just the matter of calculation, and you can calculate error in the position, and you will calculate this as per SI system. Its answer will be in meters. Okay. This is one of the questions which can be asked. Just formula, put the values in the formula. Just take care of one thing, that whatever values you are putting here in this equation, put all the values as per SI system. That's all. That's all, people. Okay. There is one more question that can be asked here. Look here carefully. The question is, if the error in the velocity, okay, if the error in the velocity and the position is same, if the error in the position and the velocity is same, what will be the error in the de Broglie wavelength? What will be the error in the de Broglie wavelength? Now, first of all, your lambda. Lambda is equal to h upon mv. Lambda is equal to h upon mv. So I can say delta lambda, error in de Broglie wavelength, will be equal to h upon m delta v. Whatever is the error in de Broglie wavelength, that's due to the error in velocity. So delta lambda is equal to h upon m delta v. Now, this is something which is given to me in the question. Now, we already know one thing. Delta v dot delta x is equal to h upon 4 pi m. Correct? Now, delta v, delta x are same. Delta v, delta x are same. So, I can write delta v ka square is equal to h upon 4 pi m. So, I can say your delta v is equal to under root of h upon 4 pi m. Since you got delta v, put the value of delta v here. So, it's going to be delta lambda is equal to h upon m. What is delta v? Delta v I already calculated. That's h upon 4 pi m. Perfect. This is your delta lambda which you are supposed to calculate. This can be one more sort of question asked from here. Okay. Now, my dear students, there is one more thing that can be asked. What is that? What is that? That is questions based on principal quantum numbers. I mean, questions based on quantum numbers. Now, you know you have got 4 sets of quantum numbers, out of which the first three, principal, azimuthal, magnetic, right? The principal, azimuthal and magnetic, they are derived from Schrodinger's wave equation. This is one important point which you need to know. Okay. Now, principal quantum number we represent with n, this we represent with L, this we represent with M, this we represent with S. So, first of all, you need to know one thing. The value of L will be from 0 to n minus 1. The value of M is from minus L to plus L. S can have only two values, plus 1 by 2 and minus 1 by 2. S can have only two values, plus 1 by 2 and minus 1 by 2. From these principal quantum numbers, let me tell you first of all, this principal quantum number, it gives me the idea about the shell number in which electron is present. This gives me the information about the subshell of a particular shell in which electron is present. This gives me the information about the orbital in which the electron is present. This just tells me whether the electron goes with clockwise spin or the electron is going with anti-clockwise. Okay? There can be few types of questions framed from these quantum numbers. What is that? Have a look. Have a look. The question will be like this. You'll be given with some set of quantum numbers. Let's say here I'm writing the n value. This is L, this is M, and this is S. I'm writing some options here. Let's say this is 5, this is 4, this is minus 4, this is plus 1 by 2. Let's say this is 4, this is 4, this is minus 3, this is minus 1 by 2. Let's say this is 4, this is 3, this is, for example, minus 4, and this is plus 1 by 2. Let's say this is 4, this is 3, this is minus 3, this is 0. I have to check which of the sets of quantum numbers are possible and which of the sets of quantum numbers are not possible. I have to check that. If you look carefully, I told you a few minutes back, L value is from 0 to n minus 1. M value is from minus L to plus L. S can have only two values, plus 1 by 2 and minus 1 by 2. Okay, now check it out. Tell me, n value is 5, so the electron is present in fifth shell. L value is 4, so 0 to n minus 1. 0 to 5 minus 1, that means 0 to 4. So L can be 0, 1, 2, 3 or 4. So this is correct. M is from minus L to plus L. L is 4, so minus 4 to plus 4. Correct. S plus 1 by 2, correct. So this one is correct. The first one is correct. First set of quantum numbers is correct. Look at the second set of quantum numbers. N value is 4, fourth shell. L is from 0 to n minus 1. 0 to 4 minus 1. 0 to 4 minus 1. That means 0 to 3. So it can be 0, 1, 2 or 3. But it's 4. So this is incorrect. This is incorrect. Look at the next one. N value is 4. L value is 3. Correct. M value is minus 4. M is from minus L to plus L. So it has to be from minus 3 to plus 3. So minus 4 does not come here. Right? N4, L3. This is minus 3. Spin cannot be 0. So this is incorrect. 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 This is the only one. That's right? Okay. For example, the question will be asked like this as well. The correct set of quantum numbers. This is the asked question. The correct set of quantum numbers for the last electron of rubidium. Correct set of quantum number for the last electron of rubidium. First of all, rubidium comes in which group? Lithium, sodium, potassium, rubidium, Cc. Right? So this, for example, your lithium, this is sodium, this is potassium, this is rubidium, and this is cesium. Now, if you talk about lithium, its configuration is 2s1, outermost configuration. 3s1, 4s1, 5s1, 6s1, right? I have to talk about the correct set of quantum numbers for the last electron of rubidium. Now, we know, in case of rubidium, the last electron is in 5s. Perfect. 5s means the shell number n value is 5, right? Since it's S subshell, for S subshell, the value of L is 0. For S subshell, the value of L is 0. You should know it, right? M is from minus L to plus L. So M can be 0. And S will be either plus 1 by 2 or minus 1 by 2. Okay? Am I clear, guys? Am I clear to everyone? Am I clear to everyone? Perfectly done. Now, guys, understand one more thing. Here I'm writing n value is equal to 1. Here I'm writing, for example, n value is equal to 2. And here I'm writing n value is equal to 3. Understand? N value is equal to 1 represents your first shell, which I call as K shell. Right? This is second shell, L shell. This is, for example, your M shell. This is your M shell. Okay? Now, understand what exactly I'm going to do. If n is equal to 1, M value will be, or leave M aside. Talk about L first. L is from 0 to n minus 1. Now, n is 1 here. So 1 minus 1, 0. So L value is coming just out to be 0. L value is 0. Let me tell you, every value of L represents a subshell. every value of L represents a subshell. Remember, L value is equal to 0, L value is equal to 1, L value is equal to 2, L value is equal to 3. L is equal to 0 represents S subshell. L is equal to 1 represents P subshell. L is equal to 2 represents D subshell. And L is equal to 3 represents F subshell. So basically, I took the value of N as 1. That means I'm talking about the first shell, K shell. In this first shell, how many values of L you are getting? You are getting one value of L, that is 0. Every value of L represents subshell. That means in case of K shell, there will be one subshell. There will be one subshell. And that subshell is what I call as S subshell. That subshell is what I call as S subshell. So basically, in your first shell, there is only one subshell. That's S subshell, right? Now, tell me the value of M. M is from minus L to plus L, right? M is from minus L to plus L. L is 0. So M value is 0. So how many M values I got? I got one M value. I got one M value. That is 0. And every value of M represents an orbital. Every value of M represents an orbital. Every value of M represents an orbital. That means there'll be one orbital. There'll be one orbital here. And that one orbital is called as S orbital. So technically, if you ask me, in your first shell, there is one subshell. And in that one subshell, there is one orbital, which I call as S orbital. Understood? Similarly, guys, N is equal to 2. N is equal to 2 represents second shell. If N is equal to 2, L will be from 0 to 2 minus 1. L will be 0 and 1. L will be 0 and 1. And every value of L represents a subshell, right? And L is equal to 0 represents S subshell. L is equal to 1 represents P subshell. Represents P subshell. So I can say one thing. In your second shell, there are two subshells, S subshell, P subshell. Okay. Now, what will be the value of M for here? M is from minus L to plus L. So minus 0 to plus 0. That means 0. M for this is minus L to plus L. Minus 1 to plus minus 1, 0, plus 1. Every value of M represents an orbital. So in S subshell, you will find one orbital. In P subshell, you will find three orbitals. Okay. So I was talking about the second shell. In the second shell, there are two subshells, right? There are two subshells. Okay. S subshell and P subshell. In S subshell, there is one orbital. In P subshell, there are three orbitals, right? Similarly, you can check for the third shell as well. If N is equal to 3, L will be 0 to N minus 1, 0 to 3 minus 1. So it can be 0, it can be 1, it can be 2, right? And every value of L represents a subshell. So this L is equal to 0, S subshell. This represents your P subshell. This represents your D subshell. This represents your D subshell, right? Now, what will be the value of M here? If L is 0, M is 0. L is equal to 1. M is from minus L to plus L. So minus 1, 0, plus 1. L is equal to 2. So M will be minus 2, minus 1, 0, plus 1, plus 2. And every value of M represents an orbital. So in S subshell, there is one orbital. In P subshell here, there are 3 orbitals. And in D subshell here, there are 5 orbitals. Perfectly done? Is that clear, guys? Is that clear? All of you? Let me know once in the chats. Let me know once in the chats. My dear students, related to electronic configuration, you just have to remember the electronic configuration of chromium and copper because they show exceptional configuration. Related to the electronic configurations, you just have to remember the electronic configuration of chromium and copper. What is the electronic configuration of chromium? It is 3d5, 4s1. Electronic configuration of copper, it is 3d10, 4s1. Remember these two configurations. These are the exceptional ones. Remaining is same. These two you have to remember. And what is the reason for this exceptional configuration? You might have heard about exchange energy. That is the reason. That is one of the major reasons. Exchange energy is the reasons why your chromium shows 3d5, 4s1. Okay? Perfect? Because more the exchange energy, more is going to be the stability. Got it? Now there is one more thing. There is one more thing. What is that? They'll ask you to calculate the orbital angular momentum. Orbital angular momentum. There is a formula to calculate the orbital angular momentum, which is under root of L into L plus 2. H upon 2 pi. This is the formula with the help of which you can calculate orbital angular momentum. For example, I'm writing 2s sub 2s. Here I'm writing 2p. Here I'm writing 3p. Okay. I need to calculate their orbital angular momentum. Now tell me one thing. N value here is 2. Well, I've got nothing with N. I just have to take the L value. What is the L value for S? L value for S is 0. L value for S is 0. If L is 0, this entire term becomes 0. So in case of 2s, orbital angular momentum is 0. Right? Similarly, in case of 2p, in case of p, what is the L value? For p, L value is 1. So orbital angular momentum will be equal to under root of L. L is 1. So L into L plus 2 into h upon 2 pi. Right? Perfect? Perfect, guys? So it's going to be 2 plus 1, 3. So it's going to be a root of 3 into h upon 2 pi. Clear? Did I write the formula wrong? Is it root of L into L plus 2 or L plus 1? I'm just asking you in the chats. Is it under root of L into L plus 2 or under root of L into L plus 1 h upon 2 pi? Just asking you. It is under root of L into L plus 1 here, not 2. Right? So this will be 1. So this will be root of 2. Okay? Now 3p. Calculate the orbital angular momentum here. It's under root of L into L plus 1. L value is, for p, L value is 1. So 1 plus 1 is 2. So it is again going to be root of 2 into h upon 2 pi. Perfect. So you can get the question based on orbital angular momentum as well. You can get the question on orbital angular momentum as well. Now guys, there is one more question that can be asked here in this particular chapter. What is that? That is calculation of nodes. Calculation of nodes. Okay. There is a formula to calculate total number of nodes. Formula is n minus 1. There is a formula to calculate total number of nodes. And total number of nodes is going to be the formula n minus 1. And these nodes are actually of two types. These nodes are actually of two types. One is called as spherical or radial node. One is called as angular node. One is called as angular node. How do we calculate the angular nodes? The value of L gives you the number of angular nodes. How do we calculate the spherical nodes? N minus L minus 1. This formula gives you the spherical node. Now take any one and check it out. For example, I have 3s. I have 3s. How many total number of nodes will be there? Total number of nodes is equal to n minus 1. First of all, what is the n value here? N value here is 3. For s, the L value is 0. So n minus 1. So 3 minus 1 is 2. Okay, 3 minus 1 is 2. Now, how many spherical nodes are there? Spherical nodes is n minus L minus 1. N minus L minus 1 is equal to 2. Angular nodes is given by the value of L. L value is 0. Right? Similarly, for example, you have got 4p, for example. 4p. What is the n value here? N value is 4. L value for p, that is 1. L value for p, that's 1. Total number of nodes, n minus 1. 4 minus 1, that is 3. Spherical nodes, n minus L minus 1. So 4 minus 2 is 2. Angular nodes is equal to the value of L, that's 1. Perfect. So like this, you can check how many total nodes are there, how many spherical nodes are there, and how many angular nodes. Okay. Now, people, there is one more thing. There is one more thing. They can ask you particularly about 1s and 2s, because this is given in your syllabus. For 1s, what is psi versus r graph? And what is psi square versus r graph? Psi square versus r graph for 1s. Similarly, for 2s also, they can give you the same. They can ask you the same. What exactly? Psi versus r, and psi square versus r. These are the graphs which they can ask. These are the graphs which they can ask. Now, let me directly make these graphs. 1s will be like this. 1s will be like this. This 1s will be like this. For 2s, it's going to be like this. And this particular one will be like this. These are the 4 graphs, my dear students, which you have to remember over here. Yes? Okay. Sir, notes are not provided on Telegram. I keep on sharing the notes of all my sessions. What else do you need? Do you want me to upload the notes of biology as well? That you have to talk to your biology educator, your physics educator. I take responsibility of my notes, my chemistry notes. Okay, guys. So with this, our atomic structure is also done. And now, tell me the answer of this question. Tell me the answer of this question quickly. Quick. How many maximum electrons can be accommodated in 3D orbital, he is saying. He is not saying 3D subshell. See, you have to be careful with this. If I talk about D subshell, in D subshell, there are 5D orbitals. There are 5D orbitals. And every orbital can accommodate a maximum of 2 electrons. So in D subshell, total electrons will be 10. But they are asking about the D orbital. Select any of the orbital. Be 2. Answer will be 2. They're asking you how many maximum electrons can be accommodated in 3D orbital, not 3D subshell. If it was 3D subshell, then 10 electrons. This 3D orbital, it's going to be 2 electrons. You have to be careful with all this. Okay. This is your asked question also. The correct ground state configuration of chromium. 2 minutes back I told you. 3d5 4s1, right? 3d5 4s1. What about this one? A p orbital can accommodate up to what? Orbital he's saying. P orbital can accommodate 2 electrons with opposite spins. He's not asking about the p subshell. P orbital he's saying. Okay? Alright. Arrange the following on the basis of their increasing energies. If this sort of a question is asked, then there is a rule for that. You call that rule as N plus L rule. Or you call this rule as Bohr-Bury's rule as well. Now, what this Bohr-Bury's rule says? Bohr-Bury's rule says that more the value of N plus L, more is going to be the energy. More is going to be the energy of the subshell. Number 1. Number 2, if N plus L value is same for 2 subshells, then remember, more the N value means more the energy. Lesser the N value means lesser the energy. Now, you can check it out. N value here is 5. For F subshell, what is the value of L? S, P, D, F. L value is 3. N plus L, 5 plus 3 is 8. N value is 6. For P, L is 1. So 6 plus 1 is 7. 5 plus 1 is 6. 4 plus 2 is 6. We have to arrange them on the basis of decreasing energy. So 5F will have maximum energy, followed by 6P. Now, among 5P and 4D, both have same N plus L value. Now, decide on the basis of N. More the N value, more the energy. A is the correct answer. Yes? Perfect. I believe this is also clear. What do you think about this one? The total number of atomic orbitals in 4th energy level. N is equal to 4. Tell me one thing. In N is equal to 4. N is equal to 4 means 4th shell. How many subshells will be there? Subshell is given by L. L will be from 0 to N minus 1. So 0, 1, 2, and 3. These are the L values. And every value of L represents a subshell. So this is your S subshell, this is P subshell, this is D subshell, and this F subshell. Right? This F subshell. S subshell has got 1 orbital, P subshell has got 3 orbitals, D subshell has got 5 orbitals, and F subshell has got 14 orbitals. Sorry, 7 orbitals. 7 orbitals. So total how many? 7 plus 1, 8, 8 plus 3 is 11, 11 plus 5 is 16. So there are total 16 orbitals. 16 atomic orbitals. Well, this can be solved like this also. total number of atomic orbitals in a shell, or I can say maximum orbitals in a shell, is equal to the value of n square. N is the principal quantum. N is 4, 4 ka square is 16. So you saw how come it's 16. You exactly saw how come it's 16. Okay? What are degenerate orbitals? Degenerate orbitals are the ones which have got same energy, right? Degenerate orbitals, they have same energy. So, simple. Degenerate orbitals are the ones which have same energy. Perfect? So, with this, we are done with atomic structure. So, next, before we start the next chapter, we'll take a small break. Okay? You can have your tea, lunch, whatever. Then we'll start the next chapter. But I would want every one of you to be back on time. Everyone should be back on time. All right? Everyone should be back on time. Then only I'll be starting the next chapter. So tell me once if atomic structure is clear now. Whatever questions I showed you, these questions will be only asked. Don't worry about anything else. These are the questions you'll be asked in your exam. Quick. Can you tell me quickly in the chats if this is clear? Okay. Perfect. Chalo, I'll see you exactly at 2:30 now. I'll see you exactly at 2:30. You can have your lunch and something. Guys, can you hear me? Am I audible again? Every one of you? Am I audible, visible again to every one of you? All right. So are you done with your lunch? Yeah? Done with your lunch? सर कहाँ गए? सर यहीं है. All right. So we are going to start the new chapter now. Before starting the new chapter, can you tell me, is the atomic structure part clear? Is the atomic structure clear? Say yes or no in the chats, everyone. And whatever topics are mentioned in the atomic structure, whatever topics are discussed in the atomic structure, you'll be getting the questions from the same topics, okay? No, I did not have my lunch. Whenever I take marathons, I don't eat basically. I just keep on having the coffee, tea in between. Guys, whatever I'm teaching you, this is enough. You'll get the similar questions in your exam. Don't worry. I'm telling you. I'm telling you, don't worry. Chill. Okay? Thank you. Shadi Mubarak, sir. Shukriya. Happy married life. Thank you. Thank you. Thank you. Okay, should we start now? Should we start now? Party I'll give you after you crack your NEET, okay? After that, there'll be party. Till then, you just study. Chalo, let's get going then. Let's get started. Guys, whatever topics I'm teaching you in a chapter, I mean, these are the most favorite topics from which questions are. Okay? And you'll be getting the questions from these topics on. All right? Don't worry about anything else. Chalo, let's move on and let's start the new chapter. And the new chapter is going to be your redox reaction. It is going to be your redox reaction. It's not a big chapter, it's a small chapter. It will not take more than 1 hour to complete. Okay? So first of all, what all topics we have to cover in redox reaction? From which questions are asked? Let's talk about that. First of all, the first topic is going to be oxidizing reducing agents. How do we identify? Whether the substance is oxidizing or reducing agent? Number one. The second topic from which questions will be coming, that will be your equivalent mass. Calculation. The third one from which questions will be asked, what is that going to be? That is going to be your balancing of redox reaction. Okay. And one more topic, that is oxidation state from structures. These are basically the topics from which questions will be asked in your NEET examination. Apart from these, questions won't be asked. These are the topics from which questions will be asked from the chapter redox reaction. So let's get going. Let's get started with the first topic, that is your oxidation state from structures. So my dear students, you mark the heading as structures of some important compounds. There are some compounds, my dear students, and you will have to remember their structures. There is no shortcut to remembering the structures. You just have to practice them 2-3 times and automatically you'll remember them. The first structure which you are going to remember, that's going to be your CrO5. CrO5. Second one will be your CrO6. The third one is going to be your H2SO5. H2SO5. Fourth one is going to be your H2S2O7. Fifth one will be H2S2O8. Sixth one will be Na2S4O6. Okay. There are a few more structures which I'll be writing on the next slide after some time. So first of all, what is the structure of CrO5? This is how your CrO5 looks like. This is how your CrO5 looks like. CrO6. This is how your CrO6 looks like. H2SO5. This is how your H2SO5 looks like. H2S2O7. This is how your H2S2O7 looks like. H2S2O8. This is your H2S2O8. This is your S4O6 dinegative. S4O6 dinegative. These are, my dear students, some of the structures which you have to remember. And you have to remember their oxidation states as well. Chromium, its oxidation state here, when you calculate, it will come out be +6. This chromium here again is in +6 oxidation state. This sulfur here is again in its +6 oxidation state. This sulfur is in +6. 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 This sulfur is in +5. This is 0. This is 0. And this is +5. These are some of the structures, some of the important structures, and the oxidation states of the underlined elements which are mentioned over here. You'll have to remember them. Number one. Similarly, there are a few more structures, people, which you have to remember. What is that? There is something called as Br3O8. There is something called as C3O2. There is something called as K3CrO8. Another one is going to be H3PO2. Another one will be H3PO3. Another one will be H3PO4. And another one will be H3PO5. Well, if I draw their structures, Br3O8 looks like this. This is your Br3O8. C3O2. This is your C3O2. K3CrO8. This is K3CrO8. H3PO2. H3PO2. H3PO3. H3PO4. H3PO4. H3PO5. Okay, these are some of the important structures, my dear students, which you have to know. Okay, again, there is no shortcut towards drawing these structures. You just have to try them once, twice, then only you can remember them. Otherwise, you won't be able to do that. Okay, otherwise, you won't be able to remember them. Now, you have to remember the oxidation states as well. Well, first of all, this particular bromine, it is in +6 oxidation state. This is in +4 oxidation state. This is in +6 oxidation. This carbon is in +2 oxidation state. This is 0. This is +2. This chromium will be in +5 oxidation state. This phosphorus is in +1. This is in +3. This is in +5. And this is also in +4. These are some of the important structures which you have to remember. Okay? All right? So how to know whether double bond comes single bond? You have to remember them. You have to practice them once, twice. You have to remember them. This is memory based. This is memory based. There's no shortcut towards that. There is no shortcut towards that. Now, what is important here? What is important here? Let me talk about that. What is important here? That is, let me talk about that. My dear students, the point is, what is oxidation? What is reduction? What is an oxidizing agent? And what is a reducing agent? What is oxidation? What is reduction? What is an oxidizing agent? And what is a reducing agent? Understand. Just one thing I would want you guys to remember. Whenever you see oxidation state of an element increasing, whenever you see oxidation state of an element increasing, remember, the element whose oxidation state will be increasing, that element undergoes oxidation. Whenever oxidation state of an element decreases, remember that element undergoes reduction. That element undergoes reduction. Increase in the oxidation state is called as oxidation. Decrease in the oxidation state is called as reduction. The one that undergoes oxidation is called as reducing agent. The one that undergoes reduction is called as oxidizing. This is a simple thing which you have to remember. Now try to understand what exactly I'm going to do. Have a look. First of all, is there any charge on magnesium? No. Its oxidation state is 0. Is there any charge on oxygen? No. Its oxidation state is 0. Can we calculate oxidation state of this magnesium? Yes. Let its oxidation state be X. What is the most common oxidation state of oxygen? That is -2. Is equal to net charge is 0. I believe this is something every one of you would be knowing. So magnesium here is in +2 oxidation. Correct? And oxygen, as I told you, its most common oxidation state is -2. Now, is the oxidation state of magnesium increasing or decreasing? Check it out. 0 to +2. Increase. Increase in the oxidation state is what you call as oxidation. Right? 0 to -2. 0 to -2. Decrease. Decrease in the oxidation state is what you call as reduction. The one that undergoes oxidation is called as reducing agent. The one that undergoes reduction is called as oxidizing. As simple as that. This is how you identify in a reaction which one is oxidizing agent and which one is reducing agent. Is this clear? Is this clear, people? Quickly in the chats. Quickly in the chats, every one of you. Yeah? For example, let me take one more reaction. I'm taking the reaction like this. MnO4 negative plus Fe di positive. It gives Mn di positive plus Fe tri positive. Now, in this reaction, I have to check which one is oxidizing agent and which one is reducing agent. First of all, my dear students, I will calculate the oxidation state of manganese here. How? Let the oxidation state of manganese be X. Oxygen shows -2 oxygen state. There are 4 oxygen atoms. Net charge is -1. When you solve, the X value comes out to be +7. So this manganese here is in +7 oxidation. This iron here is in +2 oxidation state. This manganese here is in +2 oxidation state. This iron here is in +3 oxidation state. Now tell me one thing. Is the oxidation state of manganese increasing or decreasing? +7 to +2. Decrease. Decrease in the oxidation state is what you call as reduction. And the one that undergoes reduction will be your oxidizing agent. +2 to +3. +2 to +3. Increase in the oxidation state. Increase in the oxidation state is what you call as oxidation. And the one that undergoes oxidation will be your reducing agent. As simple as that. This is how you check whether the substance in a reaction is the oxidizing agent or reducing agent. Okay? This is how you check whether the substance is the oxidizing agent or reducing agent. For example, let me take one more reaction so that you'll understand this in a better way. For example, you have got Cr2O7 di-negative plus Sn di-positive. It gives Cr tri-positive plus Sn plus 4. Let's say this is your reaction. First of all, I will calculate the oxidation state of chromium here. Let the oxidation state of chromium is X. But here you have got 2 chromium atoms, so it's 2X. Oxygen, its common oxidation state -2. There are 7 oxygen atoms. Net charge here is -2. When you calculate, the value of X comes out to be plus 6. So this chromium is in plus 6 oxidation. This tin here, plus 2 oxygen state. This chromium here, plus 3 oxygen state. This tin here, plus 4 oxidation. Right? Now check it out. Plus 6 to plus 3. Plus 6 to plus 3. Decrease. Decrease means reduction. Decrease means reduction. The one that undergoes reduction is the oxidizing agent. Plus 2 to plus 4. Increase. Increase in the oxidation state is what you call as oxidation. And the one that undergoes oxidation will be your reducing agent. So this is how you identify whether the substance in the reaction is your oxidizing agent or the reducing. Right? Got it, people? Got it, everyone? Say yes or no once in the chats quickly. Yes or no once in the chats quickly. Yes? Now, guys, there is one thing which I would want you guys to remember. What is that? What is that? For example, I'm writing a substance. I'm writing a molecule, H2O. I'm writing a molecule, H2O. Okay? I'm asking you directly whether it's oxidizing agent or reducing agent. I'm not giving you any reaction. I'm not giving you any reaction. I just wrote a substance, H2O, and I'm asking you whether it's oxidizing agent or reducing agent. How do you do it? How do you check it? There's a proper sequence to be followed. What is that? Remember, whenever you are given with a substance and you are supposed to check whether it's an oxidizing agent, whether it's going to behave like the reducing agent, or it can behave like both. How do we check that? Understand. The first step always is to calculate the oxidation state of the central atom. This is always my first step. Calculate the oxidation state of the central atom. Calculate the oxidation state of the central atom. If the central atom is present, if the central atom is present in lowest possible oxidation state, if the central atom is already present in lowest oxidation state, if the central atom is already present in the lowest oxidation state, that means it cannot decrease its oxidation state further. It cannot decrease its oxidation state further. But it can increase its oxidation state. When it increases its oxidation state, it will undergo oxidation. And when it undergoes oxidation, it's going to behave like the reducing agent. It's going to behave like the reducing agent. Number one. Number two, if the central atom is present, if the central atom is present in highest possible oxidation state, highest, if the central atom is already present in highest oxidation state, I'll tell you what are lowest oxidation states and highest oxidation states in some time. Just wait. First, remember, if the central atom is already present in highest oxidation state, that means it cannot further increase its oxidation state, but can decrease. When it decreases, it undergoes reduction. When it undergoes reduction, it behaves like the oxidizing agent. Similarly, when the central atom is present, if central atom is present in its intermediate oxidation state, in its intermediate oxidation state, that means neither highest nor lowest. If the central atom in a compound is present neither in highest oxidation state nor in lowest, that means it can increase as well as decrease. So it can behave both oxidizing as well as reducing agent. It can behave both oxidizing as well as reducing agent. Okay. Now, before showing you how do we apply this concept, there are a few things which I want to tell you. There are a few things which I'm going to tell you. And what are those things? Try to understand and remember. My dear students, if you talk about your P block elements, if you talk about your P block elements, your P block elements, they show a range of oxidation state. Your P block elements, they show a range of oxidation state. And the range of oxidation states shown by P block elements lies between group number -18 to group number -10. Group number -18 to group number -10. What does that mean? For example, you talk about chlorine. Talk about chlorine. Chlorine comes in which group? It is the 17th group element. Its group number is 17. So what is the range of the oxidation state which chlorine shows? Group number -18. So 17 minus 18 is -1. 17 minus 10 is +7. Okay. So I would say this is the lowest possible oxidation state of chlorine. This is the highest possible oxidation state of chlorine. Okay. For example, talk about sulfur. Sulfur belongs to oxygen family. Oxygen family means group number 16. Group number 16. So what is the range of oxidation states which sulfur shows? It will be group number minus 18. 16 minus 18 is minus 2. 16 minus 10 is plus 6. So this is the lowest possible oxidation state of your sulfur, and this is the highest possible oxidation state of sulfur. Similarly, there are two elements which I would want you guys to remember, which you'll frequently see here. One is your manganese, one is your chromium. Remember, the maximum, the highest oxidation state shown by chromium is plus 6. The highest oxidation state shown by manganese is plus 7. Remember these two elements, they'll be frequently used. Manganese, its highest oxidation state will be plus 7. Chromium, its highest oxidation state will be plus 6. Now see how I'm going to apply this table in the form of questions. Try to understand very properly. For example, I'm writing HCl, I'm writing H2O, I'm writing K2Cr2O7, I'm writing KMnO4, I'm writing, let's say HNO3. I have to check which of the following substances will behave as oxidizing agent, which one will behave as reducing agent, which one can behave both oxidizing as well as reducing. So what do? Try to understand. First of all, people, calculate the oxidation state of chlorine here. Halogen minus 1, oxygen minus 2, chromium when you calculate it will be plus 6, manganese when you calculate it will be plus 7, nitrogen when you calculate it will be plus 5. So you calculate the oxidation state, right? Now tell me the range of oxidation state that chlorine shows. Few minutes back I told you minus 1 to plus 7. Minus 1 to plus 7. Oxygen, the range of oxidation states will be minus 2 to plus 6. Chromium, its highest oxidation state is plus 6. Manganese, its highest is plus 6. Nitrogen belongs to group 15. So 15 minus 18 is minus 3. 15 minus 10 is plus 5. Now tell me one thing. Is chlorine here in minus 1? Yes. Minus 1 is the lowest oxidation state of chlorine. So chlorine is already in lowest. Chlorine here is already in lowest oxidation state. If chlorine is in lowest oxidation state, it cannot further decrease its oxidation, but it can increase. When it increases, it undergoes oxidation, behaves like the reducing agent. So HCl is your reducing agent. Oxygen here is in minus 2. Minus 2 is already the lowest oxidation state of oxygen. So oxygen is already in lowest, cannot further decrease. If it cannot decrease, but it can increase. When it increases, undergoes oxidation, behaves like the reducing agent, right? Chromium, plus 6. Plus 6 is the maximum oxidation state of chromium. So it cannot increase, but it can decrease. When it decreases, undergoes reduction. So it is the oxidizing agent. Similarly, KMnO4, oxidizing agent. HNO3. What is it going to be? Can you tell me in the chats? Quickly? Waiting for your answer. HNO3. This is already in highest oxidation state. So it cannot increase, but it can decrease. When it decreases, undergoes reduction. When it decreases, undergoes reduction. Reduction means oxidizing agent. I hope from now onwards you can easily check which substance is oxidizing agent, which substance is reducing. Got it? Similarly, guys, there are a few more things which I would want to tell you here. What is that? Have a look. Remember, strength of the oxidizing agent. Similarly, strength of the reducing agent. Similarly, acidic strength. Similarly, basic strength. Remember, this is directly proportional to the oxidation state of central atom. This is inversely proportional to the oxidation state of central atom. This is directly proportional to oxidation state of central atom. This is inversely proportional to oxidation state of central atom. For example, try to understand very carefully. For example, I'm writing HClO4, HClO3, HClO2, and HClO. I need to give the order of acidic strength. As I told you, acidic strength is directly proportional to oxidation state of central atom. So calculate the oxidation state of central atom, people. Calculate the oxidation state of central atom. This will be +7, this will be +5, this will be +3, and this will be +1. More the oxidation state of central atom, more is going to be the acidic strength. Number 1. For example, you have got KMnO4, you have got K2Cr2O7. You have to check which one is stronger oxidizing agent. Stronger oxidizing agent. Strength of oxidizing agent directly proportional to oxidation state of central atom. Magnesium +7, chromium +6. When you calculate, more the oxidation state of central atom, stronger the oxidizing agent. Simple. For example, you have got NH3, you have got H2S. You have to tell me the order of reducing agent. Which one is the stronger reducing agent? Calculate the oxidation state. Nitrogen in -3, sulfur in -2. Strength of reducing agent is inversely proportional to oxidation state of central atom. Lesser the oxidation state, stronger the reducing agent. So this is the order of reducing agent. So these 4 rules you have to remember. Nothing more, nothing less. Okay? Perfect. Similarly, guys, there comes one more important topic here. What is that? That is equivalent mass calculation. How do we calculate equivalent mass of different substances? Let me first of all tell you there's a formula. There's a formula by means of which we can calculate equivalent masses of different substances. And what is that formula? Remember, equivalent mass of the substance is always equal to molar mass of the substance divided by n factor of the substance. Molar mass of the substance divided by n factor of the substance. Now the point is, how do we calculate n factor of the substance? Now the point is, how do we calculate n factor of the substance? Let's try to understand. My dear students, first of all, if I talk about the n factor of elements, n factor of elements. Remember, n factor of element is nothing but the valency of element. Remember, the n factor of element is nothing but the valency of element. For example, I'm taking some elements: nitrogen, oxygen, sodium, magnesium. I want their equivalent masses. Now, equivalent mass is what? Molar mass divided by n factor. So basically, I have to calculate their n factors. Now, how do we calculate n factor of an element? N factor of an element is valency. What is the valency of nitrogen? 3. What is the valency of oxygen? 2. What is the valency of sodium? 1. What is the valency of magnesium? 2. So these are the n factors of these elements. If you got the n factors, you can calculate equivalent masses. How? Molar mass divided by n factor. So equivalent mass of nitrogen will be equal to molar mass of nitrogen divided by n factor of nitrogen. Similarly, equivalent mass of oxygen is equal to molar mass of oxygen divided by n factor of oxygen. Equivalent mass of sodium will be equal to molar mass of sodium divided by n factor of sodium. Equivalent mass of magnesium will be equal to molar mass of magnesium divided by n factor of magnesium. Right? So this is how you calculate the n factors of elements. Number 2. If I talk about n factor of salts, n factor of salts is nothing but it is equal to LCM of what? LCM of charge on cation, LCM of charge on cation and charge on LCM of charge on cation and charge on anion. Now try to understand what exactly I'm going to do. First of all, for example, I'm taking the salt as NaCl. I'm taking one more salt as BaCl2. I'm taking one more salt as AlCl3. These are different salts which I've taken, right? Now this is 1, this is 1, this is 1, this is 2, this is 1, this is 3. Now first of all, do the crisscross theory. This 1 comes as charge here, this 1 comes as charge here. This 2 goes here, +2, this 1 goes here, -1. This 3 goes here, +3, this 1 goes here, -1. Now, tell me, what is the LCM of 1 and 1? That's 1. What is the LCM of 2 and 1? That's 2. What is the LCM of 3 and 1? That is 3. And LCM of charge on cation and anion gives us the n factor. And if you got the n factor of salt, you can easily calculate its equivalent mass. How? Molar mass divided by n factor. Molar mass divided by n factor. Molar mass divided by n factor. I believe I'm clear with this. Yes? Yeah? Is this clear? Is this clear, people? Okay. Chalo, moving on to the third thing. What is that? The third thing is, how do we calculate n factor of acids? How do we calculate n factor of acids? N factor of acids is nothing but, it is defined as the basicity of the acid. It is defined as the basicity of the acid. And how do we define the basicity? In general, there are two ways to define basicity. The first is number of H positives an acid donates. Number of H positives an acid donates, or number of OH negatives an acid accepts. Number of OH negatives an acid accepts. For example, if I take some acids like HCl, you have got H2SO4, you have got, for example, HNO3, you have got, for example, H3PO4. Can you tell me, when you introduce these acids in water, how many H positives this acid is going to liberate? It's going to give one H positive. This will give two H positives. This will give one H positive. And this will give three H positive. And the number of H positives an acid donates, that defines its basicity. And whatever is the basicity of the acid, that's what you call as N factor. So N factor of HCl here is 1. N factor of this is 2. This is 1. And this is 3. And if you got the N factors, you can calculate their equivalent masses. Molar mass divided by N factor. Molar mass divided by N factor. Right? Now guys, one more thing. Remember one simple statement. An acid donates only that hydrogen. Only that hydrogen in the form of H positive. An acid donates only that hydrogen in the form of H positive, which is attached to what? Attached to more electronegative element, like chlorine, oxygen, nitrogen, etc. An acid will be donating, an acid donates only that hydrogen in the form of H positive, which will be attached to more electronegative element like fluorine, oxygen, nitrogen, etc. What does that mean? For example, I'm writing a compound like this, H3PO2, H3PO3, H3PO4, H3PO5. These are all acids. And I want you to calculate their N factors. Now, a lot of you will think, this is going to give 3H positives, this will give 3H positives, this will give 3H positives, that will give 3H positives. So N factor of all of them should be 3. But that's not the case. Why is that? If you look at the structure of H3PO2 that I gave you a few minutes back, this is the structure of your H3PO2. H3PO3 looks like this. H3PO4 looks like this. H3PO5 looks like this. Okay. Now tell me one thing. How many hydrogens do you see here? 3. Out of 3 hydrogens, how many hydrogens are attached to more electronegative? 1. Here, 2 hydrogens. Here, all the 3 hydrogens. Here, all the 3 hydrogens. I told you a few minutes back. An acid donates only that hydrogen. An acid donates only that hydrogen in the form of H positive, which is attached to more electronegative element. So this acid will be donating only one H positive. So its basicity will be 1. Its N factor is 1. Its N factor is 2. Its N factor is 3. Right? Even its N factor is 3. And if you got the N factors of these acids, you can calculate their equivalent masses. How? Their molar masses divided by their N factors. Understood? Understood, people? Similarly, if you talk about the N factor of bases, how do you calculate N factor of bases? N factor of base is nothing but, you call that as the acidity, right? Number of OH negatives a base donates. Number of OH negatives a base donates, or number of H positives. a base accepts. Or a base accepts. Okay? For example, take some common bases. Like you have got NaOH. For example, you have got BaOH whole twice. For example, you have got AlOH whole thrice. These are all your bases. Now, this base is going to give away one OH negative. This base gives away two OH negatives. This base gives away three OH negatives. And the number of OH negatives donated by the base, that defines its n factor. So, n factor of this base is 1, n factor of this base is 2, n factor of this base is 3. If you got the n factors, you can calculate the equivalent masses. Molar mass divided by n factor. Okay. For example, guys, I'm writing a reaction like this. NH3 plus H positive. Or let me keep it like this. NH3 plus H2O gives NH4 positive. Gives NH4 positive. I want you to calculate n factor of NH3. I want you to calculate n factor of NH3. If you look carefully, how many hydrogens do you see here? 3. When this NH3 is introduced in water, it got converted into NH4 positive. And how many hydrogens do you see here? 4. It had 3 hydrogens here. Now it has 4. That means when NH3 is introduced in water, can I say it has accepted one H positive? It has accepted one H positive. And the number of H positives a base accepts. The number of H positives a base accepts. That defines its acidity. And whatever is the acidity of the base, that's its n factor. So its n factor here is what? Its n factor here is 1. Its n factor here is 1. Okay? Its n factor here is 1. Now the most important thing, what is that? That is, how do we calculate the n factors of oxidizing and reducing agents? That is the most important. How do we calculate the n factors of oxidizing and reducing agents? How do we calculate n factors of oxidizing and reducing agents? My dear students, you have to remember a few things. For example, I am taking a reaction. A plus B gives, or let me keep it like this. A2 plus B2 gives 2 times A positive plus 2 times B negative. This, for example, the reaction. Okay? This, for example, the reaction. If I ask you what is the oxidation state of A here, you'll say 0. B, 0. This A, plus 1. This B, minus 1. Oxidation state of A is increasing from 0 to plus 1. 0 to plus 1 means increase in the oxidation. Increase in the oxidation state is what you call as oxidation. So this is undergoing oxidation. If it undergoes oxidation, it is your reducing agent. Right? Similarly, 0 to minus 1, decrease in the oxidation state. Decrease in the oxidation state is what you call as reduction. And the one that undergoes reduction is your oxidizing. So you identified your oxidizing and reducing agents. Now, how do I calculate their n factors? I'll say n factor of A2 will be equal to. Similarly, n factor of B2 will be equal to. How do we do it? N factor of A2. This is the initial oxidation state of A. This is the final oxidation. Initial, final. Do one thing. Write the final oxidation state first, minus initial oxidation state. Final minus initial. Mod. Multiplied by. What is the subscript of this A? 2. Multiplied by this subscript. The value comes out to be 2. So 2 is the n factor of this A2 here. Similarly, what is the n factor of B2? What is the n factor of B2? This is the initial oxidation state of B. This is the final oxidation state of B. So final minus initial come mod multiplied by. What is the subscript of B? That is 2. The value comes out to be 2. So these are the n factors of A2 and B2 respectively. Understood? For example, if I give you certain questions like this, for example, I2 gives IO3 negative. Second one, VO gives V2O5. IO3 negative gives IO4 negative. C2O4 di-negative gives CO2. I want you to calculate n factors of all these species. Why n factors? Because I want to calculate their equivalent masses. And equivalent mass, you already know, that's molar mass divided by n factor. Right? Can you do it? Can you give it a try? See guys, see what we are supposed to do. Is there any charge on this iodine here? No. What about the oxidation state of this iodine? When you calculate, it will be plus 5. X minus 2 into 3 is equal to minus 1. What is the oxidation state of vanadium here? Plus 2. This vanadium, this will be 2x, minus 2 into 5 is equal to 0, so plus 5. This iodine, plus 5, this iodine, plus 7. This carbon here, when you calculate, it will be plus 3. This carbon here will be in plus 4. Now check it out. 0 to plus 5. Final minus initial. The value comes out to be 5. Multiplied by subscript. 5 2s are 10. So its n factor is 10. Plus 2 to plus 5. Its n factor is 3. Plus 5 to plus 7. Its n factor is 2. Plus 3 to plus 4. What is the change? Final minus initial. Value is 1. Subscript is 2. 1 and 2 is 2. Its n factor is 2. Is all this clear, people? Every one of you in the chats once. Yeah? Is it clear? Simple. Final oxidation state minus initial oxidation state multiplied by subscript. That's it. One more thing, guys, which you need to remember. What is that? Remember about KMnO4. Remember about KMnO4. KMnO4 is basically a very strong oxidizing agent. It's a very strong oxidizing agent. And this KMnO4, it shows different reactions in different mediums. This KMnO4, it shows different reactions in different mediums. The first thing which you need to know, what is that? KMnO4 gets converted into Mn di positive. But in which medium? In acidic medium. KMnO4 in acidic medium gets converted into Mn di positive. KMnO4 in neutral medium, or I would say slightly alkaline medium, gets converted into MnO2. And the same KMnO4 in strongly alkaline medium, gets converted into MnO4 dinegative. These are the three things which I would want you guys to remember. Okay? Right? Now, people, understand. Oxidation state of manganese here is plus 7. Here the manganese is in plus 2 oxidation state. Here manganese is in plus 4 oxidation state. Here manganese is in plus 6 oxidation. If you look carefully, plus 7 to plus 2. Plus 7 to plus 2. What is the change? Final minus initial. The value is 5. Only 1 manganese. So, n factor of KMnO4 in acidic medium is 5. Similarly, plus 7 to plus 4. What is the change? Final minus initial. The value is 3. So, its n factor here is 3. Similarly, its n factor here is 1. Perfect. Remember these three things as well. Okay? Perfect. Perfect, people. Perfect in the chats quickly. I believe it's clear. And if it is clear, then there are few more things which you need to remember about K2Cr2O7 as well. K2Cr2O7, again, it's a strong oxidizing agent. And remember, in acidic medium, it gets converted into Cr tripositive. Chromium here is in plus 6 oxidation state. So plus 6 to plus 3. Final minus initial, the value will be 3. Multiplied by subscript 2. So 3 2s are 6. N factor of K2Cr2O7 in acidic medium is 6. Okay? Alright. Now, guys, there are a few more things about this KMnO4 and K2Cr2O7. There are some important reactions of KMnO4 and K2Cr2O7 in acidic medium. Some important reactions of KMnO4 and K2Cr2O7 in which medium? In acidic medium. Remember them as well. Let me tell you, KMnO4 as well as K2Cr2O7 converts Fe di positive into Fe tripositive. In which medium? Acidic medium. They convert Sn di positive into Sn plus 4. In which medium? Acidic medium. They convert I negative into I2. In which medium? Acidic medium. They convert oxalate ion into what? Into carbon dioxide. In which medium? Acidic medium. Similarly, they convert H2O2 into O2. In which medium? Acidic medium. They convert H2S into sulfur. In which medium? Acidic medium. Similarly, they convert SO2 into SO4 dinegative. In which medium? Acidic medium. These are few more additional points which you need to remember about the KMnO4 and K2Cr2. Right? Okay. Okay. Alright, people. So remember these important things about KMnO4 and K2Cr2O7 in which medium? In acidic medium. Alright. Now there is one more topic here. What is that? That is balancing of redox reactions. You get questions from balancing as well. And I'll give you some tricks to do the balancing of redox reaction. Just remember that. Okay? Understand. First of all, let's talk about balancing of redox reactions in acidic medium. How do you balance the redox reaction in acidic medium? How do you balance the redox reactions in acidic medium? See, guys. Understand properly. For example, I'm writing a reaction. MnO4 negative plus Fe di positive gives Mn di positive plus Fe tri positive. This reaction I have to balance in acidic medium. This reaction I have to balance in which medium? In acidic medium. How exactly am I going to do that? My first step always will be to calculate the n factors of reactants. My first step always is going to be to calculate the n factors of reactants. See, this manganese has in +7 oxidation state. +7 to +2, +7 to +2, change, final minus initial, the value is 5. Subscript of manganese is 1, so its n factor is 5. +2 to +3, +2 to +3, change, final minus initial, the value is 1, its n factor is 1. So first of all, you got the n factors of reactants. That's always your first step. Get the n factors of reactants. After getting the n factors of reactants, just crisscross these n factors. Crisscross means this 1 here, this 5 comes here. After calculating the n factors, crisscross the n factors. Now, balance all the atoms except hydrogen oxygen. Balance all the atoms except hydrogen and oxygen. So 1 manganese on this side, 1 manganese on this side. 5 iron on this side, 5 iron on this side. Balanced all the atoms except hydrogen oxygen. Now, balance oxygen with the help of water molecules. 4 oxygen on this side. No oxygen on this side. So this side is oxygen deficient. And how many oxygen deficiencies? 4. So add 4 water molecules on this. Now, balance hydrogen with the help of H positives. There is no hydrogen here. There are 4 2s, 8 hydrogens on this side. So this side is hydrogen deficient. How many? 8 hydrogens. So add 8 H positives on this side. The reaction is balanced. The reaction is balanced. So what I did, first of all, I got the n factors of reactants. Then I crisscrossed the n factors. Then I balanced all the atoms except hydrogen oxygen. Then I balanced oxygen with the help of water molecules. Then I balanced hydrogen with the help of H positives. Is it clear? Let me take one more example. With that, things will be more clear. For example, I've got Cr2O7 dinegative, right? Plus, let's say this is Sn di positive. It's giving Cr tri positive plus Sn plus 4. I want to balance this reaction in acidic medium. I want to balance this reaction in acidic medium. I want to balance this reaction in acidic medium. How exactly? Have a look. First of all, get the n factors of reactants. Oxidation state of chromium here is +6. Tin is in +2. This is +3. This is +4. +6 to +3. +6 to +3. Change. Change means final minus initial. The value is 3 into subscript 2. So 3 2s are 6. Its n factor is 6. +2 to +4. N factor 2. What are the n factors? After getting the n factors, crisscross them. So this 2 comes here. This 6 goes. Okay. Now, balance all the atoms except hydrogen oxygen. Balance all the atoms except hydrogen oxygen. So 2 2s are 4 chromium on this side. So 4 times. 6 tin on this side. 6. Now balance oxygen with the help of water. 7 2s are 14. 14 oxygen atoms on this side. No oxygen atom on this side. So add 14 water molecules to that side, which is oxygen deficient. Now, balance hydrogen. How many hydrogens here? No one. How many hydrogens here? 14 to 28. So this side is hydrogen deficient. So add 28 H positives on this side, which is hydrogen deficient. Reaction is balanced. The reaction is balanced. Okay. So if you want me to write the steps also, I can write the steps also. First of all, you have to get the n factors. N factor of what? N factors of reactants. After that, you are supposed to crisscross the n factors. After crisscrossing the n factors, balance all atoms. Balance all except hydrogen, oxygen. Then balance oxygen with the help of water. And at the end, balance hydrogen with the help of H positive. That's all. This is the process which you are supposed to follow. Okay? Is it clear, guys? Tell me once. Is it clear? Is it clear? Is it clear, everyone? How to identify whether it's acidic or basic? That will be given in the question. Is it clear, people? I believe yes. And if it is clear, then there is one more thing left in this chapter. What is that? That is balancing in basic medium. Balancing of the redox reactions in basic medium. Again, here you have to follow some steps. And what are the steps? The first step is the same. What is that? Get the n factor of reactants. Second step, crisscross the n factors. Third step, balance all the atoms except hydrogen, oxygen. Balance all the atoms except hydrogen, oxygen. Then you have to balance negative charge with the help of OH negative. And then you have to balance oxygen with the help of water molecule. That's all. These are the steps which you are supposed to follow while balancing the reaction in basic medium. Let me give you one example so that you can remember it too. Let's say I'm writing the reaction like this. Cl2 plus IO3 negative gives Cl negative plus IO4 negative. This is the reaction. This is the reaction. I have to balance this reaction in basic medium. What is my first step? Get the n factors. Oxidation state 0. 0 to -1. 0 to -1. Change. Final minus initial. The value is 1. Multiplied with subscript. So 2. 1 into 2 is 2. Iodine here is in +5. Here iodine is in +7. +5 to +7. N factor 2. So I got the n factors. Now, crisscross the n factor. This 2 goes here. This 2 goes here. Balance all the atoms except hydrogen, oxygen. 2 2s are 4 chlorine, 4 chlorine. 2 iodines, 2 iodines. So till here I'm done. Now, balance negative charge with the help of OH negatives. Balance negative charge with the help of OH negative. Now understand. Do you see any charge here? No. The charge present on this molecule is -1. If the charge present on one molecule is -1, the charge present on 2 molecules will be -2. So on left side, the total negative charge is -2. Look at the right side. On 1 Cl charge is -1. On 4 Cl charge will be -4. On 1 IO4 charge is -1. On 2 IO4 charge is -2. So -4 -2 is -6. On left side, the total negative charge is -2. On right side, the total negative charge is -6. Now, which side is negative charge deficient? Say left side. And how many negative charge deficiencies? How many negative charge deficiencies on this side? So minus 2, minus 6. This side is negative charge deficient. How many negative charge deficiencies? 4. So add 4 OH negatives to that side, which is negative charge deficient. And at the end, balance oxygen with the help of water. Now balance oxygen with the help of water. How many oxygen atoms here? 3 2s are 6, 6 4 10. 4 2s are 8. This side 10 oxygen atoms, this side 8 oxygen atoms. So this side is oxygen deficient. So add 2 water molecules to this side, right? The reaction is balanced. Tell me once in the chats if this is clear. Tell me once in the chats if this is clear. Okay? Perfect. So with this, our redox chapter is also done. So we'll take a small break. Okay. After that, we'll start. What's the time? 3:30. So break till 4. And at 4, we'll be starting a new chapter. Okay? But I would want every one of you to be back. I would want every one of you to be back. Every one of you to be back on time. All right? I'll see you exactly at 4, guys. Exactly at 4. If you want to see the n factor again, you can just take the video a little back and it will be a repetition. Chalo, I'll start. I'll see you exactly at 4 p.m. Till then, you carry on. Is everyone back? Is everyone back? No, no, I'll have my food, my lunch, dinner after the session. After the session, after the session. Okay, can you tell me once in the chats whether the redox chapter is like perfectly clear? Can you tell me once in the chats? Can you tell me quickly in the chats, is the redox clear? Perfect, guys. So then we are going to move on to the next chapter, and the next chapter is your chemical equilibrium, my dear student. Chemical equilibrium. Chemical equilibrium. So first of all, before starting this chemical equilibrium chapter, let me tell you the topics from which the questions will be asked in your NEET examination. Okay? The first topic in chemical equilibrium from which the questions will be asked, that is equilibrium constant characteristics. Equilibrium constant characteristic. Number one. Number two is going to be the relation between Kp and Kc. A relation between Kp and Kc. This is the second topic from which questions will be asked. Then it's going to be Kp and Kc calculation. Kp and Kc calculation. Kp and Kc calculation, that is the third point. That is the third topic. By mole method and degree of dissociation method. Then comes to your Lee-Chatelier principle. Then it comes to your Lee-Chatelier principle from which the questions will be asked. Okay? These are basically the topics from which the questions will be asked from the chapter chemical equilibrium. All right? So without wasting any sort of time, let's directly jump into the chemical equilibrium chapter. All right? All right, people. So let's have a look. And let's start with the chemical equilibrium chapter. My dear students, first of all, the first point is, how do we write the expression of equilibrium constant? How do we write the expression for equilibrium constant? Okay. There are few things which I would want you guys to remember first of all. And what are those things? Try to understand. My dear students, whenever you see any reactant or product in aqueous phase, whenever you see any reactant or product in aqueous phase, that means in the bracket AQ will be mentioned. Whenever you see any reactant or product in aqueous phase, that means in the bracket AQ will be mentioned. Remember, for that reactant or product, active mass is nothing but its concentration. Whenever you see any reactant or product in gaseous phase, for that reactant product which will be in gaseous phase, its active mass is its concentration as well as pressure. Okay? And whenever you see any reactant present in pure solid or pure liquid form, its active mass is taken as 1. These are first of all the three things which I would want every one of you to remember. Number one. Number two, how do we write the expression of Kp and Kc? My dear students, first of all, Let's say this is the reaction. I want to write the expression of Kc. I want to write the expression of Kc. Whenever I'll have to write the expression for Kc, I'll be starting with the product. I'll be starting with the product, right? This is our product Hi, which is in gaseous phase. So I'll write concentration of Hi at equilibrium raised par stoichiometric coefficient 2 divided by, come to the reactant side. This H2 is in gaseous phase. So I'll write concentration of H2 at equilibrium raised par stoichiometric coefficient 1, concentration of I2 at equilibrium raised par stoichiometric coefficient 1. This is how you are going to write the expression for Kc for a reaction. Now similarly, if you want to write the expression of Kp, again you can write the expression for Kp. Start with the product. Now you have to write Kp expression. So you will write partial pressure of Hi at equilibrium raised par stoichiometric coefficient 2 divided by, come to reactant side, partial pressure of H2 at equilibrium raised par stoichiometric coefficient 1 and partial pressure of I2 at equilibrium raised par stoichiometric coefficient. So this is the simplest way of writing the expression for Kp and Kc for a reaction. Look at this particular reaction. Let's say I have to write the Kc and Kp expression for this reaction as well. Well, my dear students, in order to write the Kc expression, start with the product. I'll write concentration of PCl3 at equilibrium raised par stoichiometric coefficient, concentration of Cl2 at equilibrium raised par stoichiometric coefficient divided by concentration of PCl5 at equilibrium raised par stoichiometric. Okay. Similarly, Kp expression. Start with the products. I'll write partial pressure of PCl3 at equilibrium raised par stoichiometric coefficient, partial pressure of Cl2 at equilibrium raised par stoichiometric coefficient divided by partial pressure of PCl5 at equilibrium raised par stoichiometric coefficient. Okay. All right. For example, talk about this particular reaction. Talk about this particular reaction. Let's say I have to write the expression for Kc. I'll start with the product. This product is in solid form. As I told you, for solids, active mass is equal to 1. So basically, I've got nothing to do with the solids. I've got nothing to do with the solids. This carbon dioxide is in gaseous phase. I'll write concentration of carbon dioxide at equilibrium raised par stoichiometric. Now write the expression for Kp. Kp expression is again going to be partial pressure of carbon dioxide at equilibrium raised par stoichiometric. Simple. Look at this particular reaction. This is in solid form, nothing to do with that. Gaseous phase, gaseous phase. So write the expression for Kc. Start with the product. I'll write concentration of SO3 at equilibrium raised par stoichiometric coefficient, concentration of O2 at equilibrium raised par stoichiometric coefficient. Similarly, Kp expression. Start with the product. I'll write partial pressure of SO3 at equilibrium raised par stoichiometric coefficient divided by partial pressure of O2 at equilibrium raised par stoichiometric coefficient, which is 3/2. Got it? Did you understand how do we write the expression for Kp and Kc? Say yes or no in the chats once. Did you understand how do we write the expression for Kp and Kc? Let me know once in the chats quickly. Yeah? Everyone in the chats, people, quickly. So you will have to start with the products, then go to the reactants. Now guys, there is a relation between Kp and Kc. There is a relation, a direct relation between Kp and Kc. For example, this is the reaction. The reaction is N1A gas gives N2B gas. Let's say this is a reaction. Now there is a direct result between Kp and Kc. And what is the direct result? Remember, Kp is equal to Kc RT raised par delta Ng for this gaseous phase reaction. This is the result between Kp and Kc. Kp is equal to Kc RT raised par delta Ng. Now, if I just say one thing, if delta Ng for the reaction is 0, if delta Ng for the reaction is 0, anything raised par 0 is 1, that means the reaction whose delta Ng will be 0, its Kp and Kc will be always equal. Similarly, if delta Ng for the reaction is non-zero, if delta Ng for the reaction is non-zero, remember your Kp and Kc won't be equal. In your NEET examination, which happened a few days back, there was a question asked from this as well. In which of the following reactions Kp and Kc won't be equal? So basically, you were supposed to check that reaction whose delta Ng is non-zero. Now, first of all, you must be thinking, what is this delta Ng all about? Delta Ng is simply number of moles of gaseous product minus number of moles of gaseous reactant. Number of moles of gaseous product minus number of moles of gaseous reactant. How many moles of gaseous product do you see? This is the product. It's in gaseous phase. So it's a gaseous product. How many moles of it do you see? N2 minus number of moles of gaseous reactant. If this is a gaseous reactant, its moles are N1. So N2 minus N1 gives me the number of moles of, N2 minus N1 gives me the delta Ng for the reaction. So this is the result which I would want every one of you to remember. And people at the same time, there are the units. What are the units of Kp and Kc? Let me talk about that as well. If I talk about the units of Kp and Kc, remember the units of Kc are moles per liter raised per delta Ng. And the units of Kp is atmosphere raised per delta Ng if the pressure is given in atmospheres. And if the pressure is in bar, it's going to be bar raised per delta Ng. So unit of pressure raised per delta Ng. Now tell me one thing. If you have any reaction whose delta Ng is 0, if this is 0, anything raised per 0 is 1. If this is 0, anything raised per 0 is 1. So that reaction whose delta Ng is 0, its Kp and Kc will be unitless. Okay? So if delta Ng for the reaction is equal to 0, Kp and Kc, what do they become? They become unitless quantity. Okay? They become unitless. All right? Tell me one thing. Write the expression of Kp in terms of Kc in all these reactions. Write the expression of Kp in terms of Kc in all these reactions. If you look at the first reaction, in the first reaction, if I ask you what is the delta Ng value, delta Ng is number of moles of gaseous product, which is 2, minus number of moles of gaseous reactant, which is 1 plus 1, 2. So 2 minus 2 is 0. And that reaction, whose delta Ng is 0, its Kp and Kc would definitely be equal. So Kp is equal to Kc for the reaction. Look at the second reaction. Calculate delta Ng for the second reaction. Number of moles of gaseous product, which is 1 plus 1, 2, minus number of moles of gaseous reactant, which is 1. So 2 minus 1 comes out to be 1. So I would say your Kp will be equal to Kc RT raised by delta Ng, that's 1. Look at the third reaction. Calculate delta Ng for the third reaction. Delta Ng for the third reaction is equal to number of moles of gaseous product, which is 2, minus number of moles of gaseous reactant, which is 1 plus 3, 4. So 2 minus 4 is minus 2. So I would say Kp will be equal to Kc RT raised by delta Ng. This is the relation between Kp and Kc for the reaction. Similarly, look at the next reaction, fourth one. Calculate delta Ng for it. Delta Ng is equal to number of moles of gaseous product. This is not the gaseous product, it is solid. Nothing to do with this. This is the gaseous product. How many moles? 1. Minus. There is no gaseous reactant as well. So delta Ng value here will be directly equal to 1. And if delta Ng is equal to 1, I would say your Kp would be equal to Kc RT raised by delta Ng, that's 1. Okay? Perfectly done. Similarly, if I ask you, what will be the units of Kp and Kc for this reaction? This is the reaction whose delta Ng is 0. So Kp and Kc will be unitless. Right? What about the Kc unit for this reaction? Delta Ng is 1. Kc unit will be mole per liter raised per 1. Kp will be atm raised per 1. Similarly, mole per liter raised per minus 2 and atm raised per minus 2. Mole per liter raised per 1 and atm raised per 1. Yeah? Perfect, guys? Is that clear? Look at this question. Can you tell me the answer of this question? In which of the following Kp and Kc are not equal? In which of the following Kp and Kc are not equal? Tell me. In which of the following Kp and Kc are not equal? Kp and Kc are not equal when delta Ng is non-zero. See, if you look at the last reaction, calculate delta Ng for the last reaction. Number of moles of gaseous product, 2, minus number of moles of gaseous reactant, 1, because this is a solid form. So 2 minus 1 is 1, which is non-zero. If delta Ng is non-zero, that means Kp, Kc won't be equal. Right? That means Kp and Kc won't be equal. I believe this is clear to everyone. Just give me a second, guys. Done? Exactly. It's going to be D. It's going to be D. Now, guys, there are a few more things which you need to know. What are those things? Whenever you reverse a reaction, for example, you have got the reaction like this. A gives B. Let's say its equilibrium constant is K. Let's say its equilibrium constant is K. For example, you are reversing the same reaction. When you reverse the same reaction, I would say this is something it becomes. B gives A. When you reverse the reaction, equilibrium constant is inversed. That means if the equilibrium constant was K here, now it's going to be 1 by K. Now it's going to be 1 by K. Okay, point number 1. Point number 2. You have got the reaction, for example, A gives B, whose equilibrium constant is K. Whenever you multiply a reaction by some number, that number goes to the power of equilibrium constant. So, if I multiply this reaction by some number n, it becomes Na gives Nb. So, I multiplied this reaction by number n. That number goes to the power of equilibrium constant. So, equilibrium constant of this reaction becomes K raised power n. Similarly, my dear students, for example, you have got the reaction like this. A plus B gives C. D gives E. For example, these are the reactions. Let's say equilibrium constant of this reaction is K1. Equilibrium constant of this reaction is K2. Now, for example, if you are adding these two reactions, I would say your net reaction becomes A plus B plus D. It gives what? It gives C plus E. Now, when you add the reactions, remember equilibrium constants are multiplied. So, if I ask you what is going to be the equilibrium constant of this net reaction, is final reaction, it's going to be K1 multiplied by K2. So, these are the 3 things which I would want every one of you to remember. Number 1, when you reverse the reaction, equilibrium constant is inversed. Okay? When you multiply a reaction by some number, that number goes to the power of equilibrium constant. Point number 3, on adding the reactions, equilibrium constants are multiplied. These are the 3 things which you need to remember. Then only you can solve the questions based on characteristics of equilibrium constant. Okay? Am I clear till here? Everyone wants in the chats? Sir, GOC already today. GOC is already done. GOC is already done in the day before yesterday's session. KK sir has taken that. Wassim sir, शादी मुबारक हो, थोड़ा रेस्ट कर. Tell me, people, quickly. Is it clear? Is it clear? Everyone? Everyone? Rita, it's not very important. Are you getting married? Seriously? No, I got married. I'm not getting married. You do not see my Instagram posts. Public now. All clear, people? Why would I lie? I actually got married. Do you see this? Yeah? Chalo, let's move on. Let's move on now. Let's see what kind of questions can be framed from this characteristic of equilibrium constant. Let's exactly see. For For example, this is the first and the basic question, guys. First and the basic question. Understand. We are given with a reaction like this, N2 plus 3 times H2. It gives what? It gives 2 times NH3. It gives 2 times NH3. Its equilibrium constant is given to me as 49. Its equilibrium constant is given to me as 49. Now, as per the question is concerned, I need to calculate equilibrium constant for this reaction. I need to calculate equilibrium constant for this particular reaction. Now, first of all, the reaction whose equilibrium constant is given to you, the reaction whose equilibrium constant is given to you, you are going to use this reaction to make the one whose equilibrium constant is to be calculated. Understand what I'm trying to say? I'm telling you, this is the reaction whose equilibrium constant is to be calculated. This is the reaction whose equilibrium constant is given. I'll be using this reaction to make this reaction. Understand how? If I first of all reverse the reaction, it becomes 2 times NH3. It gives N2 plus 3 times H2. And since when you reverse the reaction, equilibrium constant is inversed. So now the equilibrium constant will be 1 by 49. Earlier it was 49, now it's going to be 1 by 49. Now if I multiply the same reaction with 1 by 2. So first of all what I did? First of all I reversed. Now I'm multiplying this reaction with 1 by 2. So 2 gets cancelled. It becomes NH3. Gives half of N2 plus 3 by 2 times H2. Since I multiplied this reaction with 1 by 2, so this 1 by 2 goes to the power of equilibrium constant. So it's 1 by 49 whole raised power 1 by 2, which comes out to be 1 by 7. Do you see? I was supposed to calculate the equilibrium constant of this reaction only. I was supposed to calculate equilibrium constant of this reaction only, and we got to know it as 1 by 7. Right? We got to know it as 1 by 7. Perfect. Let's move on to the next question so that it becomes like very clear to you. For example, this is the question. I'm given 3 reactions, their equilibrium constants are given. I need to calculate equilibrium constant for this particular reaction. And the reaction for which I am supposed to calculate equilibrium constant, I am supposed to make this reaction from these 3 reactions. The reaction whose equilibrium constant is to be calculated. We are supposed to make the reaction from these 3 reactions. Now, how exactly I'm going to do that? Understand. My dear students, if you look carefully, this is the reaction which I'm supposed to make. And in this reaction, NH3 is on left side. NH3 is on left side. Now, among these 3 reactions, do you see NH3 anywhere? Yes, I can see NH3 here. But on right side. But on right side. So, what do I need? I need NH3 on left side. But here NH3 is on right side. So, I'll reverse this reaction first. When I reverse the reaction, it becomes twice NH3, gives N2 plus 3 times H2. And when you reverse the reaction, equilibrium constant is inversed. Now, the equilibrium constant will be 1 by K1. It will be 1 by K1. Right? Similarly, guys, the reaction which I have to make. In this reaction, twice NO is on right side. In these reactions, here I can see twice NO. That's already on right side. So I need not to reverse this reaction. I'll write the reaction as such. N2 plus O2 gives 2 times NO. I made no change with this reaction, so its equilibrium constant remains unaffected. K2 as such. Okay. The reaction which I have to make, I need 3 times water on right side. I need 3 times water on right side. Here we have got water already on right side, but it's not 3 times water. So multiply this with 3. When you multiply with 3, that 3 goes to the power of equilibrium constant. Now write the same reaction again. 3 times H2 plus 3 by 2 times O2. It gives what? It gives 3 times water. Its equilibrium constant is K3 raised power 3. Okay. Now if I add these 3 reactions, N to N2 cancels out. 3 times H2 cancels out. So it will be twice NH3 plus O2 plus 3 by 2 O2 makes it 5 by 2 O2. It gives 2 times NO plus 3 times H2O. Was I supposed to make this reaction only? Check it out. Was I supposed to make this reaction only? Yes. And how did I get this reaction? When I added these 3. And when you add the reactions, equilibrium constant is multiplied. Equilibrium constant of first reaction was 1 by K1 multiplied by second reactions. Equilibrium constant is K2. Third one is K3 raised power 3. So this is the equilibrium constant for the reaction which I was supposed to calculate. Tell me once in the chats if this is clear. Tell me once in the chats if this is clear. Every one of you. Every one of you. Yes? Perfect. Now guys, there is one more important thing that I need to discuss with you. What is that? calculation of Kp and Kc. Calculation of Kp and Kc by mole method and by degree of dissociation method. Now, before going into the calculation of Kp and Kc by mole method and degree of dissociation method, there is one more simple and important thing that I need to share with you. What is that? That is very, very, very important. So first of all, let's try to cover that. That is calculation of moles. Calculation of moles of reactants and products. Calculation of moles of reactants and products at equilibrium. How do we calculate the moles of reactants and products at equilibrium? Try to understand properly what I'm going to say, because this is very, very, very important. Your complete ionic equilibrium and chemical equilibrium is based on this. Okay? See, guys. See, guys. For example, you have got the reaction like this. A gives B plus C. Let's say this is the reaction. For example, I'm writing here a term, time t is equal to 0. Tell me at time t is equal to 0, whether the reaction would have started or not. At time t is equal to 0, reaction would not have started. I'll say at time t is equal to 0, we'll only have reactant in the container. At time t is equal to 0, we'll only have reactant in the container. Let the moles of reactant at time t is equal to 0 is A. Since the reaction has not started, so B and C have not got formed yet. So this will be 0, this will be 0. Initially at time t is equal to 0, there will be only reactant in the container. And let there be A moles of reactant in the container initially. B will be 0, C will be 0. Now there will be a time when equilibrium will be established in the reaction. There will be a time when equilibrium will be established in the reaction. And let's assume at that point of time, when equilibrium is established, let's assume out of A moles of reactant, X moles got converted into product. Let's say at equilibrium, out of A moles of reactant, X moles got converted into product. So I'll be left with A minus X. So what is this A minus X? These are the moles of reactant present in the container at equilibrium. Right? Now use the stoichiometry. How? I'll say 1 mole of A gives 1 mole of B. So X moles of A would have given X moles of B. 1 mole of A gives 1 mole of C. X moles of A would have given X moles of C. Right? So what is A minus X? These are the moles of reactant present in the container at equilibrium. These are the moles of B present in the container at equilibrium. These are the moles of C present in the container at equilibrium. Got it? Now, one more thing, guys. For example, I've got the reaction like this. A gives 2 times B plus 3 times C. A gives 2 times B plus 3 times C. Let's say at time t is equal to 0. Moles of reactant are A. This will be 0, this will be 0. Now at equilibrium, out of A moles of reactant, imagine X moles got converted into product. So I'll be left with A minus X. 1 mole of A gives 2 moles of B. X moles would be giving 2X. 1 mole of A gives 3 moles of C. X will be giving 3X. So these are the moles of reactants products present in the container at equilibrium. Understood? Now guys, one more thing. For example, if I do certain chains, let's say the reaction is A gives B plus C, okay? Now, at time t is equal to 0, let's say there are A moles of reactant in the container. Since the reaction has not started yet, but I'm assuming before the start of the reaction, I am keeping some B and C in the container as well. Before the reaction starts, I'm keeping some B and C in the container. Let's say I'm keeping some B moles of this and I'm keeping some C moles of this. Before the start of the reaction itself, I'm keeping B and C in the container as well. Now, as the reaction starts, more moles of B, more moles of C will get formed. Already before the start of the reaction, I kept B moles of this and C moles of this in the container. Now, at equilibrium, out of A moles of reactant, X moles got converted into product. So I'll be left with A minus X. Already there were B moles of this product in the container. Now some more moles would have got formed. 1 mole of A gives 1 mole of B. X would give X. Similarly, this will be C plus X. So these are the moles of reactants products present in the container at equilibrium. My dear students, this is how you calculate moles of reactants products present in the container at equilibrium. Got it? Now, understand what exactly I'm going to do. Something important. That is calculation of Kp and Kc by which method? Calculation of Kp and Kc by mole method. Understand what exactly I'm going to do. I'll give you one example so that you will remember it. For example, I'm taking the reaction as 2 times A, it gives B plus C. 2 times A gives B plus C. This is the reaction which I'm taking, a general reaction. You tell me first of all in the chats, what about delta Ng for this reaction? I would say delta Ng is equal to number of moles of gaseous product minus number of moles of gaseous reactant. Delta Ng is 0. And since we already know that reaction whose delta Ng is 0, its Kp and Kc would be equal. That reaction whose delta Ng is equal to 0, its Kp and Kc would be equal. We know that already. Now understand what exactly I'm going to do. At time t is equal to 0, let there be A moles of reactant. This would be 0, this would be 0. Now at equilibrium, assume that out of A moles of reactant, X got converted into product. So I'll be left with A minus X. These are the moles of reactant in the container at equilibrium. Okay. Now guys, 2 moles of A gives 1 mole of B. 2 moles of A gives 1 mole of B. 1 mole of A gives 1 by 2 moles of B. X will give 1 by 2 into X. Similarly, this will be also X by 2. So what are these terms? These are the moles of reactants products present in the container at equilibrium. These are the moles of reactants and products present in the container at equilibrium. Now, my dear students, let's assume that this reaction is taking place in a container whose volume is V liters. When we divide moles with the total volume, what do we get? We get concentration. So these are the concentrations of reactants products in the container at equilibrium. These are the concentrations of reactants products in the container at equilibrium. Okay. And if you got the concentrations of reactants products in the container at equilibrium, you can easily make the expression of Kc. How do we make the expression of Kc? It's going to be concentration of B at equilibrium raised power 1, concentration of C at equilibrium raised power 1, concentration of A at equilibrium raised power 2. So tell me, what is the concentration of B at equilibrium? It's X divided by 2V. Concentration of C at equilibrium, again X by 2V, so square, divided by concentration of A at equilibrium, that is A minus X divided by V raised power 2 here. So what all things will get cancelled out? V square cancelled out. So it becomes X square divided by 2 ka square is 4 multiplied by A minus X ka square. So this is the expression of your Kc for this particular reaction. This is the expression for your Kc for the reaction which I gave you. Now, how do we get the expression for Kp? Well, Kp expression will be equal to partial pressure of B at equilibrium raised power 1, partial pressure of C at equilibrium raised power 1 divided by partial pressure of A at equilibrium raised power 2. Now the point is, we have to calculate the partial pressures of reactants products. We have to calculate the partial pressures of reactants products. How do we calculate the partial pressures? Understand. Tell me one thing. How many total moles are there in the container at equilibrium? How many total moles are there in the container at equilibrium? At equilibrium, we have got these moles of reactant, these moles of product, and these moles of product. So total moles in the container at equilibrium, this plus this plus this. X by 2 is X, X gets cancelled. So total moles at equilibrium is A. So my step will be, what I'll be doing? I'll be dividing A minus X with total moles. I'll be dividing X by 2 with total moles. I'll be dividing X by 2 with total moles. What do I call these terms now as? Moles of reactant at equilibrium divided by total moles at equilibrium. Moles of B at equilibrium divided by total moles at equilibrium. Moles of C at equilibrium divided by total moles of equilibrium. I'll be calling them as mole fractions. These are mole fractions of reactants products at equilibrium. And remember, my dear students, let the total pressure of the mixture at equilibrium. Since at equilibrium, if I ask you, at equilibrium, how many gases are there in the container? If I ask you, at equilibrium, how many gases are there in the container? I'll say at equilibrium, there are 3 gases in the container. So can I say at equilibrium, we have got a gaseous mixture? Let the total pressure of the gaseous mixture at equilibrium be Pt. So if I multiply mole fractions with the total pressure at equilibrium, I call these terms as partial pressures. These are the partial pressures of reactant products present in the container at equilibrium. Now, since you got the partial pressures, you can write the expression of Kp easily now. Partial pressure of B at equilibrium, how much is that? That's X divided by 2A multiplied by Pt. Partial pressure of C at equilibrium, that's again the same, so it is square. Partial pressure of A at equilibrium, that also we calculate, that's A minus X multiplied by PT divided by A. Raised power stoichiometric coefficient here, that is 2. So what all things will get cancelled out? Check it out once. I'll say PT square cancels, A square cancel. So it's going to be X square divided by 2 ka square is 4 multiplied by A minus X ka square. So look at the expression of Kp. Is it coming out to be same as that of Kc? Yes. Why is that? Because this was the reaction whose delta Ng was equal to 0. And we know that particular reaction whose delta Ng is 0, its Kp and Kc would be always equal. Did you understand, people, what I did? Did you understand? Say yes or no once in the chats, quick. Every one of you. Say yes or no once in the chats, quick. Every one of you, quickly in the chats. Everyone wants the chats. All right. Now see how I'm going to utilize all this in the questions. For example, this is the question. This is the question, guys. Try to understand. We are given with a reaction. The reaction is A plus B. It gives 2 times C. This is the reaction that's given to me. Now, if you look at the question carefully, we are starting with 2 moles of A, 1 mole of B, and 1 mole of C. We are starting with 2 moles of A, 1 mole of B, and 1 mole of C are placed in a 10-liter container. Okay. Now, guys, at equilibrium, let's say out of 2 moles of reactant, X moles reacted. So I'll be left with 2 minus X. Right? This will be also 1 minus X. And this will be 1 plus 1 gives 2, X gives 2X, 1 plus 2X. These are the moles of reactants products in the container at equilibrium. Now, if I divide these moles with the total volume is how much? 10 liters. If I divide these moles with the total volume, what do I get? I'll be getting the concentration. These are the concentrations of reactants products at equilibrium. In the question, they have mentioned that the final concentration of C means concentration of C at equilibrium, which as per our calculation is 1 plus 2x divided by 10, and as per the question, it is given to me as 0.2. 0.2 is 2 by 10. 10 gets cancelled out. So x will come out to be 0.5. If x is equal to 0.5, put the value of x in these parameters. So 2 minus 0.5 comes out to be 1.5. 1.5 divided by 10, 0.15 molar. Similarly, 1 minus 0.5 is 0.5. 0.5 divided by 10 is 0.05. Similarly, this entire term is given to me as 0.2 molar. So I got the concentrations of all the reactants products at equilibrium. And if I got the concentrations of all the reactants products at equilibrium, I can easily get the expression for Kc. Kc is concentration of C at equilibrium, raised power stoichiometric coefficient 2, concentration of A at equilibrium, raised power stoichiometric coefficient 1, and concentration of B at equilibrium, raised power stoichiometric coefficient 1. I know all these concentrations. Concentration of C at equilibrium, that is 0.2, raised power stoichiometric coefficient 2, divided by concentration of A at equilibrium, that is 0.15, raised power stoichiometric coefficient 1. Concentration of B at equilibrium, that is 0.05, raised power stoichiometric coefficient. You just have to solve this and get the value of Kc. That's it. Understood, people? Understood, everyone? So this is how, these are the sorts of the questions which you frequently get in your examination. Look at this question. A similar sort of question. Sorry. First of all, as far as this question is concerned, we are given the reaction as X plus Y gives this. As far as the question is concerned, we are starting with 1 mole of X, 1.5 moles of Y, and 0.5 moles of Z. in a 1 liter container. In a 1 liter container. First of all, tell me, out of 1 mole of reactant, X moles would have got, they would have reacted. So I'll be left with 1 minus X. This would be 1.5 minus X. This will be 0.5 plus 2X. Why is that? Because already there were 0.5. Now 1 mole of X gives 2 moles of this. So X will give 2X. So 0.5 plus 2X. If I divide these moles with the total volume is 1 liter. Divide with total volume 1 liter, you got the concentration. These are the concentration of reactants products in the container at equilibrium. As far as the question is concerned, the concentration of Z at equilibrium is given to me. Concentration of Z at equilibrium is given to me as 1 molar, right? And as per our calculation, what is the concentration of Z at equilibrium? That is 0.5 plus 2X. This is equal to 1. X will be equal to 0.25. You got the value of X. You got the value of X. Now put the value of X in these parameters. 1 minus 0.25 will be 0.75. 1.5 minus 0.25 will be 1.25. And put the value of X here, you'll be getting exactly as 1. So I got the concentrations of reactants products at equilibrium. Now put the expression of Kc. Expression of Kc is concentration of Z at equilibrium raised by stoichiometric coefficient 2 divided by concentration of X at equilibrium raised by stoichiometric coefficient 1, and similarly concentration of Y at equilibrium raised by stoichiometric coefficient 1. What is the concentration of Z at equilibrium? That's 1. 1 ka square is 1 divided by concentration of X at equilibrium, that is 0.75 raised by stoichiometric coefficient 1. Concentration of Y at equilibrium, that is 1.25 raised by stoichiometric coefficient 1. When you solve this, the value comes out to be 16 divided by 15. The value of Kc is coming out to be 16 by 15. And as per the question, it is equal to X by 15. So when you compare, I can say the value of X here, nothing but 16. That's something I was supposed to calculate. Yeah? Perfect, guys? Is that clear? Now, let's see what other types of the questions can be framed. Look here. There will be some questions, my dear students. See, till now, I was starting with moles. A0, 0, A minus X, 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 right? Something like that. There will be some questions wherein you are not supposed to start with the moles. You are supposed to start with the pressure directly. Some questions will be there wherein you are supposed to start with the pressure directly. Let's say there's a question here on the screen. Understand what I'll be doing. The reaction that's given to me is AB3 gas. It gives AB2 gas plus half of B2 gas. This is the reaction. The question says if the initial pressure of AB3 is 900. Initial pressure of AB3 is 900 torr. So I have to start with the pressure directly. Earlier I was starting with the moles, right? Now I'm starting with the pressure directly. So this is 900, this will be 0, this will be 0. Now the way you used to treat moles, the way we used to treat moles, in the similar way you have to treat the pressure. So this will be 900 minus X torr. 1 gives 1, so X gives X. 1 gives 1 by 2, X gives X by 2. So I'll say these are directly the partial pressures of reactants products at equilibrium. I started with pressure. So I directly got the partial pressures of reactants products at equilibrium. Now in the question, they mentioned that the total pressure at equilibrium is equal to how much? 1000 torr. Total pressure at equilibrium is equal to 1000 torr. Can I say total pressure at equilibrium will be equal to the sum of partial pressures at equilibrium? Total pressure at equilibrium will be equal to sum of partial pressures at equilibrium. So it's going to be 900 minus X plus X by 2. This value is equal to 1000. Correct? So this got cancelled. So X value is equal to 200. X value is equal to 200 torr. So 900 minus 200 is 700 torr. X value is equal to 200. X by 2, 200 by 2 is equal to 100 torr. So you got the partial pressures of reactants products at equilibrium. Now get the Kp expression. Kp is going to be partial pressure of AB2 at equilibrium, that is 200, raised by stoichiometric coefficient 1. Partial pressure of B2 at equilibrium, that's 100, raised by stoichiometric coefficient 1 by 2. Partial pressure of AB3 at equilibrium, that's 700, raised by stoichiometric coefficient 1. So this will be 10 into 200 is 2000, 2000 divided by 700 is 20 by 7. So this is the value of Kp which you are supposed to calculate. right? This is the value of Kp which you are supposed to calculate. These sort of questions can also be asked. These sort of questions can also be asked. Now, guys, the point is, how do we calculate Kp and Kc with the help of degree of dissociation method? Right now, I was teaching you about the Kp Kc calculation by mole method. Now, how do we do the Kp Kc calculation by degree of dissociation method? Understand what I'll be doing. First of all, you should know what degree of dissociation is all about. Alpha. Alpha is nothing but it's Nd divided by Ni. What is Nd and what is Ni? Nd means number of moles of reactant, dissociated. Dissociated means converted into products. Dissociated means converted into products. Ni are basically the initial moles of reactants. These are the initial moles of reactants. Initial moles of reactants. Now understand what exactly I'm going to do. Let's say you've got the reaction like this. A gives B plus C. Okay. At time t is equal to 0. Let the initial moles of reactant is A. This is 0. This is 0. Let the degree of dissociation is alpha. And you know alpha is Nd divided by Ni. What is Ni? Ni are the initial moles of reactants. Initial moles are A. So can I say Nd is equal to A into alpha? Nd is equal to A into alpha. What is Nd? I'll say these are basically the moles of reactants which are dissociated. These are the moles of reactants which are getting converted into products. These are the moles of reactants which got converted into products. So can I say at equilibrium, I started with A moles of reactants. Out of A moles of reactants, how many are getting converted into product? Remember, from now onwards directly. From A, always A alpha you will subtract. From A moles of reactant, always A alpha moles will get converted into product. So I'll be left with A minus A alpha. Right? Now, use the stoichiometry. 1 gives 1, A alpha gives A alpha. 1 gives 1, A alpha gives A alpha. So these are basically the moles of reactants products present in the container at equilibrium. Right? My dear students, in mole method, this A alpha I used to call as X basic. Do you remember? It used to be A minus X, X and X. So technically A alpha is nothing but X. Technically A alpha is nothing but X. Got it? Let's take a look on the detailed overview of all of this. For example, I'm giving you the reaction like this. Reaction is 2 times A gives B plus C. Let's say all of them are in gaseous phase. You tell me first of all, what about the delta Ng for the reaction? You will say delta Ng is 0. If delta Ng is 0, that means Kp and Kc are equal, right? Kp and Kc are equal. Now I want to make the expression. For Kp and Kc in terms of alpha, not in terms of X. In terms of alpha, not in terms of X. In terms of X, we have already seen. Now let's see the expression in terms of alpha. First of all, at time t is equal to 0, let the moles of this is A, this is 0, this is 0. Let the degree of dissociation is alpha. So at equilibrium, from A moles of reactant, A alpha moles would have got converted into product. So I'll be left with A minus A alpha. Correct? 2 moles are giving 1. 2 moles are giving 1. 1 will give 1 by 2. A alpha gives A alpha by 2. This will be also A alpha by 2. These are the moles of reactants products in the container at equilibrium. If you got the moles of reactants products in the container at equilibrium, you can calculate the concentration of reactants and products at equilibrium. How? Divide the moles by the total volume. So A minus A alpha divided by V. A alpha divided by 2 divided by V. A alpha divided by 2 divided by V. These are the concentrations of reactants products in the container at equilibrium. These are the concentrations of reactants products in the container at equilibrium. Therefore, I can easily write the expression for Kc. Concentration of B at equilibrium. Concentration of B at equilibrium, raised power stoichiometric coefficient. Concentration of C at equilibrium, raised power stoichiometric coefficient. Concentration of A at equilibrium, raised power stoichiometric coefficient, that's 2. Kc will be equal. Concentration of B at equilibrium, that is A alpha divided by 2V. Concentration of C at equilibrium is the same, so it becomes square. Divided by concentration of A at equilibrium, that is A minus A alpha divided by V, raised power stoichiometric coefficient 2. So Kc will be equal. What all terms will get cancelled out? V square cancels, A square cancels. So it is alpha square divided by 2 ka square is 4 multiplied by 1 minus alpha ka square. This is the expression of Kc for this reaction. Right? Now, what about Kp? What about Kp? In order to calculate Kp, what do we need? We need the partial pressures of reactants products at equilibrium. We need the partial pressures of reactants products at equilibrium. My dear students, tell me, how do we get the partial pressures? How do we get the partial pressures? First of all, I'll be calculating total moles in the container at equilibrium. How many total moles are there in the container at equilibrium? A minus A alpha plus A alpha by 2 plus A alpha by 2. That comes out to be A. So divide this A minus A alpha with the total moles. Divide this A alpha by 2 with the total moles. Divide this A alpha divided by 2 with the total moles. So I got the mole fractions. I got the mole fractions of reactance products in the container at equilibrium. These are the mole fractions of reactance products in the container at equilibrium. Let the total pressure at equilibrium is PT. Let the total pressure of the mixture at equilibrium is PT. Now mole fraction multiplied by total pressure of mixture. That gives me what? That gives me partial pressure. Few minutes back, we discussed that. Now this A and A gets cancelled, so it becomes 1 minus alpha multiplied by PT. Similarly, A gets cancelled. This alpha divided by 2 multiplied by PT. This is alpha divided by 2 multiplied by PT. What are these terms? What are these terms? These are the partial pressures of reactance products at equilibrium. These are the partial pressures of reactance products at equilibrium. If you got the partial pressures of reactance products at equilibrium, we can easily calculate Kp value. Kp will be equal partial pressure of B at equilibrium. How much is that? Alpha Pt divided by 2 multiplied by partial pressure of C at equilibrium. That's again the same, so it's square, divided by partial pressure of A at equilibrium. That's 1 minus alpha multiplied by Pt raised power stoichiometric coefficient. So Kp will be equal. Kp will be equal. Pt square cancels. Alpha square divided by 4 multiplied by 1 minus alpha. This is basically the value of Kp. Do you see Kp and Kc are coming out to be same here also? Why? Because the reaction has got delta and G 0. And that particular reaction was delta and G 0. Its Kp and Kc will be always equal. Tell me once in the chats if this is clear. Tell me once in the chats, people, if this is like very, very, very clear to you. Quick. Quickly in the chats. Tell me. Is it done? Perfect. Now, guys, there is one more topic left. What is that? That is your Lee-Chatelier principle. That is your Lee-Chatelier principle. Okay? Lee-Chatelier principle. Let me summarize all of this in just one slide. Let me summarize all of this, all of the Lee-Chatelier principle in one slide. I'm not going to explain you what Lee-Chatelier principle is, how this happens, how that happens. No, I'll just tell you those things which are sufficient for you to solve the question. They're based on Lee-Chatelier. Rest, I'm not going to explain anything unwanted, okay? Whatever is required, solve the question from Lee-Chatelier's principle, I'll be talking about those things. Understand? The first thing here is effect of addition or removal. Effect of addition or removal of a reactant or product. Effect of addition or removal of a reactant or product. Understand, guys, what exactly I'll say. For example, you have got the reaction like this. R gives P. Let's say this reaction is already at equilibrium. The reaction is already at equilibrium. Now, at equilibrium, remember the system is highly stable. It is the most stable at equilibrium. Since there is equilibrium in this reaction, so the system is at maximum stable state. Now, at equilibrium, when the system is at equilibrium, whatever things we do to the system at equilibrium, equilibrium does opposite of that. This is something which you need to remember. What is meant by that? Since the reaction is at equilibrium. Now, what I'm doing is, I want to increase the concentration of reactant. The reaction is already at equilibrium. Now, still I want to increase the amount of reactant. I want to add more reactant in the container. Whatever we do to the reaction, equilibrium does opposite of that. If I'm increasing the concentration of reactant, equilibrium will try to decrease it. How equilibrium will decrease the concentration of reactant? It will shift the equilibrium forward. I'll say equilibrium shifts forward. Equilibrium shifts forward. Okay. Similarly, if I decrease the amount of reactant, equilibrium will try to increase it. If I decrease the amount of reactant, equilibrium will try to increase it. How equilibrium increase the amount of reactant? When shift is backward. When equilibrium shifts backward. Okay. Similarly, if I increase the amount of product, equilibrium will try to decrease it. How? It will shift the reaction backward. Equilibrium shifts backward. If I decrease the amount of product, equilibrium will try to increase it. How? It will shift the reaction forward. Equilibrium will shift the forward. Equilibrium shifts forward. Simple. Whatever I do to the reaction, equilibrium is going to do opposite of that. Remember one more thing. If you see any reactant or product in solid state, if there will be any reactant or product in which form? In solid state. Remember, on adding or removing a solid at equilibrium, remember, there will be no shift. There is no shift. For example, you have got the reaction like this. Calcium carbonate solid. It gives calcium oxide solid plus carbon dioxide gas. This is the reaction, okay? Now you are increasing or decreasing. Now if you are increasing or decreasing the amount of calcium carbonate, or if you are increasing or decreasing the amount of calcium oxide, there will be no shift. Remember it directly. It has got the logic as well, which can be explained on the basis of QC, but I'm not going to go there. I'm not going to talk about the logics and stuff. Just remember things which are required to solve the question. So whenever a solid is added or removed at equilibrium, there will be no shift at all. Number one. Number two, guys. Point number two. Effect of change in pressure. I'll show you the questions of it in some time. First of all, let me summarize all of this in one slide so that it becomes easier for you. Effect of change in pressure. Remember, on increasing the pressure, equilibrium shifts in the direction. In which the gaseous moles decreases. So if we have got the reaction at equilibrium and will be increasing the pressure, on increasing the pressure, equilibrium will shift in the direction in which gaseous moles decreases. What does that mean? For example, you have got the reaction like this. A gas gives B gas plus C gas. This is the reaction taking place in a container. How many gaseous moles on reactant side? 1. How many gaseous moles on product side? 1 plus 1, 2. So, due to the forward reaction, gaseous moles are increasing. Because of backward reaction, gaseous moles are decreasing. Now, if I increase the pressure, since the reaction is at equilibrium, and I'm increasing the pressure, on increasing the pressure, what happens? On increasing the pressure, the equilibrium shifts in the direction in which gaseous moles decreases. Now, in which direction here gaseous moles are decreasing? Backward direction. I'll say on increasing the pressure, there will be backward shift. Similarly, on decreasing the pressure, there will be forward shift. For this particular area, which I gave it to you. Okay? Similarly, guys, one more thing which you want to take a note, which you need to take a note of. If you have got the reaction whose delta Ng is 0, will be 0. Remember, on changing the pressure, there will be no shift. That particular reaction whose delta Ng will be 0, Remember, on increasing or decreasing the pressure, in that particular case, there will be no shift, right? Similarly, third point. Third point is basically effect of temperature. Effect of temperature. My dear students, we have got two types of reactions, endothermic, exothermic. We have got two types of reactions, endothermic and exothermic. Remember, in case of endothermic reactions, equilibrium constant is directly proportional to temperature. In case of exothermic reactions, equilibrium constant is inversely proportional to temperature. Now, one thing which directly you will remember. In case of endothermic reactions, on increasing the temperature, there will be forward shift. In case of exothermic reactions, on increasing the temperature, there will be backward shift. Just these two things you have to remember. Yeah? In case of endothermic reactions, on increasing the temperature, there will be forward shift. On increasing the temperature in exothermic, there will be backward shift. Remember it directly. Similarly, there are three more points, and we are done with chemical equilibrium chapter. Three more points we have. That is effect of inert gas. Effect of inert gas addition. Effect of inert gas addition. Effect of inert gas addition at constant volume and at constant pressure. At constant pressure. Remember, my dear students, when you add inert gas at constant volume, there will be no shift. For example, you have got the reaction. A reaction is taking place in a container. Okay? Now you are adding inert gas at constant volume. Remember, there is no shift at that point of time. Now, if you are adding inert gas at constant pressure, equilibrium shifts in the direction in which gaseous moles increase. And remember at the same time one more point. That reaction whose delta Ng is 0. On adding inert gas at constant pressure, there will be no shift in that particular case. These are two more important things which can be asked in your examination. I'll show you its application in some time. Just wait for it. And the last thing, guys, here, what is that? That is effect of catalyst. Effect of catalyst. Remember, your equilibrium constant does not depend on the catalyst. Catalyst has got no role when it comes to equilibrium constant. So there will be no shift on addition of the catalyst. Okay? Now see, all of this you can use in the questions and you can easily solve them. What do you think about this question? Everything is here. Predict the direction of shift at equilibrium if H2 is added. First of all, if you look carefully, sir, will you teach Henry's law? Henry's law is there in solution chapter. Solution chapter will be taken in class 12th physical. This is class 11th. See, guys, first of all, look at the reaction. H2 is the reactant. If you add more H2, if we add more H2, equilibrium is going to decrease it. How? Forward shift. In the first case, forward. If we add NH3, if NH3 is added, equilibrium will decrease. If we increase NH3, equilibrium will try to decrease. How? Backward shift. Since heat is absorbed means endothermic. And when temperature is increased in endothermic reaction, 2 minutes back I told you, when temperature is increased in endothermic reaction, forward shift. When inert gas is added at constant volume, no shift. When inert gas is added at constant pressure, equilibrium shifts in the direction in which gaseous moles increases. So in which direction gaseous moles are increasing? So on reactant side, you have got 4 gaseous moles, 2 gaseous moles. In the backward direction, gaseous moles are. So the shift will be in the backward direction. Got it? All the things are here in one question. Everything. Whatever things I told you, you're done. Whatever things I told you, you just have to remember them and we are done. Okay, tell me one more thing. What do you think will be the answer of this question? What do you think will be the answer of this question? I'm seeing closed container. That means volume constant. Inert gas added. Inert gas added at constant volume. No shift. No change. No shift. No change. No change in the concentration of anything. Yeah? Got it? Is it clear, guys? What do you think about this one? The equilibrium amount of carbon dioxide, can be increased by. How can we increase the equilibrium amount of carbon dioxide? Equilibrium amount of carbon dioxide can be increased if the reaction shifts forward. Now, when can reaction shift forward? When will reaction shift forward? If we increase the amount of reactant, equilibrium will try to decrease it. At that point of time, forward shift will happen and the amount of products will increase. So I'll say by increasing the amount of CO, by increasing the amount of reactant, equilibrium will try to decrease it, so it will shift the reaction forward. Got it? With this, our chemical equilibrium is done. We are going to take a small break till 5:30 and we'll start the ionic equilibrium. Okay? So break till 5:30 and we will be kickstarting the ionic equilibrium. All right? Whatever things I taught you in chemical equilibrium, these things will be asked in the exam. Apart from this, nothing will be asked. Don't worry. Chill. I'll see you exactly, all of you, at 5:30 because we are going to kickstart the ionic equilibrium chapter. Okay? So let me have some coffee, tea. Get back. Exactly at 5:30. Sorry, guys. I was late a bit. Can you all hear me? Am I audible, visible? Every one of you? Can you all hear me? Am I audible, visible to every one of you? Tell me once in the chats, quick. All right. Is everyone back? Everyone is back. Just give me a minute and we'll be starting, okay? Just give me a minute. We'll be starting. Okay. Should we start, guys? Now we are going to start what? Now we are going to start the ionic equilibrium. Right? Now we are going to start the ionic equilibrium. So first of all, let me tell you what all topics can be asked from the ionic equilibrium chapter. What all topics can be asked from ionic equilibrium chapter? My dear students, the first topic is going to be ionization, or you call it as the dissociation constant. Ionization or the dissociation constant of a weak electrolyte. Ionization or the dissociation constant of the weak electrolyte. This is going to be the first topic, number one. Number two is going to be Ostwald's dilution law. Number 3 is going to be the common ion effect. After discussing the common ion effect, we'll be directly going into the pH calculation. pH calculation. And after pH calculation, we'll go to the buffer. And after buffer, the last topic will be solubility product. Solubility product. Well, these are the topics from which the questions will be asked from the chapter Ionic Equilibrium. These are the topics from which questions will be asked from the chapter Ionic Equilibrium. Okay? So let's talk about them one by one, and let's try to understand and analyze the kind of questions which will be framed from these topics. Okay? Let's try to understand, guys. The first topic which I mentioned over here, that is dissociation or ionization constant of a weak electrolyte. First of all, if I ask you what is a weak electrolyte? What is a weak electrolyte? My dear students, any substance which on dissolving in water, does not dissociate completely. Any substance which on dissolving in water does not dissociate completely is something I call as weak electrolyte. Okay, is something I call as weak electrolyte. So any substance which is partially ionized in water, any electrolyte which is partially ionized in water is what you call as weak electrolyte. So first of all, the first topic which I'm going to talk about here, what is that? That is the ionization or dissociation constant. Ionization or the dissociation constant of a weak electrolyte. Of a weak electrolyte. Let the weak electrolyte is AB. Let the weak electrolyte is AB. Ionization or the dissociation constant of the weak electrolyte AB. My dear students, first of all, imagine that you have got a container filled with water. Imagine that you have got a container filled with water. And in that container, you are introducing a weak electrolyte AB. In that container, which is completely filled with water, for example. This is the container which is filled with water. Okay. Now, in this container, you are introducing a weak electrolyte AB. Now, this weak electrolyte, as since it partially ionizes, it does not ionize 100% in water. Let me tell you, weak electrolyte, it always remains in equilibrium with its ions. When a weak electrolyte is introduced in water, it partially ionizes. It remains in equilibrium with its ions. Now, my dear students, let's assume that at time t is equal to 0, the concentration of this weak electrolyte is C molar. Let's say the concentration of this electrolyte is C. This would be 0, this would be 0. Now, the degree of ionization, let's say that's alpha. So tell me at equilibrium, what would be the concentration of reactant left? It will be C minus C alpha. Like we used to do in chemical equilibrium, A0, 0, A minus C alpha, A alpha, A alpha. Similarly, here this is C0, 0, C minus C alpha. Now 1 gives 1, C alpha gives C alpha, 1 gives 1, C alpha gives C alpha. So if I ask you, what are these terms? What are these terms? These are the concentrations of reactants and products. These are the concentrations of reactants and products present in the container at equilibrium. Okay. Now, my dear students, the term which I'm introducing here, that is Ki. Ki is what you call as ionization or dissociation constant. Ki is what you call as ionization or dissociation constant. Its expression is written the similar way as you write Kc expression. Its expression is written as the similar way, the way we write Kc expression. So it's going to be concentration of A positive at equilibrium raised power stoichiometric coefficient. Concentration of B negative at equilibrium raised power stoichiometric coefficient divided by concentration of AB at equilibrium raised power stoichiometric. Okay. Now, first of all, what is the concentration of A positive at equilibrium? That is C alpha. What is concentration of B negative at equilibrium in the container? C alpha divided by. What is the concentration of AB in the container at equilibrium? That is C minus C alpha. So if I take C common, C gets cancelled. I would say Ki is equal to C alpha square divided by 1 minus alpha. So remember, this is the expression of ionization constant of the weak electrolyte. It is C alpha square divided by 1 minus alpha. Okay? C alpha square divided by 1 minus alpha. Now, my dear students, one more thing. If I say let alpha is less than 0.05, I'm saying let alpha is less than 0.05. What does that mean? Alpha is less than 0.05. It means this weak electrolyte, its ionization in water is less than 5%. I'm assuming the weak electrolyte which we have introduced in water, its ionization in water is less than 5%. Now, if alpha is less than 0.05, that means I'm considering alpha to be very small. That means this weak electrolyte, some percentage, less than 5% of it has ionized in water. Less than 5%. Okay? If that means alpha value I'm considering very small. If alpha is very small, that means instead of 1 minus alpha, I can just write 1. Instead of 1 minus alpha, I can just write 1. Therefore, I can say Ki is equal to C alpha square, or alpha can be calculated as under root of Ki divided by C. Alpha can be calculated as under root of Ki divided by C. So if you get the value of alpha from here, under root of Ki by C, Ki will be given in the question, C value will be given in the question. So you can get the alpha value here. And my dear students, once you get the alpha value, you can easily calculate the concentration of A positive in the container at equilibrium, and you can calculate concentration of B negative in the container at equilibrium. And both are equal to what? Both are equal to C alpha. Right? Alpha you have calculated from here. C value is given. So we can easily calculate the concentration of ions in the container at equilibrium. Okay? Perfect, guys. Is it clear? Every one of you? Every one of you? Every one of you quickly in the chats. Everyone once, quickly in the chats, people. Perfect. Now, my dear students, let's try to understand a few more things. Then I'll show you what kind of questions can be framed. First of all, your weak electrolytes can be your weak acids, or they can be your weak bases. Weak acids, weak bases. They are the examples of weak electrolytes. Okay? Weak acids, weak bases, they are the examples of your weak electrolytes. Now, understand here, I'm marking the heading as ionization constant. Ionization constant of a weak acid. Ionization constant of a weak acid. And here I'm marking the heading as ionization constant. Ionization constant of a weak base. Ionization constant of a weak base. Well, ionization constant of weak acid. Well, I should be writing it as Ki. Ki is the ionization constant of weak electrolyte. Ki is the ionization constant of weak electrolyte. But when the weak electrolyte is weak acid, at that point of time, Ki is called as Ka. Similarly, when the weak electrolyte is your weak base, at that point of time, Ka is called as Kb. Ka is called as Kb. Ka is called as Kb. Okay? Now try to understand what exactly I'm going to say. Understand properly. Imagine that I'm taking a weak acid HA. It's a weak acid, for example. Okay? Now you're introducing this in water, in a container. So it is going to remain in equilibrium with its ions. Ions are going to be H positive aqueous plus A negative aqueous. Okay? Let's say at time t is equal to 0, its concentration is C. This is 0, this is 0. Now at equilibrium, this is again going to be C minus C alpha. This will be C alpha, this will be C alpha. Now, Ki right now is called as Ka here because the weak electrolyte taken is weak acid and its expression will be same, C alpha square divided by 1 minus alpha. Now after that, what do we do? Again, let alpha is less than 0.05. Therefore, 1 minus alpha can be written as 1. Therefore, I can say Ka is equal to C alpha square, or I can say alpha is equal to under root of Ka divided by C. Now, what is my point here? My point is just one. My point is just one. What is that? Alpha and Ka, are they directly proportional? Yes. So remember one thing, my dear students. More the value of Ka for the acid, more the value of Ka for the acid, more will be the value of alpha for the acid. More the value of Ka for the acid, more will be the value of alpha for the acid. And more the value of alpha means more is the degree of dissociation of the acid. That means the acid has got dissociated more into its ions. That means in the container, H positive ion concentration will be more. If H positive ion concentration in the container is more, what does that mean? That means acidic strength. That means acidic strength of the solution will be more. And if acidic solution of the solution will be more, that means pH of the solution is less. So that particular acid whose Ka value is more, that particular acid whose Ka value is more, its pH value will be less. Okay? Its pH value will be less. Now, similarly, if I talk about a weak base, for example, you have taken a weak base like BOH. Let's say this is a weak base. And when you introduce this weak base in water, it's going to partially ionize as B positive and OH negative. Okay, again the same process. This is C, this is 0, 0. This will be C minus C alpha. This will be C alpha, even this will be C alpha. Now you can write the expression for Kb. Kb is equal to C alpha square divided by 1 minus alpha, right? So let alpha value is less than 0.05. Therefore, instead of 1 minus alpha, I can just write 1. So I can say Kb is equal to C alpha square, or I can say alpha is equal to under root of Kb divided by C. So tell me, alpha and Kb, are they directly or inversely? They're again directly. They're again directly. So remember, more the dissociation constant, more the ionization constant of the weak base, more the ionization constant of the weak base, more is the alpha value for the weak base. And more alpha value for the weak base means more base has got ionized, more base has got dissociated into the ions. That means in the container, OH negative concentration will be more. And if OH negative concentration is more, that means basic strength of the solution is more. Basic strength of the solution is more. And if the basic strength of the solution is more, that means pH of the solution will be more. Got it? Did you understand this particular point? Did you understand, people? Everyone? Quick. Quickly, people. It's pH increase here, pH increase. Okay, just give me a second. All right. So I believe this particular stuff is clear. So let's try to solve one question so that you can understand what we have to do here. Look at the question, guys. Calculate the concentration of each ion at equilibrium. Calculate the concentration of each ion at equilibrium. What is 0.1 molar solution of a weak electrolyte AB? So you have taken a weak electrolyte AB, and for example, you have introduced in water. So definitely, this weak electrolyte would remain in equilibrium with its ions. Ions are A positive aqueous and B negative aqueous. Correct? Right? So first of all, what do we have to calculate? Concentration of each ion at equilibrium. We have to calculate concentration of A positive at equilibrium as well as concentration of B negative at equilibrium. Few minutes back, I told you their concentration is equal to C into alpha. Now C is the concentration of weak electrolyte. C is the concentration of weak electrolyte that's given to me 0.1 molar. What do I need? I need alpha. How do I get alpha? Alpha, I told you a few minutes back, under root of Ki by C. What is Ki value? Ki value is given to me as 10 raised power minus 5. C value is how much? That is 0.1, 10 raised power minus 1. So this is root of 10 raised power minus 4. So it is 10 raised power minus 2. Right? So this is alpha. If you got alpha, you got the concentration of ions. C into alpha. How much is C? C is 0.1, means 10 raised power minus 1. Alpha is 10 raised power minus 2. So the value comes out to be 10 raised power minus 3 molar. Similarly, the value comes out to be 10 raised power minus 3 molar. This is how you calculate the concentration of ions at equilibrium. Perfect. Is this particular question clear to everyone? Whatever I taught you till now, same thing I'm using here. That's it. Now, my dear students, there is one thing which I would want to share with you. What is that? Okay, let's try to solve one question first. Then we'll talk about few more things. I think I'm going to fall ill. Okay. Calculate the H positive ion concentration of a 0.05 molar CH3COH. CH3COH is a weak acid. It is a weak acid. So first of all, how this weak acid will undergo dissociation? How this weak acid will undergo dissociation? It will undergo dissociation as CH3CO negative and H positive. It will undergo dissociation like this. Okay. Now, first of all, the concentration of this acid is given 0.05 molar. Ka value is also given. What do I need to calculate? Concentration of H positive. Few minutes back, I told you concentration of ions at equilibrium will be equal to C into alpha. C value is given 0.05. What do I need? Alpha. How do I calculate alpha? Under root of Ka divided by C. Right? Under root of Ka divided by C. Because the weak electrolyte is the weak acid here. What is Ka value? It is 1.25 into 10 raised power minus 6 divided by, what is C? C value is given to me as 0.05. So this is 1. This is 25 times. Root of 25 is 5 into 10 raised power minus 3. This is alpha. Therefore, C into alpha. C is how much? 0.05. 0.05 is 5 into 10 raised power minus 2. Alpha value is 5 into 10 raised power minus 3. So the value comes out to be 25 into 10 raised power minus 5. This is the concentration of H positive in the solution at equilibrium, which I was supposed to calculate. Right? Now, my dear students, there is one thing which is called as Ostwald's dilution law. There is one thing which is called as Ostwald's dilution law. And what this Ostwald's dilution law says, in simple words, I would say Ostwald's dilution law says that with dilution, with the dilution, the degree of ionization of a weak electrolyte, that increases. The degree of ionization of the weak electrolyte with dilution increases. Okay? So basically, imagine that this is the container, and this container is filled with water. This container is filled with water. Now you have introduced a weak electrolyte AB here in this container. Now when you introduce this weak electrolyte AB in the container, it's going to partially ionize as A positive aqueous and B negative aqueous. It's going to partially ionize. It won't ionize completely. Now if you put more water in the container, that means you are doing the dilution. With the dilution, what happens to the degree of ionization of weak electrolyte? With dilution, the degree of ionization of the weak electrolyte that increases. With the dilution, the degree of ionization of the weak electrolyte increases. That means on introducing water, on introducing more water, on doing the dilution, this weak electrolyte keeps on getting ionized more and more into its ions. Okay? Got it? With the dilution, the degree of ionization of weak electrolyte increases. That means when I keep on doing the dilution, the weak electrolyte will keep on ionizing, with dilution. That's what is said in the science terms as degree of ionization of the weak electrolyte increases with dilution. This is your simplest law, which is called as the Ostwald's dilution law. Okay? Perfect, guys. Got it? Now there is one more thing, guys, which I need to share with you. What is that? That's called as common ion effect. What happens in common ion effect? My dear students, I'm not explaining this in detail. I'll just tell you those things which are required to solve the questions. Imagine we have got a weak electrolyte here, CH3COH. And this CH3COH, since it's a weak electrolyte, it's going to remain in equilibrium with its ions. Ions are CH3CO negative and H positive. Let the concentration of this weak electrolyte is C. This is 0, this is 0. Let its degree of ionization is alpha. So this will be C minus C alpha. This will be C alpha. This will be C alpha. So basically this weak electrolyte is in equilibrium with its ions. Now if I introduce the strong electrolyte like HCl, I'm introducing a strong electrolyte in the same container. If I introduce the strong electrolyte in the same container, strong electrolyte ionizes completely. It will ionize completely into its ions. Let its concentration initially is C1, this is 0, this is 0. Now it's a strong electrolyte, completely ionized. So this is 0, this is C1, this is C1. Now do you see two electrolytes in the container? Weak, strong. And both are having one ion in common. So whenever you have got a weak electrolyte and a strong electrolyte, both are having one ion in common. Right? If I ask you what is the concentration, total concentration of this common ion, the concentration of H positive generated from weak electrolyte is C alpha. The concentration of H positive generated from strong electrolyte is C1. So the total H positive concentration will be C1 plus C alpha. Now what happens when you have weak electrolyte, strong electrolyte, having a common ion in the same container? The degree of ionization of the weak electrolyte that decreases. Right? It suppresses, it decreases. Due to which, wherever you would want to neglect alpha, you can do that. So C1 plus C alpha can be just written as C1. Okay. Now, if I want to write the dissociation constant of this weak acid, Ka, it is going to be concentration of CH3CO negative, that is C alpha. Concentration of H positive, that is C1, divided by concentration of CH3COH, that is C minus C alpha. Perfect. So C and C got cancelled. As I told you, because of common ion effect, alpha gets reduced very much. There will be suppression, decrease in the value of alpha. So you can neglect alpha wherever you want it. Right? So this will be alpha into C1 divided by. Instead of 1 minus alpha you can neglect here, it will be 1. So you can calculate alpha here. It will be Ka divided by C1. Now which alpha this is? Is it the old alpha or new alpha? This is the value of alpha after the common ion effect is operated. So remember, because of the common ion effect, alpha value decreases and the final alpha value will be called Ka divided by C1. Where C1 is the concentration of this strong electrolyte. Just remember this particular point, guys. Alpha, the new alpha value after the common ion effect is operated is equal to Ka by C1. Right? Ka by C1. Perfect. Now, if I ask you what is the concentration of the common ion, concentration of common ion is equal to C1. Simple. C1 is the concentration of strong electrolyte. So can I say concentration of common ion is entirely decided by the strong electrolyte? As you can see, concentration of H positive here is C1, right? And concentration of strong electrolyte was also C1. You can just generalize one statement. You can say concentration of common ion is entirely decided by what? By the strong electrolyte, right? Is entirely decided by the strong electrolyte. Perfect. Now see, where do I use this concept? Look here carefully, guys. This is a question. You'll understand where I'll be using this. Calculate the concentration of H positive at equilibrium if 0.1 molar HCl is added in an aqueous solution containing 0.1 molar CH3COH. So in the container, you have got CH3COH, whose concentration is 0.1 molar, right? So in the beginning, this will be CH3CO negative. And with CH3CO negative, you'll be writing H positive as well. Let's say this is C, this will be 0, this will be 0. Let the degree of dissolution alpha. So this is C minus C alpha, this will be C alpha, this will be C alpha, correct? Now in the same container, you have introduced HCl. HCl is a strong electrolyte, would have completely ionized as H positive plus Cl negative. H positive plus Cl negative. Let its concentration is C1, which is given to me in the question how much? It is given to me in the question as 0.1 molar. Now this is 0, this is 0. Since it's a strong electrolyte completely ionized, so this will be 0.1 molar, this will be 0.1 molar. So technically this is C1 basically. This is also C1. Now do you see in the same container you have got weak electrolyte, strong electrolyte, both having one ion in common. What is the concentration of that common ion? It will be C1 plus C alpha. Now because of common ion effect, the degree of ionization of the weak electrolyte decreases, due to which C1 plus C alpha can be just written as C1. Now I don't have to do all of this. What do I just need? I just need the concentration of H positive. Is H positive the common ion? Yes, H positive is the common ion. Yes, H positive is the common ion. And the concentration of common ion is decided completely by the strong electrolyte. What is the concentration of strong electrolyte here? 0.1. So the concentration of common ion is equal to C1. And C1 value is equal to 0.1 molar. As simple as that. Okay. If they ask you, what is the final concentration of CH3CO negative in the container? After the common ion effect is operated, concentration of CH3CO negative will be C into nu alpha. C value is given 0.1 and alpha value, few minutes back I gave you the formula Ka divided by C1. Ka is given, C1 is given. Put the values, get the answer. Got it? Is it clear, people? Everyone? Tell me guys in the chats if this is clear. Clear, people? Perfect. Now let's move on to one more thing. What is that? How do we calculate the pH? First of all, I'll show you how do we calculate the pH of strong acids and strong bases. So I'm writing here the pH calculation. pH calculation. pH calculation. First of all, we'll do the pH calculation of strong acids or strong bases. How do we do the pH calculation of strong acids or strong bases? Or the strong bases. Now understand, guys. How do we do the pH calculation of strong acids or strong bases? What is the strong acid, first of all? A strong acid ionizes completely. A strong base ionizes completely. For example, here I'm writing 10 raised power minus 3 molar HCl aqueous. HCl is a strong acid. I want to calculate its pH. I want to calculate pH of this solution. You tell me, first of all, how this HCl will undergo dissociation. HCl in water would have dissociated as H positive aqueous and Cl negative. Okay. Now, at time t is equal to 0, its concentration I've kept as 10 raised power minus 3 molar. This is 0. This. Now, since it's a strong acid, completely ionized, completely dissociated, so I'll be left with nothing. 1 mole gives 1, 10 power minus 3 gives 10 power minus 3. Similarly, this will be 10 power minus 3. So I got to know in the container, the concentration of H positive is nothing but 10 raised power minus 3 molar. I got to know, since I had 10 raised power minus 3 molar HCl in the container, so I got to know in the container the concentration of H positive is 10 raised power minus 3 molar. So how do we calculate pH? pH is nothing but P stands for minus log. It is minus log of H positive concentration. So it is minus log of H positive concentration is 10 raised power minus 3. The value comes out to be 3. pH of the solution is nothing but 3. pH of the solution is equal to 3. Okay. For example, understand. Let's say I'm writing 10 raised power minus 7 molar HCl aqueous solution. I want to calculate its pH. Now tell me, first of all, this HCl, how it would have dissociated in water? H positive aqueous and Cl negative aqueous. This is how it would have dissociated. Initially, at time t is equal to 0, let its concentration be 10 raised power minus 7 molar. This would be 0. This would be 0. Now it's a strong acid, completely ionized. I'll be left with nothing. 1 gives 1. 10 power minus 7 gives 10 power minus 7. This is also 10 power minus 7. So as per our calculations till now, can I say concentration of H positive in the solution should be 10 raised power minus 7 molar? Yes. So as per this, pH should be equal to, pH is minus log of 10 raised power minus 7. The value should come out to be 7. But if the pH of the solution is 7, then it's supposed to be neutral. It is supposed to be neutral. But we have taken acid. Its pH should be less than 7. Its pH should be less than 7. But as per our calculations, it's coming out to be 7. So what do we do? In such cases, what you have to understand is, since you are introducing HCl in water, in water there are already H positive ions. In water there are already H positive ions, which are equal 10 raised power minus 7 molar. Now you are introducing HCl. Due to which more H positives are generated in the container. So concentration of H positive generated from HCl, that's again 10 power minus 7. The concentration of H positive which was there in the container due to water, that was 10 power minus 7. That's at 25 degrees centigrade, that's always 10 power minus 7. Now the concentration of H positive which is getting generated after the addition of acid, that's also 10 raised power minus 7. Now you tell me, what is the net total H positive ion concentration? That is 10 power minus 7, 10 power minus 7, which is 2 into 10 power minus 7. Now you can calculate pH. pH will be equal to what? It will be minus log of net H positive, which is 2 into 10 raised power minus 7. Now, matter of calculation, when you solve this, the value comes out to be 6.7. The actual pH of the solution is nothing but 6.7. Is it clear? Is it clear, people? Quickly. Yes. Done, people? Can you tell me quickly in the chats? Is it done? All right, let's move on. Let's move on, guys. For example, I'm writing a question like this. 10 raised power minus 3 molar NaOH aqueous solution. I want to calculate its pH. First of all, NaOH is a strong base, right? It's a strong base. So first of all, when this NaOH is introduced in water, it will ionize completely as Na positive aqueous. And with Na positive aqueous, you'll be writing OH negative, right? Now, its concentration in the beginning is 10 raised power minus 3 molar. This would be 0, this would be 0. Now, this would be 0. This is 10 power minus 3, and this is 10 power minus 3. So, if I ask you what is the OH negative ion concentration in the container, it is 10 raised power minus 3 molar. If you got the OH negative concentration, you can calculate POH. P stands for minus log. Minus log of what? OH negative concentration. So, this is minus log. Minus log of what? 10 raised power minus 3. The value comes out to be 3. So, POH is 3. Now, all of you would have heard one result. pH plus POH is equal to 14 at 25 degrees centigrade. So, I can say pH is equal to 14 minus POH. 14 minus 3. That comes out to be 11. Right? That comes out to be 11. So, pH of the solution is nothing but 11. I hope these sort of questions you can easily solve. Now, guys, there is one more thing. How do we calculate pH of? How do we calculate the pH of the mixture? Mixtures of strong acids and strong bases. Mixtures of strong acids and strong bases. If you'll be having a mixture containing either 2 strong acids or 2 strong bases or strong acid and strong base, how do we calculate pH of the final solution? Understand. For example, if I talk about case 1 here, let's say, my dear students, these are the 2 containers I'm taking, and this one more container. Imagine that you have got a strong acid here in this container. Here also you have got a strong acid. So you have got 2 strong acids. You have got 2 strong acids. Let its normality is N1, volume is V1. Let its normality is N2, volume is V2. Now you are mixing these 2 strong acid here in this container. You are introducing them in this container. What do I get? I get a final solution here. This final solution is first of all going to be acidic. This final solution is going to be acidic because in this container, you have got 2 strong acids, right? So, in this particular final solution, the net H positive ion concentration is always equal to N1V1 plus N2V2 divided by V1 plus V2. And if you got the net H positive ion concentration, you can easily calculate the pH. which will be minus log of net H positive ion concentration. This is how you calculate the pH of the final solution. This is how we calculate the pH of the final solution. Okay. Similarly, guys, what if in the first container there is a strong base? Okay. In the second container also there is a strong base. Let its normality is N1, volume is V1. Let its normality is N2, volume is V2. Now you are mixing two strong bases in a container. So what do you get? You get a final solution. When you mix them, you get a final solution. That final solution is first of all going to be basic. How do I calculate net OH negative ion concentration in the final solution? It's again going to be N1 V1 plus N2 V2 divided by what? Divided by V1 plus V2. And if you got the net OH negative ion concentration in the final solution, you can calculate POH. And let me tell you, P stands for minus log of what? Minus log of OH negative net. And if you got POH, you can easily calculate pH, which is 14 minus POH. Got it? Am I clear, people? Am I clear? Am I clear? Am I clear till here? Guys, is it all clear? Can you tell me once in the chats if this is clear? So basically here I have mixed two strong acids. Here I have mixed two strong bases. Now there is one more case. There is one more case here. What if I take a strong acid in the first container and I take a strong base in the second container? Its normality is N1, volume is V1. Normality is N2, volume is V2. Okay? So if I mix them up, in this container, what do I get? I'll be getting a final solution. I'll be getting a final solution. If I mix them up, I'll be getting a final solution, right? Now, my dear students, this final solution, it can be either acidic, basic, or neutral. Now understand what exactly I'm going to say. If, for example, n1 multiplied by v1 is greater than n2 multiplied by v2, if n1 multiplied by v1 is greater than n2 multiplied by v2, then remember, the final solution is going to be acidic. The final solution is going to be acidic. And if the final solution is acidic, the net H positive ion concentration will be equal to N1V1 minus N2V2 divided by V1 plus V2. And if you got the net H positive ion concentration, you can calculate pH minus log of H positive net. Minus log of H positive net. Similarly, guys, if, for example, remember, if N2V2 is greater than that of N1V1, if N2 into V2 is greater than that of N1V1, then remember the final solution which is obtained, that will be basic in nature. If the final solution is basic, the OH negative ion concentration in the final solution will be equal N2V2 minus N1V1 divided by V1 plus V2. And at the same time, if you got the OH negative concentration, you can calculate POH. And once you calculate POH, you can easily calculate pH. Now, guys, the third case. If, for example, N1V1 is equal to N2V2, if N1V1 is equal to N2V2, remember the final solution is going to be neutral. The final solution is going to be neutral, right? It's going to be neutral. Its pH at 25 degrees centigrade is going to be 7. Am I clear? Who is continuously spamming? Who is this NTA, INC? You're blocked, bro. Thank you for joining in. Perfect? No, tomorrow is organic chemistry session. Tomorrow is class 12th organic chemistry session. I hope all of this is clear till here. Just give me a second. Can you solve this question? Can you solve this question for me? Can you give this question a try quick? It's a simple question though. you are mixing two strong acids. You are mixing two strong acids, right? Volume of the first solution is 400 ml. Its molarity is 0.5. I believe all of you would be knowing normality is equal to molarity multiplied by n factor. Molarity is 0.5 and n factor of H2SO4 is 2. So it would be 1. The second solution, its volume is equal to 400 ml. Its volume is equal to 400 ml. Its molarity is equal to 0.5. Therefore, its normality will be also 0.5. Why? Because n factor of HCl is 1. Now, since you are mixing two strong acids, so the final solution has to be acidic. And the net H positive ion concentration in the final solution is equal to N1V1 plus N2V2 divided by V1 plus V2. This is the net H positive ion concentration in the final solution. So N1 into V1, N1 into V1, that is 400 plus N2 multiplied by V2, that is 200 divided by V1 plus V2, that is 800. So this comes out to be 6 by 8. 6 by 8 is 3 by 4. 3 by 4. This is the net H positive ion concentration. Therefore, I can calculate pH as minus log of net H positive ion concentration. And this is going to be minus log of net H positive ion concentration is 3 by 4. So it is minus log of m by n, which is log m minus log n. So it's going to be minus times log 3 is 0.47, log 4 is 0.6. The value comes out to be 0.13. So this is the pH of the final solution. As simple as that. Understood? Understood, people? Is it clear? Yes, perfect. All right, there is one more case wherein you are supposed to calculate pH. What is that? How do we calculate the pH of weak acids? How do we calculate the pH of weak acids? pH of weak acid. Well, my dear students, I am going to give you a direct formula. Direct formula by means of which you can calculate pH of weak acid. And pH of weak acids means weak monoprotic acid. Weak monoprotic acid, which will give only one H positive. For example, let me take the acid as, let's say, CH3COH. It's a weak acid as well as monoprotic. Perfect. It is going to remain in equilibrium with its ions. Ions are CH3CO negative, and with that we have got H positive. Perfect. Now, since you have introduced CH3COH in water, perfect. The solution which we get, how do we calculate its pH? How do we calculate its pH? There is a formula for that, direct formula. Remember that. Half of it is pKa plus log C. Half of P of Ka plus log C. This is the formula by means of which you can calculate pH of a weak monoprotic acid whose alpha value is less than 0.05. Okay. Similarly, if you have got a weak base, which weak base? Monoacidic base. Monoacidic base. Its pOH is calculated as half of P of Kb plus log of C, where C is the concentration of the base. Remember these two results, they are valid for your weak acids and weak bases. Okay? I believe this is clear. And if this is clear, my dear students, then we can solve one simple question here. We can solve one simple question here so that you'll understand where do I use these formulas. See guys, the question is calculate the pH of 10 raised power minus 1 molar CH3COH. CH3COH is a weak acid. It is weak acid. It is monoprotic. It's weak as well as monoprotic. How do I calculate its pH? How do I calculate its pH? We know the formula. I've given you the formula already. pH is equal to half of P of Ka plus log of C. Okay. So first of all, P of K. P of K. P stands for minus log. Minus log of what? Minus log of Ka. So it is minus log of what is Ka? Ka is 1.8 into 10 raised power minus 5. Remember, this value is always equal to 4.74. This value is always equal to 4.74. So it is half of, this will be 4.74 plus log of C, where C is the concentration of acid. That's 10 raised power minus 1. Right? So it is half of 4.74 minus 1. Wait, I think I wrote the formula wrong here. Is it plus log C or minus log C? Can you check it out once? Otherwise, I'll have to derive it once. Can you check this formula once? I think this is minus log C. I think this is minus log C, yes. So this is 5.74 divided by 2. The value comes out to be 2.87. This is the pH of the solution. Let me modify the formulas wherever I have written it. This is pKa minus log. This is also pKb minus log. Minus log. Okay? Okay, guys? So I believe all of this you can easily solve from now onwards. Now there is one more topic here, that is buffer. That is buffer, right? What is a buffer first of all? Buffer is a solution. Buffer is a solution. Inside the buffer, whenever you introduce a small amount of acid or small amount of base, whenever you add small amount of acid or small amount of base in a buffer, its pH does not significantly change. Its pH does not significantly change. Whenever you add a small amount of acid or small amount of base in a buffer, its pH is not going to change a lot. Buffer always shows the resistance towards the change in pH. Buffer always shows resistance towards the change in pH. Okay? Buffer is the solution in which when you add a small amount of acid or small amount of base, its pH is not going to change that much. All right? It is going to show resistance towards the change in pH. Just remember that. And now we have got two types of buffers here which we should know. One is called as acidic buffer. One is called as basic buffer. Acidic buffer and basic buffer. My dear students, how this acidic buffer is made? Imagine that you have got a container containing a weak acid. Imagine you have got a container containing a weak acid. And in the same container, you have got the salt of same weak acid with a strong base. Imagine that you have got a container containing a weak acid, and in the same container, you have got the salt of same weak acid with a strong base. This complete mixture is what you call as the acidic buffer. For example, let's say the weak acid is CH3COOH. This is a weak acid. Now, do you know any salt of the same weak acid with a strong base? Imagine this weak acid is reacting with strong base NaOH. What kind of salt it's going to form? It's going to form CH3COONA. Perfect. So this is the weak acid. Salt of same weak acid with a strong base. This mixture here I'll be calling as the acidic buffer. This mixture here I'll be calling as the acidic buffer. Okay. Similarly, basic buffer. Whenever in the container you'll be having a weak base and salt of same weak base with a strong acid. Whenever in the container you have got a weak base and salt of same weak base with a strong acid, you call the mixture as the basic buffer. For example, if you have got a weak base like NH4OH, NH4OH is a weak base. Now, can you tell me any salt that this weak base forms with a strong acid? So NH4OH with strong acid like HCl, NH4OH plus HCl forms what? NH4Cl. Forms what? NH4Cl. Do you see in the container, we have got a weak base and the salt of same weak base with a strong acid, right? This is something I call as basic buffer. This is something I call as basic buffer. This is something I call as basic buffer, right? This is something I call as basic buffer. Now, my dear students, the point is how do we calculate pH of acidic buffers and how do we calculate pH of basic buffers? Remember, Remember this particular formula. In case of acidic buffer, pH is calculated as P of Ka plus log of concentration of salt divided by concentration of acid. Remember this result directly. pH is equal to P of Ka plus log of concentration of salt divided by concentration of acid. Similarly, pH of the basic buffer, pOH of the basic buffer is equal to P of Kb plus log of concentration of salt divided by concentration of base. These are the two formulas. One is the pH of acidic buffer, one is pOH of basic buffer. Okay. Now, how do we use these formulas? Let's try to solve one question so that you can understand this. For example, this is the question. This is the question, guys. You have got a container, and in this container, we have kept CH3COOH, whose concentration is 0.01 molar. And we have got CH3COONA, whose concentration is kept as 0.02 molar. So tell me first of all, which kind of buffer this is? Is this acidic buffer or basic buffer? Is this acidic buffer or basic buffer? Quickly. Is this acidic buffer or basic buffer? In the chats, quickly. You have got a weak acid, salt of same weak acid with strong base. It's an acidic buffer. How do we calculate pH of the acidic buffer? I give you the result. P of Ka plus log of concentration of salt divided by concentration of acid. Simple. Right? pK, P stands for minus log. And minus log of this value, few minutes back only I told you it's 4.74 plus log of, what is the concentration of salt? It's 0.02. Concentration of acid, 0.01. So this term becomes log 2. And log 2 is 0.3. So 4.74 plus 0.3 will be 5.04. Okay. Got it? Done, guys? Perfect. Now, guys, there are some questions which are asked about the solubility product as well. So I need to show you, first of all, how do you write the expression of solubility product first. I need to show you how do you write the expression of solubility product first of all. Okay? Understand and remember. Understand and remember. For example, you have got a sparingly soluble salt as AB. It is a sparingly soluble salt. Sparingly means its solubility is very, very, very less. Its solubility is very, very, very less. Now, this sparingly soluble salt, how it's going to ionize? It will ionize as A positive. And with A positive, you'll be having B negative. Okay? Now, if the solubility of this salt is S, if the solubility of this salt is S, I would say 1 gives 1, S gives S, this also S. So, when I need to write the KSP, solubility product expression for this salt, how it's written? Concentration of A positive, raised power stoichiometric coefficient, concentration of B negative, raised power stoichiometric. So, I'll say KSP expression for this AB salt is going to be, what is the concentration of A positive? It is basically S moles per liter. This is also S moles per liter. So, it's S multiplied by S, that comes out to be S square, right? This is how you write the KSP expression of the salt, which is of the type AB. Which is of the type AB. Similarly, my dear students, for example, you have got the salt of the type AB2. AB2. How will it undergo dissociation? It will undergo dissociation as A di positive aqueous plus 2 times B negative. Let's say its solubility is S. Now 1 gives 1, S gives S. 1 gives 2, S gives 2S. Okay, S gives 2S. Now, my dear students, if I need to write the expression for KSP, KSP expression is going to be concentration of A di positive, that's S raised power stoichiometric coefficient 1. Concentration of B negative, that is 2 times S raised power stoichiometric coefficient 2. So, its KSP expression will be written as 4S cube. Okay, 4S cube. Perfect. Now, guys, for example, you have got a salt of this type, a general salt, AXBY. A general salt, AXBY. How will it undergo dissociation? It undergoes dissociation as X times A plus Y. And you'll be writing Y times B minus X. Now, let me tell you, let its solubility is S. Since 1 gives X, S gives X times S. This is Y times S. Now, how do I write the expression for KSP? How do I write the expression for KSP? Concentration of AY positive, that is X times S, raised power stoichiometric coefficient. Concentration of BX negative, which is Y times S, raised power stoichiometric coefficient. Okay, this is how you can write the KSP expression for this particular salt. It can be further written as X raised power X, Y raised power Y, and it can be S raised power X plus Y. Because bases are same, powers are added. Okay. Now, people, now, what kind of questions I can frame from this? What kind of questions I can frame from this? Some simple questions we can frame. Let's say this is the question. KSP of MgOH whole twice is 3.2 into 10 raised power minus 14. Calculate its solubility. You can easily do it. Now tell me how MgOH whole twice will undergo dissociation. It will undergo dissociation as Mg di positive plus 2 times OH negative. This is how it undergoes dissociation. Let its solubility is S. This will be S. This will be 2 times S because the stoichiometric coefficient is 2. Now, how do I write the expression for KSP? Concentration of Mg di positive, that's S raised power stoichiometric coefficient 1. Concentration of OH negative, that's 2 times S raised power stoichiometric coefficient 2. So I can say KSP is nothing but it will be 4S cube, right? So S can be written as KSP divided by 4 whole raised power 1 by 3. Now what is KSP? KSP is given to me in the question 3.2 into 10 raised power minus 14. Divided by what? Divided by 4. Whole raised power what? 1 by 3. So this can be written as 0.8, or you can write it as 8 into 10 raised power minus 15. Raised power 1 by 3, which can be further written as 2 into 10 raised power minus 5 moles per liter. This is the solubility of MgOH whole twice in water, which I was supposed to calculate. So you can get these simple questions from solubility product, my dear students. Okay. My dear students, there is one thing which you will remember as exception. Hg2Cl2. You call it as mercurous chloride. How mercurous chloride undergoes dissociation? it undergoes dissociation like Hg2 di positive plus 2 times Cl negative. Remember this particular case. Mercurous chloride, it undergoes dissociation as Hg2 di positive and 2 times Cl negative. Now, let its solubility is S. This is S and this is 2 times S. Okay. So I have taken the mercurous chloride. This mercurous chloride has undergone dissociation as Hg2 di positive and 2 times Cl negative. Now, first of all, if I want to write the KSP expression, how do I exactly write the KSP expression? It is going to be concentration of Hg2 di positive, that's S, raised power stoichiometric coefficient 1. Concentration of Cl negative, that is 2 times S, raised power stoichiometric coefficient 2. So it is going to be 4S cube. So KSP is equal to 4S cube. So I'll say S is equal to KSP divided by 4 whole raised power 1 by 3. Now KSP value is given to me in the equation, I think. How much is that? 10.8 into 10 raised power minus 23. This is not 23, this is minus 23 divided by 4. When you solve this value will come out to be 27 into 10 raised power minus 24 whole raised power 1 by 3. So the value comes out to be 3 into 10 raised power minus 8 moles per liter. So this is basically the solubility of mercurous chloride, which I was supposed to calculate. And with this, we are done with the ionic equilibrium chapter as well. Okay. So guys, in your class 11th physical chemistry, we are left with one chapter, that's thermodynamics. But thermodynamics, I won't be teaching today. I'll be teaching that with the next marathon, which is 11th inorganic, which is periodic classification and chemical bonding. And with that, I'll be teaching thermodynamics also in that marathon. Okay? All right? The second marathon which we are having, that is inorganic. Class 11th inorganic, right? Class 11th inorganic. In that marathon, there is periodic classification, there is chemical bonding, and I'll be teaching you thermodynamics also in that marathon. Okay? So with this, I'll be taking a leave. I hope you enjoyed the session. Now do revise this particular session properly. Do revise this particular session properly. I'll be sharing its PDF also in the Telegram channel, right? And once I end the session, do let me know in the comment section. How did you find the session? Was it beneficial? Right? All of you, do let me know that in the comment section. Okay?